Okay. I hope you can
Yes,
can
sir.
see it on this. Okay.
Yes.
Thank you. And first of all, I would like to congratulate the organizers for this conference. It's a very nice initiative, and I'm glad to take part in this conference organized by the Vellore Institute of Technology. So, first of all, thank you to the organizers. What I would like to present you today is so we'll speak about the use of microgas turbines and the relation with the use of fuels. Different kind of fuels. Usually, microgas turbines use natural gas, but some other options are available. I will start with the description of the technology, and later I will show you some developments and some new features in these fields. For those of you that are not familiar with the technology, microgas turbines are high-speed turbo machinery that use open cycle Brayton cycles using regenerative or recuperative systems. As you see in this schematic, after the compression of air in a compressor, the air is preheated using a recuperator or regenerator, and later after the combustion, the gases at high temperature and pressure are expanded, and before leaving the gases to the ambient, these gases are used to preheat the air for the combustion process, and later usually in a cogeneration system. We'll see here in this we'll see here in this animation. It's a commercial one, but I think it's quite interesting. This is a commercial product that's a modular system, and you will see how maybe I can remove the air is used to cooling the generator, and after the compressor, it goes to the combustion chamber, and then it's used in the turbine to produce power. And finally, the gases go through the recuperator and to the ambient. This is the typical This is the typical configuration of a gas turbine. The features, the features of this technology are quite interesting because they have some advantages over the conventional engines, the reciprocating engines using pistons. One of the main advantages is the compactness. For the same capacity, these units are more compact. The weight is also lower, so they are very suitable also for transport applications in vehicles. The noise level is also quite low, and one of the advantages is also the environmental performance. The NOx emissions are much lower than the case of engines. Usually in engines, the combustion temperatures are higher, and we obtain also higher emissions of NOx. But in these systems, the working temperatures are lower. The efficiencies, we'll see it later, the efficiencies are a little bit lower, more modest than in reciprocating engines, but this is compensated by other features. One of the advantages also is the fuel flexibility. We can use any kind of gases, natural gas, biogas, synthetic natural gas, and so on, and also liquid fuels. There are different versions of microgas turbines using different types of fuels, from liquids to gas. There is another advantage of this kind of system with respect to reciprocating engines is the concentration of the waste heat in just one stream. In reciprocating engines, we have the heat to recover distributed with the cooling of the engine, the intercooler, the exhaust gases, and so on. So there are different sources, different streams that provide heat. In the case of the gas turbines, this heat is concentrated in just one stream, so it's easier to recover heat from a microgas turbine. Also, because there is only just one moving part in the system, the service periods and overhauls are longer. So the period is larger. So the objective of this presentation will be the review of these systems, because there is a renewed interest in microgas turbines and other small turbo machinery like organic Rankine cycles and so on, for the use of renewable fuels or clean energy technologies that provide biomethane or hydrogen or other what considered renewable gases. So the interest of microgas turbines has increased in the recent years. But it's a well-known technology, and as you see in this graph, this is the number of microgas turbines used for cogeneration applications in this case, in this example for the US, is quite large. It's about 400 microturbines in service in 2017, and in many applications, recreation, commercial buildings, hotels, family buildings, colleges, universities, wastewater treatment plants, and many other applications. So the variety of applications for this kind of systems is this kind of systems are present in many sectors. What we'll do in this presentation is to review the main features of microgas turbines and also recent developments in this area, in the area of microgas turbines. We'll start. We have seen more or less what is the configuration of the microgas turbine. It's a Brayton cycle, usually a regenerative Brayton cycle, using permanent magnets generators and power conditioning of the produced electricity for the connection to the grid. One of the characteristics of this system is the production of waste heat at quite high temperature, around 300 degrees centigrades. This temperature, this exhaust gas from the microturbine can be used not only for the production of hot water, but also for the production of steam. The exhaust gases can be used as a post-combustion in a boiler or something to produce steam. Also, it can be used directly in dryers, in the brick industry, tile industry, and so on. Also, in trigeneration, application trigeneration, it means, as you know, the production of power, the production of heating, and also the production of cooling using thermal-driven chillers. Another possibility is what we call polygeneration. In polygeneration, it's a technology where the microturbine can be integrated easily, and it's a step further beyond the concept of trigeneration. Typically, in trigeneration, as I said, we have the production of electricity, the production of heat and cooling, but with this heat, it can be used also for not only for heating, but also for other applications. This where we can get heat at different temperatures. We can use this heat to produce fuels, And then these renewable fuels can be also integrated with as a fuel for the microgas turbines. In these graphs here, we have a configuration where we produce, using the exhaust gases from the system, we produce thermal oil at high temperature, and then with this high temperature, we can drive an absorption chiller using ammonia water, so producing cooling at very low temperatures, maybe below 0 degrees centigrade. And also with the remaining heat from the system, we can produce hot water for heating or for other applications. The microturbine, as I said, is quite fuel flexible. We can use not only natural gas but also biogas, biomethane, and other kind of fuels. In the case of biogas, it's a conventional application, so there are standardized pretreatment processes using biogas for the conditioning of this gas prior to the combustion in the microturbine, and going from the initial pressure and temperature and high humidity and containing siloxanes, after the cooling, drying, the use of filters and the compression, we can condition this gas for the use in the microturbine, reducing the amount of siloxanes, the humidity, and the presence of sulfuric acid. Usually, just to give an idea of the sizes, 1,000 cubic meter digester, it could be enough to produce biogas to drive a 60 kilowatt of power microturbine. And with this microturbine, we produce around 120 kilowatts of recuperated heat that could be also more or less equivalent for the heating demand in a digester to keep the production of biogas. So this would be the conditions and the sizes in a conventional biogas plant. The integration of the use of the biogas in microturbines can be improved with the complete integration with other technologies. There are some questions that maybe later I will try to answer at the end of the presentation. I will try to answer the questions. Thank you. And in this integration, what we have is the microturbines using the biogas after the pretreatment, and the biogas using the microturbines can be also, if there are additional heat required, we can use natural gas, and this natural gas, the heat recovered from the system, from the gas turbines, can be used in an absorption chiller to produce cooling, and this cooling can be used to reduce the temperature, the air inlet temperature of the gas turbine, so to increase the power capacity, to increase the efficiency of the system, and also the cooling produced in this case for the absorption chiller can be also used to reduce the humidity of the biogas. So this is a complete integration of a 3-generation system using microgas turbines in the system. Obviously, the heat can also be used in the digester and to drive the absorption chiller. This could be one option. Another option, another set of solutions, it could be the direct use of the exhaust gas in the absorption chiller to get a lower temperature of the chilled water, to use directly the exhaust gas. If we use directly the exhaust gas, the temperatures are higher, and then we can produce cooling at a lower temperature. And the heat can be also used in a recuperator to produce the heating for the digester. This would be a complete integration of microgas turbines and absorption chillers in biogas plants. Here there is the reference if you want to know more details on this configuration. Okay, as I said, the microgas turbine exhaust can be used in different type of fuels, and also another characteristic is that usually microgas turbines do not use oil for the lubrication of the system, so the exhaust gases are free from oil and can be used directly in greenhouses with the CO2 to promote the growth of the plants. Also, microgas turbines are excellent technologies for the integration, as I said, in poly generation plants for the strategy of power to gas and later gas to power strategies. In this kind of systems, the gas turbines can use the synthetic methane obtained by the methanization using hydrogen from electrolysis and CO2 from the biogas, the gated biogas, so the separation of methane and the CO2. The CO2 can be used to produce synthetic methane that can be used in the gas turbines here, or also they can use biogas directly. So it's possible to use biomethane, synthetic methane, or the biogas directly. So the gas turbines can be a good technology for the integration of this kind of technologies, the connection of the renewables with the conventional sources of gases, and then to increase the profitability of renewables that are also this continuous production system, a source of not continuous source of energy. Okay, we have seen the advantages and applications of microgas turbines. What we will do now is to see what kind of gas turbines we have available we can use for our projects or what are commercially available and what are the developments in these fields. Okay. According to the definition of micro-cogeneration, the European Union in the cogeneration directive, we are speaking about micro-cogeneration when we are below 50 kilowatts. And between 50 and 1 megawatt, we speak about small systems. What we can do is, what we could classify the systems is ultra-low capacity systems that are ultra micro turbines, domestic gas turbines between 1 and 15 kilowatts, commercial micro gas turbines between 50 and 200 kilowatts, and large micro turbines that are between 200 and 1 megawatt. This would be more or less the classification. Okay. In going into each category of in each group, we have ultra microgas turbines with very low capacities. There are a few manufacturers. Here you have some pictures of the systems available, are usually used in ground or aerial vehicles for aeromodeling, for drones, or for humanoid robots and so on. And the advantage of this system is that they have a better energy density than batteries. You see that the size of these systems is really small, and even that they are also for propulsion purposes. There has been also some tests for the production of electricity using these systems. Above this category, between 1 kilowatt and 20 kilowatt, there is another group of microturbines that the main purpose is the substitution or the replacement of heating boilers for households and small businesses, small and medium enterprises. The idea of these systems is to produce the heat needed or supplied conventionally by a boiler, but using a microturbine. There are some, we'll not go into details, but there are some manufacturers here. There are those two examples from the Netherlands and the UK. So, two examples of this kind of systems that are the production of electricity is very small. For example, this one can modulate the electricity production from 3.2 to 1 kilowatt of electricity, but the main purpose is the production of heat. The possibility to use fuels is also, they are fuel flexible, and we can, they claim that they can use natural gas, including 23% of hydrogen mix using this system. And the same for these other systems that use non-recuperated and recuperated turbines in this case. The idea is to substitute a boiler, and you have the same power, the same heat production, but additionally you have the production of electricity. Above this category of domestic, there are the conventional commercial microgas turbines, like the custom product that was one of the first systems on the field. Here you have some examples from our laboratory. We are running a capstone of 30 kilowatts in our laboratory and producing about 60 kilowatts of heat for different purposes, for heating and also for the driving of absorption chillers. It's a very interesting system because it's possible to use a catalyst reduction module and also can be connected to the grid, modulated in different packet units, and also work in dual mode. So the system can connect and disconnect from the grid, depending if there is a problem, a failure in the grid or not. You can be connected or disconnected, working as a standalone, using the same unit. Okay. Another interesting product is the Ansaldo, the Turbec. It's interesting because it's a little bit larger. It's 100 kilowatts. The advantage is that the advantage of this system is that there is a version that is possible to be external fire. So you can burn in biomass, and then with this heat you can drive the system. So through the turbine, we are only working with air as working fluid. The capacity in that case is reduced from 100 kilowatts to 75 kilowatts, but it's very interesting because it consists of an externally fired unit. So this is very interesting, for example, to integrate microturbines in concentrated solar power plants. This could be one option for this connection. So we have seen the microturbines in the market, and now we'll see higher capacity units with a higher power capacity that are under development and will be commercialized very soon, along this year or next year. The capacity of this system, as you see here, is larger than the conventional microturbines, is about 300 kilowatts. They use multiple shaft units, so the system is larger. The configuration can be more sophisticated in the sense that it can use intercooler, multiple shaft units. And this is an example of the ICR turbine that has a capacity of 350 kilowatts. This is very interesting because additionally to this more complex configuration or higher efficiency. They use also a ceramic section for the firing that allows temperatures that are close to 1,100 degrees centigrade. So the efficiency reaches 39%. That's very interesting for this size. So this is a high efficiency microturbine. In parallel to that development, Aurelia Turbines is also providing a similar strategy, a similar multi-shaft system using also intercooler, and the efficiency is also very high, 40%. So this is a new generation of microturbines of higher capacity, high complexity, but offering an efficiency that is even higher than equivalent reciprocating engines. Even he said that the unit of 1,000 kilowatts will have even a higher efficiency. This, for this turbine, it is under development a hydrogen combustor in collaboration with the DLR from Germany. This is a Finnish company. So we have seen what's in the market, what will be, and the development and so on. What will be the features that we will see in the coming years in microturbines? One of the limitations is the turbine inlet temperature. The additive manufacturing that is started to be introduced in this kind of systems will allow to use also cooling in these first stages of the turbine, and also some new material like ceramics and so on will increase the turbine inlet temperature, so the efficiencies are expected to be higher. The use of magnetic bearings and air bearings is an advantage of micro gas turbines. Magnetic bearings will be the preferred option for the next future bigger size engines technologies. Using the advantage of using air or magnetic bearings is clear for the use of the exhaust gases, because they will be clean. Another advantage of the future technologies is the flameless oxidation or flameless combustion. That is a new type of low emissions combustion technology that it was developed initially for steel furnaces, and it will be introduced in microgas turbines. The Ansaldo turbine is also started working with flameless oxidation burner. In this case, what we need for this kind of high efficiency, low emission combustion is a high temperature for the reactants and also recirculation of the exhaust gases. So the presence of the oxygen will be low, and the advantage is that the temperature of this flameless combustion will be much lower, and the emissions, the NOx and emissions will be much lower than in the conventional combustion. It will be here. So we need high temperature in the input air. Also, the additional to the exhaust gas recirculation will need also the burning of hydrogen-rich mixtures. We'll have also the option for burning this kind of fuels. Another option, and this we are close to finish, to not extend too much the presentation. Additional to these new features, there is the possibility to integrate with other cycles and other technologies. As you probably know, the integration of gas turbines and solid oxide fuel cells will produce very high efficiency, even higher than the high capacity combined cycles, where we are efficiencies were having efficiencies close to 60%. We can go far than that using combination of fuel cells and gas turbines. Another interesting technology is the inverted Brayton cycle. It's a similar technology, the Brayton cycle, but in this case, it's the reverse. This cycle can be used by itself, or it can be used as a bottom-on cycle in gas turbines or reciprocating engines. In this case, in an inverted Brayton cycle, the air is first expanded in a turbine, is preheated, and after the combustion is expanded in the turbine. We can have this combustion chamber here, or we can use exhaust gases from another microgas turbine. So we can have this combustion chamber or these exhaust gases from our turbine. We expand this in this turbine, and later, after the expansion, we cool down this stream, and when it's at low temperature and low pressure, we compress again to the ambient pressure. So it's an inverted cycle that can be used as a bottom-on cycle and can improve the efficiency, producing a combined cycle, but instead of using a Rankine, an inverted Brayton cycle. And finally, just to conclude and have some time for questions, I would like just to summarize, telling that the microgas turbines are high-speed turbomachinery that usually it's an open Brayton cycle using regenerative cycles with permanent magnets. So it's a high-speed turbomachinery, so we need some conditioning of the power produced. It usually is oil-free. It requires low maintenance, and that makes this technology very attractive and comparative due to lower emissions, fuel flexibility. We have seen that there are some developments to introduce also the combustion of hydrogen, synthetic natural gas, and so on in this kind of system. And the interest of this microgas turbine is to use these renewable fuels in these systems. I also mentioned that there is a new generation of microgas turbines of higher capacity. So at higher capacity, there is the possibility to use a more complex configuration with intercoolers, multiple shafts, and so on. So the efficiency of this system can reach values of 40% that are very high. So this promise of high performance and use of clean fuels using flameless combustion, hydrogen, green hydrogen, and so on, it offers a good perspective for microgas turbines as distributed generation systems for the future. So thank you very much, and that's all from my side. Okay, thank you.
Thank you, Professor. And we received 3 questions regarding the presentation. So the first question is, excellent Professor presentation, and what could be the efficiency improvement through water injection while using biogas in micro turbine? Is there polygeneration plant in operation using this technology?
Yes, there are some plants using microgas turbines, mainly using biogas, and in water treatment plant, sewage water plant. This is the main application of microgas turbines. But we can find them in regular cogeneration and regeneration systems. Usually, it's more typical in biogas, because in countries like Spain, where our climate is really warm, so we don't need a lot of heating like in North Europe and so on. So our application, our niche of application is mainly in the use of recovery of fuels, of low capacity low heating value fuels like biogas, digester fuels, the landfill, sorry, and this kind of fuels that are low heating value, and also the engines, the reciprocating engines, have problems in some cases burning these gases. So this is the main application. For the use in power generation is very interesting because they can use also, it's not, it's a demonstration level, but they can use syngas, the result of the gasification. So it's the integration with renewable gases. It's a very promising field for microturbines. I don't know if I have answered exactly your question.
Yes, sir. The second question is flux is a low emission technology, as said, but when we burn mixers, for example, if hydrogen is burned, how is noxious emission being controlled? Are we using any emission resistors in turn?
The emissions.
Yes.
The emissions using the flameless combustion are reduced because of the temperature. No? The fuel is injected in the combustor in such a way and conditions, working at very high temperatures and very low presence of oxygen. So we need some exhaust gas recirculation there. And at these conditions, the combustion produces a lower amount of NOx than the regular combustion. This kind of combustion is tested in the Turbeck turbine in the Ansaldo, the one of 100 kilowatts, and it's a collaboration between the German DLR, the Aerospatial Agency of Germany, and this Finnish company that have an European project on that. They are working in the development of this burner.
Okay. The next question, it is there any limitation of contents like hydrogen carbon monoxide percentage for its input?
The concentration, sorry, the concentration of?
Is there any limitation of contents like hydrogen CO percentage, carbon monoxide percentage in the input?
No, the input, the main limitation of the input is related as a fuel, is related with the content of sulfuric acid and other acid gases. There is no other limitation. The heating value of the gases that is reduced because of the presence of CO in the input, it can be tolerated. So usually it's not a restriction, the low heating value of the fuel. The capstone turbines can be adjusted to use low heating value fuels, and they are usually used in some places where the gases are not suitable for the use of other engines of compression of reciprocating engines. So the presence of gases that reduce the heating value like CO and others, there is not a problem. The problem will come from the presence of siloxanes that are present in some biogas and other. This is the main concern: siloxane and sulfuric acid. This is one of the problems.
And the final question is about can pyrolysis oils be used as biofuels in these micro gas turbines? And are all the biofuels clean and green fuels?
Yeah, the possibility to use the products from pyrolysis in gas turbines is still open. So I think there are no plans working actually with these fuels, but it could be interesting to develop this kind of testing, because the micro turbines can use liquid fuels. They can use they can burn liquid and also gas. So both products from the pyrolysis could be used in microturbines, and would be possible to see what will be the best alternative. Use to condensate the gases and use it as a liquid in the system, or use both products separately in separate turbines. The products of pyrolysis, it could be also a source of energy for microturbines. Even the bio-oil, or condensing the gases and use them as a liquid, or separately, as I said, in liquid and gases. It could be an option. But currently, as far as I know, there are not units working using pyrolysis.
Okay. Thank you, Professor, and for joining us to give your research ideas and research works. Thank you very much.
Thank you. It has been a pleasure. Thanks.
Ma'am, Ranjitha ma'am.
Professor, can you please stop sharing your screen, sir? Professor John, sir.
Yeah.
Thank you, sir.
Okay.
Next session will be from Dr. Nazil Hassan. Dr. Nazil Hassan received the Bachelor of Engineering degree in Electrical and Electronic Information from Toyohashi University of Technology, Japan in the year 1997, and MS and PhD degrees in Electronic Engineering from University of Tokyo, Japan in the year 1999 and 2002 respectively. He is currently a Research Associate Professor at the Research Center for Advanced Science and Technology at the University of Tokyo. His research interests include ultra-high efficiency photovoltaic devices, spintronic devices, molecular beam epitaxy of compound semiconductors, material design and characterization. He is a member of various prestigious societies. He is also a fellow of the International Association of Advanced Materials, Sweden, for contribution to strengthening the advancement of material. He has been serving as a PI and co-PI of several government and international funded projects, also published various scientific articles of about 100 numbers. So now over to Sir. Sir, I would like to invite Dr. Azam Nazul to start the presentation. Sir?
Yes, thank you very much. I'm sorry, I had some trouble with my microphone.
No problems.
Good. So thank you very much, Dr. Vijayalakshmi, for the nice introduction. And today I'm going to talk about highly mismatched semiconductor alloys for high efficiency solar cells. So let me have some quick introduction of my current work. So these are the group and the funding agencies for this presentation. And so in Tokyo University, we have Professor Yoshitaka Okada's group. And from the United States, we have Dr. Vladek Valukovic in Lawrence Berkeley National Lab. And also we have Professor Kinman Yu from City University of Hong Kong. And recently we have another professor, last few years, it's not last few, it's in a way pretty long years with Professor Kalainathan in Viet University. And recently we have some collaboration going on solar cells. So, and these are the funding agencies. And just let me quickly show my university. This is the oldest university in Japan and established in 1877. And we do have 10 faculties right here. And Dr. Vijayalakshmi introduced me that I did my graduate studies from Faculty of Engineering under Electrical and Electronic Engineering here. And then I was long assistant professor with this faculty. Later, I moved to Research Center for Advanced Science and Technology, where currently I am a research associate professor, and we have 11 research institutes. And the location of this institute is at the center of Tokyo. So this is the center, one of the center of Tokyo. And the tallest building here is the office of the Tokyo mayor. And our institute right here, you can see a little bit green. Okay, so, and this green area is our campus. And probably it is difficult to see, this is our campus. So this is, so in Tokyo University, you have a couple of campuses. So this is one of the campus, and our research institute is right here. And now let me go to the background of my work. Okay, so this is a figure which forecast the world energy. Okay, this is from the group from Germany, that they are forecasting the world global energy demand by 2100. And currently we are right here, 2020. And how to read this figure? Okay, so the vertical axis, let's start from the vertical axis. This is the energy supply every year. Okay, this is the energy supply, and horizontal axis started from 2000 and all the way to 2050, and there is a gap, but finally it is 2100. So we are here, and probably right here we have our son or grandson, granddaughter, okay, right here, just 80 years later. And you see different colors. And if you look at the gray color right here, this gray color coming from oil. So if you look at there, a significant portion coming from oil, and the black area coming from coal, okay, by 2020. And this area, brown area coming from gas. So all these are fossil fuels. And if you look, if we go a little fast forward by 2030, you see that the gas is going higher and the peak is somewhere here. So by 2035 or by 40, huge amount of fossil fuels coming. And this tells us that we're gonna have a lot of carbon dioxide emission in our atmosphere. And if you look rest of the part, and especially if you look somewhere here, 2020, I suppose you can't distinguish any yellow part. And the yellow part is right here by 2100, the significant part will be coming from yellow part, and this yellow is solar electricity. But right now, I think you can't distinguish the contribution coming from solar. It's very, very small. But this energy vision, this forecast that by 2050 and later, the global, the energy reserve from the fossil fuel is very, very going down. So right here, we don't have much option for fossil fuels, okay? So it is not an option. So what my message here that this is not an option. Right now we are talking about global warming, but later part, if you see, we don't have an option because there are not much left in the reserve. So it is going down. And if you look at by 2100, I suppose, so in India, if in India right now, coal is one of the prime energy resource. But if we go 80 years fast forward, you can't have, I think it is difficult in your eyes to distinguish any coal, okay? So almost you can't see any coal coming. So and also if you look there, almost very tiny amount of oil and some amount of, let's say gas. But if you look just 8 years later, almost 70% should be coming from solar, and 80% should be coming from renewable energy. So today my focus is solar cell and solar energy, okay? So 70%, but right now you don't feel the pressure, but the pressure will be coming just 20 years later from right here, 2040. And then the question comes, do we have the materials, advanced materials to sustain this demand? And one of the big answer is no. We don't have, okay, we don't have that much semiconductor materials or which are right there. For example, indium, okay? The demand of indium, okay, by 2050 is 70 times the reserve we have, okay? So we have 70 times, so means only 69 times we are missing. But indium is highly used material element in semiconductor. Similarly, we have a lot of materials. And today, one of the purpose, we're going to talk about this material scarcity or depleted resources. So, but if you look at the yellow part, started to see from 2030. If you see from 2030, you start to see some contribution coming from solar energy. Okay, and by 2050, some amount is right there. And by 2080, just after 80 years later, okay, I suppose many of you are there, and you're going to find materials which can sustain the demand. And then another question comes, why the solar energy is not distinguishable here? And one of the reasons is we cannot fight with this fossil fuels. We have to be cost competitive with fossil fuels. And only then we expect people gonna use the solar energy. Unless it is competitive with the current fossil fuels, it will be very difficult to, make it more, let's say, penetrate into market. Okay, then comes what is the limitation of solar energy. Okay, so this is a p-n junction in semiconductor physics. This is p-type semiconductor, and this is n-type semiconductor, and this is a sandwich. So this is a solar cell, and if it is made of all silicon, we call this single junction solar cell because this is a homojunction material. And this is a detailed balance calculation based on first. So this is the thermodynamic limit maximum we can get the power, electrical power out of solar energy. Let's say this one. If you look at the right picture, the one means, okay, this is the incident solar radiation. So this one means this is 100% power coming from the sunlight, okay? So your input is 100%. Then the question comes, how much you can convert to solar energy? Let's say in your rooftop, in your house, you might have silicon solar cell, and the efficiency is roughly less than 20%. So it means that 80% are lost. And if you have a tricky way to improve the efficiency by, let's say, double, let's say 40%, you can reduce the cost by, okay, half. And then quickly you can compete with fossil fuels. So this is one of the challenge with people in the renewable energy, that how we can increase the efficiency. And today's lecture presentation, this is my main focus. Again, let me talk a little bit more about here. So this is a semiconductor material, and any material semiconductor, there is a band gap. So this is the band gap. Let's say silicon, we have a band gap 1.1 electron volt. And if you look at the horizontal axis right here, this is also the band gap. And this is the theoretical calculation. And it will give you the theoretical maximum efficiency, electrical efficiency you can take out of the solar radiation. So in the horizontal axis, I'm changing the band gap. So this gap from 0.5 to 3.5 electron volt. And for silicon, somewhere here, we are here, 1.1 electron volt. And if you look at here, yeah, silicon is a pretty good semiconductor material because this belongs to this range where you can get, look at this, by the way, look at this blue area. This blue area means the electrical power you get out of the solar energy, and rest of the color are lost. So just let me again show here. So the maximum, you can see, okay, not silicon is somewhere 1.1, but the maximum is 1.3 electron volt, but we don't have any real material right there. Silicon is very close, and this is one of the reasons silicon is very popular. And another reason silicon is available in our Earth crust. But one of the limitation of silicon is that it is highly energy it costs huge amount of energy to make high-grade solar semiconductor material. So this is one of the limitation, and this is one of the reason my topic will be involved with different materials, not silicon. And okay, so and now then there are different kind of semiconductor material. For example, the color, if you look at here, this is a red color, and this is laser pointer, and this pointer we made by gallium arsenide. This is a compound semiconductor, but here I'm using not a real laser pointer. This is from a PowerPoint here, but if you go gallium arsenide is light here. So gallium arsenide is a very good material in terms of solar cell and compound semiconductor. But you have different kind of semiconductor material. For example, gallium nitride, they're one bandgap material. But if you look at there, if you go wider bandgap material, then your electrical power is going down. On the other hand, if your bandgap is too low, again, your electrical power is going down. So what is the reason? This tells the story. So if your bandgap is so wide, then most of the light which will be impinging on the semiconductor surface, if the bandgap is too wide, let's say this is valence band, if you're conduction band, and if it is too wide, most of the photons should pass through. And here I have written below bandgap. And for this is a reference paper, and the thermodynamic calculation details are explained. So this is a very popular paper, and you can go there. But this pink area shows these are the transmitted light who pass through the material because they are low energy photon, and they cannot excite an electron, bound electron, to the conduction band because their energy is low. And if you're lucky, if the energy is equals to the band gap, then you can excite the electron to the conduction band. Only then you can use this as electrical current. And so obviously you want to reduce your band gap. But if you reduce your band gaps too low, then you get a lot of excitation, you get current. But if your band gap is low, then most of the energy, they are lost as heat. And this is thermalization loss, okay? If you look at there, this part is huge loss due to heat loss, okay? So these two are the biggest loss. So we need tricky way to reduce this loss, this transmission loss and the hot electron loss. And I'm going to talk about that. And there are other kind of loss we call non-radiative recombination loss right here. If you have a lot of defects, typically semiconductor has a lot of defects, and there are a lot of historical events. And one of the reasons the 1948, let's say, Nobel Prize was given the transistor was because from the Bell Lab, they could make high-grade silicon semiconductor. But if your material is not high-grade, you have a lot of defects in the bulk and on the surface. Okay, so let's believe we have high-quality material, and let's forget about these defects for let's say brief time. Let's think about just band gaps and high-quality semiconductor. And so in the previous slide, I was talking about that we have different kind of loss below the band gap, which is transmission loss, then above the band gap, thermalization loss, and we have some other loss, let's say a Boltzmann loss. This is also one of the loss. For example, for the kernel loss, this is a pure heat engine loss. So you cannot, okay, thermodynamic loss, you cannot do a lot with that, okay? It is always there, and there is no solution. But if we go back in the previous slide, the kernel loss is right here. It is very small. But this Boltzmann loss, we can play with the Boltzmann loss right here. Let's say if you concentrate your solar cell, okay? If you concentrate the sunlight, and if you match the angle of the incident light, okay, with the radiative light from the semiconductor, you can reduce this Boltzmann loss. And below the band gap loss, okay, we can use spectrum splitting. And this is multi-junction solar cell, and this is one of the talk today, one of the topic, okay. So I'm going to talk about this part. Okay. And also there is thermalization loss. And by spectrum splitting, we can deal both of them. Okay. So let me talk that part. And for example, this is the spectrum splitting and multi-junction solar cell. For example, this is silicon. If you have a single semiconductor material, and if you look at this graph, this is the solar view radius in the horizontal axis. If you look at the horizontal axis, this is the wavelength. You have different color from the sunlight coming. So different wavelength right here. And in the vertical axis, this is the solar radius. I mean, the power of each photon coming from the sunlight. And, you know, it looked like this. And if you have this, okay, silicon, there's only one small part of the whole spectrum you can collect. But if you look at there, this is the solar spectrum. And again, but the horizontal axis from wavelength, I've converted to electron volt because this will give you a direct idea about the band gaps because the semiconductor use electron volt. But it is the exactly same thing, but you are just inversing the horizontal axis, then it would look like this. Now, if you do have 4-junction solar cell, because the world record right now, right now is 6 junctions, but until recently there was 4-junction solar cell, and the world record was 44.3%. Right now is 47.1%. I'm going to talk about that part again. But if you look at there, the theoretical limit for silicon is around 30%. But if you split your spectrum, then you can call it different part. And also, if you use different band gaps, you don't need to compromise your voltage. So using multi-junction solar cell, you can trickily use most of the part of the spectrum, and you can increase the current and voltage, and that's why we have a world record. I'm talk about that quickly. So use a multiple semiconductor to split the solar spectrum to better absorb photon. This is the message. And this is a very popular chart from United States National Renewable Energy Laboratory. And this is very popular, and people in renewable energy, they frequently use this chart. And this is the very recent chart. And how to read the chart? This is the chart from 1975 to present. And the vertical axis is the efficiency, solar cell efficiency. And if you look there, this is the best research cell efficiency. This best indicates that these are the data. These are coming here not because they are presented in a high quality impact factor journal. This is because they have passed one of the 3 solar cell measurement laboratory in the world. One is Andrel, another is in Japan, and another is in the Germany. So if your solar cell have good efficiency and it passed through, because they have some specific qualification standard to pass, and only then after your data will come here. So these, okay, it requires a lot of effort to appear the data coming here. So with all this, let me explain what are the data. So right here, you have different technologies, solar cell technology. For example, here we have multi-junction solar cells. We have 3-junction solar cell, 2-junction solar cell, 4-junction solar cell. We do have single junction gallium arsenide solar cell because this is highly efficient single junction solar cell. Also, we do have crystalline silicon solar cell right here. And also, we have different, if you look at there, if you have some green, also some other, let's say brown, and the green for CIGS solar cell, thin film solar cell, also cadmium telluride solar cell, also amorphous silicon solar cell. And again, the brown area coming from new technologies, let's say perovskite solar cell, dye-sensitive solar cell, all are here. And because they are new technologies, they started, for example, perovskite, right here, if you look at this empty diamond, hardly the research started by 2010, and the efficiency was very close to 4%, but right now their efficiency is very close to, let's say, 20%. Okay, right here. So 23%. So if you look at there, but if you look at again there, silicon, this is a, okay, if you look at there now, if you look at now this blue one is very stable and not much improvement since 1995. It is almost straight line, and this perovskite is trying hard to touch it. Then what's the problem? Why silicon is going higher? This is because this is the thermodynamic limit, the Shockley Quasar limit 31%. Okay, this is the, okay, this is, I have done a pink line, okay, right here. So single junction solar cell cannot break the limit. It will approach near, but it never can break. But if you look right here, which is the purpose of today's presentation, that multi-junction solar cell and intermediate band solar cell, that if you have this spectrum splitting, then you can break this limit and you can go beyond 30%. And the world record right now is 6-junction solar cell, which is 47.1%. It's difficult to see in your eyes because it is also difficult for me, for my eyes either, but somehow I can see it is 47.1%. If you have interest, you can go to this site. Okay. And what are the technologies we involve with this spectrum splitting technologies? We use in our laboratory molecular beam epitaxy. And here we have, in this picture, we have 2 molecular epitaxy chamber. One is right here, another is right there, and they're connected by a vacuum. And you have different cell right here. For example, here we grow different 3-5 semiconductors. Some of the cell is gallium, one is, let's say, arsenic, someone is, let's say, silicon doping, someone is beryllium doping. We do have aluminum, we do have indium, we do have nitrogen, and we have antimonite and hydrogen. So, and we have other cells. So in this way, we can grow different kind of semiconductor material for our solar cell, and we can play with the band gaps. And I just introduced you that with VIT, recently we started some collaboration, and this is a sputtering code deposition, very similar to the MB system. We have different, so with VIT, after we have started a collaboration between DST and Japan JSPS. After that, we build this system. And this is very similar to MB, but this is a cost-effective system because this is sputtering. But here we do grow different kind of CIGS semiconductor for solar cell. And because this is also code deposition, you can deposit different kind of targets simultaneously and make different kind of alloys. And it will give you CIGS. So we are separating our technologies in different chambers. And we do have other electron beam and thermal evaporator and other for contact. And also we do have mask aligner and other things to make solar cells, transistors, diode, or any electron device. And we do have wire bonder, RTA, and other things to have annealing the systems. And later part, I'm going to talk today about, okay, I do have some time yet. About intermediate band solar cell. And for intermediate band solar cell, we do have to demonstrate that we need to use the photon absorption to prove the concept that we can generate multi-photon absorption and more current from solar cell. And okay, so we have 2 light source and we have solar cell here, and we measure the photocurrent, and out of this, I'm going to talk about this one later again. Let me fast forward mode. Okay, so this is, I already talked about that if we have a solar spectrum like this, and we have the wavelength in the horizontal axis and the photon energy in the vertical, and if we split the solar spectrum into different semiconductor, into different windows, let's say here, then you can increase the solar cell efficiency. And this is one of the way to increase the efficiency. And currently in the satellite, we use this multi-junction solar cell. But this is very expensive, and because we are using latest matched semiconductors in our laboratory, and to make it, we need very challenging technologies, and we need, let's say, in between the different semiconductor junctions, we need tunnel junctions. This is also very challenging technology for different semiconductor, because you need to make a p-type and n-type, highly doped p-type and n-type semiconductor. So a lot of technology innovation is required in this case. But good thing right now in the wall rocket is coming from SiC junctions, but it is expensive. So to reduce the cost, another tricky idea that if you have a single band, semiconductor, but somehow you have a intermediate band in between, then okay, in literally you have multiple gaps, and you can let's say simulate the multi-junction solar cell, and then because you have a single semiconductor material, then you don't need to worry about the tunnel junction and other things, and you can reduce the cost. So this is going to be one of the main talk in the later part. And with DST and JSPS collaboration, I mean the VIT, Professor Kalanathan. So this idea we are trying to make together with different kind of materials. Okay, so let me start with for the multi-junction solar cells and intermediate band solar cell. But for both cases, I'm going to use dilute nitride semiconductors. Then the question comes, what is dilute nitride semiconductor and what exactly our purpose is? Okay, this is a first principle calculation based on a DFT. So if you guys knows about this electronic structure, this is the gamma band, gamma critical point. So in gallium arsenide, this is direct band gap semiconductor. But if you put some amount of nitrogen, now if you look at right here, okay, so then the gallium arsenide, in between the gallium arsenide, you have valence band. This is some unknown band. Then you have conduction band. So, okay, so I'm sorry. I think you guys can see my face. Hopefully you can see me. Okay. Okay, thank you so much. So, but if you look at here, now you do have multiple band. So for multi-junction solar cell, I'm going to use this part. But for multi-band solar cell, I'm going to use most of the part. So there is a model by one of the co-author, Dr. Vellore. He made a very interesting model about this kind of material. So again, I'm drawing, this is by the way, a movie. This is an animation, but this, oh, I'm sorry. This is a animation, but this is theoretically calculated animation. So you can trust the data. I do have some trouble. So if you guys know about gallium arsenide, this is gallium arsenide conduction band. This is gallium arsenide valence band. If in the valence band, you have a heavy hole, you have light hole band, you have spin orbit band, and this is the, wave number in the horizontal axis. And this vertical axis, you see this is energy. So this is your band gap. In gallium arsenide, this is, this is 1.41 electron volt. But if you have little amount of nitrogen, the state comes somewhere here. And now I'm going to show you a little bit movie. And I have done this calculation based on this band anti-crossing model, very similar to the previous DFT calculation. Now look at there. I have put some amount of nitrogen, let's say 0.6%, very dilute amount of, okay, let's say not even 1%. Now quickly you see I got two bands out of this conduction band. One is red band, another is blue band. And the red band is E- band and the blue band is E+ band. So now we quickly see that I can split my conduction band into two bands, and I do have three band gaps. First band gap, second band gap, and the third band gap. Again, if you put more nitrogen, now I can play with my band gaps and different band gaps. So I can split the band gap, okay? And this splitting I can use for the solar splitting for different windows. This is the idea for intermediate band or multi-band semiconductor. Okay, so this is, let me move fast forward. So now just keep this in your mind. Keep this in your mind and look at here. That if you put some amount of nitrogen, you can reduce the band gap of gallium arsenide. Now it gives us an idea, why don't you use this for multi-junction solar cell? Because, oh, I'm going there. This is our experimental data, I'm sorry. I'm going back. This is our experimental data that if you put some, okay, this is horizontal axis is the photon energy, and vertical axis, I'm measuring the change of the reflectance. And this is we call photomodulated reflectance data. Okay, But what I'm trying to explain you here, that if you change the nitrogen concentration from very low amount, 0.78% to increase and increase and increase, this 1.7. Okay, so these are very dilute amount of nitrogen. This is one of the reason I'm talking this dilute nitrate. These are not the nitrate, okay, which for people got Nobel Prize, okay, in the blue LED. This is mainly gallium arsenide, but you have tiny amount of nitrogen. But you see that with changing nitrogen, by the way, this is my gallium arsenide band gap at 1.4 electron volt. And this sample are grown by MBE, molecular beam epitaxy. So these are, okay, heteroepitaxy. You have good quality crystalline structure. But if you're increasing nitrogen, you see you have a new band and it is becoming lower and lower and lower, another band going higher and higher. And if you, okay, redraw this data into here, you see that with increasing nitrogen concentration, you have a lower band, which is the E- band, going down and down. You have another band going up and up. And this agree with this solid line, which based on the band anti-crossing model. And this proof that model works very well with these materials. Now, if you look at there, I'm sorry, there are some Japanese written here, but you can see here, this is germanium, this is indium gallium arsenide, and this is indium gallium phosphide. And this is the 3-junction Wallracott structure for 3-junction solar cell. And if you look at there, okay, so, but if 3-junction, we can split the solar spectrum like there. But because 3-junction, the Wallracott efficiency was somewhere 39%. So if you put, what is the problem with this 3-junction is that in this 3-junction, the germanium band gap is 0.66, the gallium arsenide band gap 1.42, and you have gallium indium phosphide somewhere 1.88. But another material was missing, very close to 1 electron volt. And with changing nitrogen, we are designing a 4th subcell. We are putting in between so we can make 4-junction solar cell. Then we can make our solar cell into from 3 cells to 4 cells. And they should be lattice match, by the way. And this is one of the difficult technology I told you, to making lattice match, because if there is lattice mismatch, you have a lot of defects, and you will reduce quickly, you will damage your material. Oh, okay, I'm some limit of time. So this is how we design our lattice match. Okay, so we have a germanium. So this is the lattice constant, and this is the band gap. You have different semiconductor material, but here I want to tell you that this, all the layer semiconductor solar cells are just lining with this single piece or single lattice constant. So this is a lattice mesh semiconductor. And with this alignment, we expect the conversion efficiency around 53%. So we can go beyond 53%, and this is our target. So we are designing, this is a design concept, that if we change the gallium indium nitride arsenide with different thickness, and for 3-junction, and this is a series junction, the current is, okay, there is a current in a series circuit, there should be current matching. So we need a current around 14 milliampere, and we calculate that our gallium indium nitride solar cell should be somewhere around 2 micrometer of thickness. And this is our solar cell structure grown by MB. Okay, and in fact, we produce a solar cell in our lab, and we, okay, and we show that the external quantum efficiency from our solar cell, we get our current very close to 12 milliampere, which is very close to the required 14 milliampere. And so if it is close to 14 ampere, then we can break the 50% limit. And what are the problem of the dilute nitride? Here I'm showing you just one example, that in dilute nitride, okay, this is a very challenging material because nitrogen is a very small amount. This is why I'm talking about highly mismatched, because nitrogen gonna go into the arsenic side. Arsenic is a big amount, but nitrogen is a very small amount. So you have a difference in the ionic radii, and this make a lot of trouble in this material. This is a historic material. People are changing since the 90s. We have a lot of trouble. So if you look at there, you can feel the trouble that if you make a solar cell, okay, at low temperature, if you have a, let's say, grown at 580 degree, 500 nearby 500 degrees Celsius, then you don't see any, almost no activity of solar cell. This is voltage and current under the sunlight. And if you look at the current generated by the solar cell, this is very small. But if you put different annealing conditions, you start to see that it started to show high current from here. For example, if I'm increasing the annealing condition from 650, 700, 750, 800, 850, you start to see that I'm improving the open circuit voltage and the short circuit current. And you can see the short circuit current is improving here, okay, because quantum efficiency is increasing. So this is the picture tell us that this material requires a lot of effort to play with the defects. And this is one of the methods we are characterizing the defect in this material. We have different kind of defects, bulk defects, interface defects. And if you are as-grown material, which is the black one, we have, let's say, U1 defect. But if you start to annealing, we start to see other defects coming. But after some high level of annealing, we start to see that most of the defects are reducing. And this is one of the reasons you see our open circuit voltage and short circuit current is improving. I have very limited time, and let me go fast forward. Okay, so that was multi-junction solar cell. Okay, now again, how we can make cost, because multi-junctions are very expensive. And now let us make it cost effective. So this is a single band semiconductor, but if you somehow put an intermediate band, which is IB, then here is the simulation that if you play with different combination of conduction band valence band gap and different combination of conduction band intermediate gap, with this, okay, you see that we can go 63% of conversion efficiency with some specific location of the intermediate band, and this is the motivation. Okay, so and for this purpose, we have different approaches. For example, quantum dot superlative solar structure, multi-band highly mismatched structure, which dilute nitride, and I'm talking about this part again. And also the third topic is impurity band engineering, and this part I'm collaborating with Professor Kalainathan in VIT. But today I'm going to talk about mainly this number 2, because okay, this is the third one. I'm not going to talk about this part, but this is a DFT density functional calculation that in CIGS solar cell, that if you have a CGS, this is sulfur by the way, then you have a wide band gap semiconductor. And if you put some amount of chromium, you see that your single band, you can split into multiple band gaps. And with this, so this is the idea that even if you have a single semiconductor, you can split multiple band gaps and you can use it for spectrum of the solar. So this is the introduction that we are going between JSP and DST, but let me go back to dilute nitride semiconductor grown by MB. So this is again the same, movie that if you put some amount of nitrogen, you can split multiple gaps. Then the question comes, why don't I use it for intermediate band solar cell? And this is the calculation, theoretical calculation, that if you change the nitrogen like here, 0% to 2.5%, and you start to, in the vertical axis, the solar concentration, and the color shows the efficiency. You see that by around 1%, you can go 63% of conversion efficiency, which is the red color, with the solar maximum solar spectrum, okay? Solar concentration. And we're gonna utilize for our solar cell this multi-photon multi-step absorption. And this is the solar cell structure to demonstrate the proof of the concept that this intermediate band solar cell works. So if you look at there, this is my dilute nitride material, and this structure is grown by molecular beam epitaxy, and this is a gallium arsenide substrate, 001 substrate, and I have the aluminum gallium arsenide, okay, and tap semiconductor. This is wide band gap, and gallium nitride arsenide on top p-tap aluminum gallium arsenide. So if you look at that, this is PN semiconductor sandwich, and in between I have intermediate multi-band semiconductor. And just look at the right side. This is the multi-photon absorption demonstration. This vertical axis in the bottom is the current delta QE. This is the current I can generate due to the multi-photon absorptions. And the horizontal axis is the photon wavelength from the sunlight. And on top, if you look at, this is the reflectance spectrum coming from the dilute nitride, that I have 2 band gaps, 3 band gaps, okay? Okay, so I have different band gaps inside it on my material. And if I don't have intermediate band in this material, then in this experiment, I see this red line. This red line shows that in this structure, if you have a, let's say, gallium indium arsenide material, which have only single band gap, then indium gallium arsenide, you don't see any extra current due to multi-photon I am showing here. But if you have this kind of material, you see that you are gaining current due to the multi-photon absorption. And this demonstrates that even using a material which has multiple band gap, you can spectrum the solar sunlight, and you can generate more and more current. And this is the proof of the concept. This is published by 2012. This is the first paper demonstrated for this material at room temperature. So with that, I'm almost in time. So I've shown you that the two-step photon absorption is very, very important for the multiband semiconductor, which today I show for the dilute nitride semiconductors. And I have just show a few slides about the chromium doped CGS density functional calculation. Of course, we are doing a lot of calculation between VIT and Tokyo University. And we have some publication about this material. Unfortunately, due to limited time, I could not introduce much about our current work between our collaboration. So with that, let me thank you all and for your attention. And I'm ready to accept your questions.
Professor? Sir?
Yes, sir.
I'll just put some question asked by the audience.
Okay.
What is Carnot loss?
Just a moment. Okay. I have opened the chat in front of me. Are you asking the question from the chat?
Yes, sir.
Okay, can I read and answer them?
Sure.
Okay, that will be good for me and fast. Okay, so one question from Bhashugi Balakrishnan is that what are the best software for simulating semiconductor solar cell thin films? Okay, so if you want to pay for the software, there are a couple of software there, but I'm not representing any of the companies, so I'm not going to talk about those. Okay, but there are some free software, for example, SCAPS 1D, SCAPS. This is, I think, very good software for thin film solar cells. You can characterize your defects. So, and there are other free software, and you can work with them. Okay, so let me quickly move to other questions. Okay, from Gaia here, sir, could you please share some information on the concept of latest research that is going on singlet fission, which has the potential to enhance solar cell efficiency? As it is a new area, is this concept is really encouraging? Yeah, I think this is encouraging, and I think some of the professors in Holland, they are working on this. So, because today I have limited time, and the singlet fission is not my it doesn't include any of my slide, and I should stop answering more, but you can search. And my direct answer, this is, I think, a very promising idea. But they use, I think, organic materials, but organic materials have a lot of challenges, because today I'm talking about molecular beam epitaxy. This is very highly, you can produce high quality semiconductor. So I think there are more technology challenge in that direction. Okay, so what is the maximum thickness of absorbing layer in thin film solar cell technology? Okay, this is from Lakshmi Mohan Raj. Okay, this is, I think, very important question because this question is connected to the second generation solar cell. We have three generation solar cell. First generation solar cell is silicon technology. Second generation solar cells are thin film technology, and this question is connected to that. And today I talk about third generation solar cell, which are based for high efficiency solar cell. But to reduce the cost, because my today's presentation was purposed to reduce the cost, I think this question is very, very important. So what is the maximum thickness? Okay, this is connected to the absorption coefficients. For example, silicon, you cannot, there are some new ideas, but with existing ideas, you cannot use silicon for thin film technology because silicon absorption coefficient is very, very small. So why thin film solar cell, cadmium telluride, CIGS are popular? For example, for silicon, you have to make 3 micrometer or 300 micrometer to 400 micrometer of silicon. And for example, for CIGS, you hardly need 2 micrometer. So you can reduce the thickness by 3 order, 2 order. Okay, so 2 order means you are reducing the weight by 2 orders. So for satellite, weight is a very, very big issue. So the question is why? Because CIGS has the absorption coefficient almost 2 to 3 order higher than silicon. And this is one of the reasons direct bandgap solar cells are very popular in this cadmium telluride. This is direct bandgap solar cell. Any direct bandgap semiconductor has high absorption coefficient. So, the maximum thickness, so the question for direct bandgap semiconductor, I think it is around 3 to 3 micrometer. Okay, let me move to the next question. Jevitha Parthiban, how can I calculate optimum active layer thickness of the solar cells to get the maximum efficiency? Okay, I think I have technically answered your questions, but it's not only absorption coefficient. Also, to calculate the active thickness, you have to worry about the diffusion length of your carriers. For example, if your material has a very poor quality, mobility is very bad, or if your material has a lot of defects, I talked about at the very beginning, the defects is then lifetime of the carrier is very low. Before you collect the carrier, this guy is going back to the valence band, so you cannot collect them, or this guy is trapped in the defect. So increasing the lifetime of the carrier. So if you have infinite amount of the lifetime, then I think 2 to 3 micrometer is sufficient. But real materials, lifetime is very, very limited. So you have to make high quality semiconductor. And there are a lot of questions. I am already over 5 minutes. So Dr.Vijayalakshmi, do you have any time or should I stop here today?
Sir, any questions? Next session. Sir, one final question.
Okay, so can I continue one final questions? So let me from the panelist, I got some question. Let me move to the panelist questions. From Professor Dr. S.K. Ashok Kumar, is there any photovoltaic cell which works from street light or household light as source light in place of the sunlight? I think this is a very important question, and actually we should. Is there any photovoltaic cell? Okay, we are also working in the, some of my colleagues also working in that direction, and this is very important. For example, at night, you don't have sun outside, but in your room light, you can do that. In fact, there are some ideas going around, and I think it is quite possible. It is quite possible that we can work in this direction. Some of the professors are working in that. But as I told you, the output depends on the input. So you will get less amount of the output, but I think it depends on the, but it's still, it is very, very important for future, because at the very, very beginning, I was telling you that we need to cover 70% of the demand of the after 50 to 80 years span. And from Professor Chandini Priya Shiva Raman, I think, what are the principles to improve the efficiency of silicon solar cells? Okay, this is, I think, very important. So one of our ideas that, okay, so if you search Professor Martin paper from Australia, he has very unique ideas, and they are working very good in this. So one idea next, I told you there are some limitation of silicon because it's let's say absorption is very, very less, 2 order less. So with the standard technology, you cannot go beyond. But to make it, okay, improve the efficiency, okay, you have to work with the, let's say, photon management, okay? And let's say there are some ideas coming from the United States that how if you trap your photon inside your silicon more and more, okay, before they are relatively go outside, then you can improve the efficiency. So there's some room is still going there, and some people are working on that light trapping management. And okay, I think this is the last questions from Dr. Chandini Priya Shivaraman, that the band gap differences of P and N layers in solar cells. Okay, so okay, for heterojunction solar cell, okay, we do have different band gaps, but the best is homojunction solar cell, because if you have different band gaps at the interface, okay, you generate different kind of interface defects, and also your carriers face some barrier. Unfortunately, cadmium solar CIGS solar cell, it is difficult to make homojunction. That's why you bring different kind of buffer layers, let's say cadmium sulfide and other, and we make heterojunction solar cell. So there are ideas, different band gaps, if it is difficult to make a homojunction. But the best is like you make multi-junction solar cell, but each junction you have homojunctions. With that, let me stop all my answers, and thank you very much.
Thank you. Thank you so much, sir.
Sir, thank you very much. I want to join my colleague, Dr. Vijayalakshmi. It was a wonderful lecture. Now there are a lot of positive feedbacks. I'm very glad about that. Thank you very much.
Thank you, Professor Senthil Kumar. Thank you.
Now I request Dr. Senthil Kumar Annamalai, sir, to introduce our next speaker.
Hello, Dr. Arun.
Hello, sir.
Hello. It's a good afternoon there, right?
Yes, sir.
Okay.
11 o'clock.
11. Oh, it's still good morning there.
Yes, sir.
Okay. Could you please upload your file?
Yes, sure.
Meantime, I'll introduce the speaker.
Okay.
Yes. It's my pleasure to introduce Dr. Arun Prakash. He is currently working as a visiting academic research fellow in Professor Tiruchi's Sustainable Carbon Group at the Department of Chemical Engineering in Imperial College, London, UK. He received his MSc and MPhil degrees in Department of Chemistry, Sri Ramakrishna Mission Vidyalaya College, Arts and Science, affiliated to Bardiyar University, Coimbatore. And he received his PhD degree in chemistry with specialization in electrochemistry from National Taipei University, Taiwan in 2011. During this PhD time, he was awarded for Taiwan government scholarship. He completed his first postdoc research from 2011 to 2018 on sustainable materials development for electrocatalysis and photoelectrocatalysis application in Professor Chung's lab relating to bio and nano analytical group, National Taipei University, Taiwan. He then joined as a second postdoctoral research associate from 2018 to 2020 in Advanced Sustainable Energy Material Group of Dr. Anna Sobirita at the School of Engineering and Material Science in Queen Mary University, London, UK, to continue his research on oxygen electrocatalysis and zinc-air battery development. Harun has published about 45 research papers, 6 review articles, and 4 book chapters. He is holding 3 international patents and currently is the guest editor for special issue on graphene-based nano sensor and their application for the under its application for the journal Sensors. His research focus on preparation of functionalized nanocomposites, photoluminescent carbon nanomaterials, and the semiconductors, micro and nano structured interface for biosensing, photoelectrocatalysis, carbon dioxide reduction, and the hydrogen and the oxygen electrocatalysis. With this highlight, I request Dr. Arun to present his work on electrochemical reduction of carbon dioxide. Arun, please, welcome.
Thank you, sir. Thank you for the nice introduction. And I also would like to thank the organizer and the speakers for nice presentation. So I'm working.
Arun, one request, please
yes.
restrict your presentation for 35 minutes. After that, we can go for a discussion.
Thank you, sir. Thank you, sir. So today I'm going to talk about the electrochemical reaction of carbon dioxide. So this work, most of the carbon dioxide reduction work I carried out in National Taiwan University in Professor Chang's group in collaboration with Dr.A.Senthil from SICRI. So straight away I'm moving to my topic and what is the motivation for my research, why CO2 reduction is needed. So here you can see the CO2 emissions, the video released by NASA for the period of 1 year, last 1 year. And you can observe a lot of carbon dioxide has been emitted into the atmosphere, and the carbon dioxide level in the atmosphere is increasing consistently. So the graph on the right shows the carbon dioxide level in the atmosphere around 1950s were about 300 ppm, but whereas now it has increased significantly and the current level is about 400 ppm. So it is very important to minimize the CO2 emission, as well as the methods that convert CO2 into useful products are also receiving equal attention. Also, CO emission is also increasing in the atmosphere, and it also causes a lot of pollution. So the increase in the greenhouse gas emission or the greenhouse gases like carbon dioxide leads to additional global warming and greenhouse effect. So we need to minimize the carbon dioxide level in the atmosphere. So what are the main sources of carbon dioxide? So industrial and power grids can emit carbon dioxide, and flue gas also produces carbon dioxide, and home and transportation can result in the carbon dioxide emission. So also the renewable sources can also emit some little amount of carbon dioxide. So we as an electrochemist, what we are doing, we are collecting the carbon dioxide and we are converting the carbon dioxide electrochemically into useful chemical or feedstocks, as well as we are converting into fuels. So these fuels or feedstocks can be stored for further purpose. So what is electrochemical reduction of carbon dioxide? So we use different type of electrodes to carry out this reaction. Mostly copper is the best catalyst for the carbon dioxide reduction. So I will explain why copper is important and why it is playing a major role in carbon dioxide later on. So for example, it is a multiple proton and electron transfer process. So different kinds of liquid and gaseous products can be formed. For example, if carbon dioxide is reduced, so it can form liquid products like formic acid, formaldehyde, and also other products, methanol or propanol, alcohols also it can form. Also it forms some gases like ethylene. So our main interest is on methanol. So what is a multiple electron and proton process? In the liquid phase, there will be protons, right? During water splitting or the bicarbonate solution, it will generate some protons, and also the electrons will be moving through the external circuit. For example, 2 proton and 2 electron transfer process leads to hydrogen evolution. And for all these processes, different standard potentials or equilibrium potentials are needed. Always we supply more than the standard potential, that is called over potential. For example, 2 proton and 2 electron transfer process can lead to the formation of both liquid and gaseous product. The main gaseous product is CO, whereas the main liquid product is formic acid. So similarly, so the number of proton and electron transfer process varies from 4 to 12. And for example, here you can see, observe in the plot that 6 proton and 6 electron transfer process leads to methanol. But the gray squares indicate the ideal over potential and the Faradaic efficiency. So Faradaic efficiency is termed as the amount of charge consumed to produce a particular product. So for example, already the red circle is the literature data for CO and formic acid and methanol and methane and ethane. So already there is a huge deviation from the standard condition, and also the main factors affecting the CO2 reduction is CO2 concentration and pH gradient. So the local CO2 concentration as well as the pH gradient will affect the CO2 reduction. So the main issue in CO2 reduction is the selectivity. So why we need to synthesize the electrochemically or electrosynthesized chemicals? What is the importance and what are the production costs? So this is an interesting review published by Luna et al. In Science in the year 2019, and you can observe the different global market values for formic acid, carbon monoxide, ethanol, and also ethylene. So these are the different global market values, and also you can observe the energy conversion efficiency and the net emission rate for formic acid, carbon monoxide, ethylene, and ethanol. So how profitable are these approaches, or electrochemical synthesis of chemicals from carbon dioxide? How it is profitable? For example, this is the current hydrogen price cost, and how profit you can observe that is from 80% we can achieve by electrochemical synthesis. Also carbon monoxide. So compared to ethanol and ethylene, carbon monoxide production and hydrogen production is much profitable. Also in this review, they have consumed these the CO2 price of $30 per ton and the Faraday efficiency of 90%. So the 100% is our goal, but at least they consider the 90% as the maximum and the current density of 500 milliampere per centimeter square. For industrial scale, this is really a huge current density, and we are aiming to achieve this current density in the electrolyzer, and also the electrolyzer cost will be around $300 US dollars per kilowatts, and also the lifetime should be long, like 30 years. This really is our future goals, and we are focusing on these achieving these parameters. And for example, the current challenges. So as I told, different liquid and gaseous products are formed during CO2 reduction, and you can observe the partial current density. For example, for the formic acid, the maximum partial current density is 500, whereas for the other products, it is only about 300 to 400. So still we need to achieve a lot of improvement in the current density. So electrochemical cell setup for carbon dioxide reduction. So usually the carbon dioxide reduction, you need an electrode that is conductive. Either it can be a glassy carbon electrode or a nickel foam or any conductive material, but it should be stable when you apply the potential. So usually the carbon dioxide reduction will be carried out by applying a potential or a current density. So these electrodes will be separated by a separator. The separator is usually a proton conducting membrane, and Nafion 115 membrane is used as a proton conducting membrane. As I told, lot of products like CO2, so when carbon dioxide is reduced, it will generate carbon monoxide, formic acid, formaldehyde, methane, ethane, and several alcohols and different products. So these are the standard types of cells utilized for the carbon dioxide reduction. For example, it is a H-type cell separated by a Nafion or a proton permeable membrane. So why we need to separate these electrodes? For example, the working electrode and reference electrode. So the reference electrode can be a AgCl reference electrode or a standard Kellerman electrode. The counter electrode is generally platinum. So because oxidation will occur at the anode, whereas the reduction process will occur at the cathode. So we need to separate these products. For example, otherwise, a lot of gas accumulation or product accumulation will happen in the cathode side. So alternatively, so here the mass transport limitation will be there because the liquid is not, electrolyte is not flowing and it is very static. We can stir the solution, but it can only lead to convection. So alternatively, we can use some gas diffusion electrodes like carbon paper. So where these carbon paper will separate the gas and liquid phase, and the carbon dioxide gas can be directly delivered to the catalyst surface. So this in this way, we can overcome the mass transport limitations. So this is a triple phase boundary where a liquid or an electrolyte, gas, and solid catalyst layer will interact. So this is the area where the CO2 reduction will happen. And alternatively, so instead of having a static flow of electrolyte, we can use a circulated flow. And this the main advantage of having a circulated flow is once the product is formed, the electrolyte will be continuously circulating, and this circulation can be done by using a pump. As a result, the product can be, as formed product can be easily transported, and it can be analyzed using a liquid gas chromatography or a HPLC. So what is the advantage between gas diffusion electrode and aqueous phase electrode? For example, as I told, the gas diffusion electrode has lot of pores and the gas can be easily fed to the catalyst layer. So this gas diffusion layer will separate the gas phase and electrolyte phase. As a result, mass transport limitation can be overcome. Also, if you observe, more number of CO2 molecules can interact on the electrode surface or the catalyst surface. Whereas on the aqueous phase electrode, the number of carbon dioxide molecule observing will be less, because the electrolyte, as we know, will have both cations and anions, and also there will be a competition between the proton and the carbon dioxide to adsorb on the catalyst surface. So it is preferred to use a gas diffusion electrode rather than an aqueous phase electrode. So the gas stream and electrolyte stream are separated, and it can help overcome the pH limitation. It can promote the CO2 transport as well. Also, we need to consider the nanometer and micrometer scale regimes and what are the reactions. For example, the gas diffusion electrode is in the micron scale, whereas the reaction happening is in the nanometer scale. So we need to pay attention to the reaction at the nanometer regime. So alternatively, how we can create these 3D supports. For example, instead of having a bulk electrode, we can have a porous or a 3D electrode like this structure, like a pillar-like structure made of carbon nanotube or a carbon fiber. And if it is very porous, the gas transport can be efficient. So this is a recent trend like 3D printing. You can design your GDE or your gas diffusion electrode, and then you can control the viscosity of the polymer, and then you can easily control using a software to directly print the GDEs and also other catalysts. So the other alternative method to make the GDE or a catalyst, freestanding catalyst, is electrospinning. So here you will take a polymer solution and you will apply high voltage like 15 kV, and then it will create a Taylor cone. And as a result of the Taylor cone, here you will apply some potential, and here this is a collector or a drum, and you can collect the carbon fiber. So this is more efficient, and we can, in this way, by using 3D printing and electrospinning, we can create the GDEs. So next, let's move on to the why nanostructure materials are important and why nanostructure materials play a major role in CO2 reduction. For example, compared to the, we all know, compared to the bulk material or the bulk electrodes, nanomaterials have high surface area and also more number of catalytic active sites. So the particle size have a particular effect. For example, for gold nanoparticle 4 to 10 nanometer, the current density for CO will vary. So this is a partial current density calculated geometric area, and you can see for the 4 nanometer gold, much higher current density is observed rather than a 10 nanometer gold. So it is preferred to use smaller size nanoparticle. Also, the Faraday efficiency will be affected by the size of the gold nanomaterials. Also, the defects and anisotropic effects. Instead of having a nanoparticle, you can have a nano wire, and then it can help your electron transport, and also it can enhance the site density. For example, compared to the nanoparticle, nanowire have more edges. Also, the nanoparticle edge and corners are lesser than the nanowire. This can also influence the CO2 reduction. And the Faraday efficiency for carbon monoxide can be tuned based on the length of the nanowires. For example, the 500 micron nanowire is performing better than the 15 micron nanowire. So also, the copper is the best catalyst for the CO2 reduction, and most of the work has been initially done by Hori et al., and then it is followed by the Kul's group, and different groups are working on the CO2 reduction recently. For example, compared to the normal or the polycrystalline copper materials, oxide-derived materials are performing well, and also the mesoporous one. So this is the geometric current density, and this is the current density normalized with respect to the electrochemical surface area. As I told, the Horis group has done a lot of work on the copper-based materials, and different number of different products has been generated by them, and also the oxide-derived materials are performing well in CO2 reduction. So the main drawback in the copper-based catalyst, they are not selective. They can generate a lot of liquid and gaseous product. So next we move on to the choice of electrolytes. So three types of electrolytes can be used. One is aqueous electrolyte, the other one is non-aqueous electrolyte, and the other one is ionic liquid containing imidazolinium cation. So aqueous electrolytes, as I told, when you use an aqueous electrolyte, you are having water base or water medium. So there is always protons will be there, and hydrogen evolution is a competitive reaction compared to CO2 reduction. So what are the electrolytes can be used in CO2 reduction? Aqueous electrolytes, the alkali metal cation containing salts can be used, like sodium bicarbonate, potassium carbonate, and KCl and KOH. Also, the concentration of the electrolyte also affect the Faradaic efficiency. So you no need to use higher concentration of the electrolyte, like 10 molar KOH, for example. The higher Faradaic efficiency can be achieved using 1 molar KOH. Also, the TAFL analysis gives you information about the rate determining step and also the kinetic information. For example, compared to the KOH, if you see the red one, the TAFL slope value is 133, whereas for the when you use KCl or potassium bicarbonate, the value is less, around 115 millivolts per decade. So it is preferred to, so people are using bicarbonate rather than the KOH for CO2 reduction. So what is the advantage of using non-aqueous electrolytes? As I told, non-aqueous electrolytes don't have any protons, and as a result, we can suppress the hydrogen evolution reaction. Also, the solubility of carbon dioxide is an important issue. So compared to the water, the DMSO and acetonitrile have 4 times higher solubility. Also, the methanol and propylene carbonate have 5 and 8 times higher solubility than water. Whereas for DMF, it is 20 times better soluble than in water. So you can choose any solvent depending on it, the solubility of the carbon dioxide. But the only difficulty is separation of the product from the non-aqueous electrolyte. So when you use imidazolinium containing ionic liquids, they will coordinate with the carbon dioxide and they can lower the reduction over potential. Also, it can reduce the energy of the CO2 intermediate, and pretty much it can inhibit the hydrogen evolution reaction. As a result, it can increase the selectivity for CO formation. So the electrolytes in CO2 reduction, as I told, there exists an equilibrium between the dissolved carbon dioxide and the bicarbonate ions. So the bicarbonate is preferably used in the CO2 reduction as an aqueous electrolyte. So this equilibrium determines the CO production, and also the dissolved CO2 is playing a major role. So we can supply a lot of carbon dioxide, but only the dissolved carbon dioxide in the solution will only take part in the reaction. As a result, the effective concentration of dissolved CO2 near the electrode surface is important, and the equilibrium between the bicarbonate and the dissolved CO2 determines the CO2 selectivity or the rate of production. So we know also, other than the electrolyte, the concentration can also affect. For example, for potassium bicarbonate, if you increase the concentration, the bulk pH or the pH, local pH near the electrode surface will also change, and it can also alter the current density. So pay attention to the concentration of the bicarbonate concentration. Also, outer Helmholtz plane. We know in electrochemistry, when you have an electrode surface and when you apply some potential and some polarization will happen. As a result, so the oppositely charged ions will be aligned on the electrode surface. It leads to the Helmholtz plane, that is called Helmholtz double layer. So there are two types of Helmholtz double layer. One is inner Helmholtz plane and outer Helmholtz plane. So for example, if you use a lithium containing electrolyte like lithium carbonate or lithium hydroxide, then the lithium cation will be surrounded by the water molecule. So this is called the solvation cell. So this can also affect your CO2 reduction. Also, depending on the size of the cation, for example, lithium and cesium. So they have different size, and based on the size can also the solvation mechanism and hydrolysis can vary, and this can affect the coordination or the formation of the intermediate. So the hydration cell of the cation plays a major role, and also the adsorbed intermediate. Also, the buffering cations, you can have any different types of cation and anion, like simple salts like potassium chloride, potassium bromide, and potassium iodide. This can also affect your, we know that these are the supporting electrolytes, right? If you add these salts to your electrolyte like 0.1 molar potassium bicarbonate, it can also affect the selectivity. For example, when you have potassium iodide, the methane production will be enhanced, the Faradaic efficiency will be higher. Whereas if you have KCl, it will be decreased. So choose the cation based on the buffering capacity. Also based on the buffering capacity, hydrogen production can also be suppressed. So what are the other factors influencing the selectivity? So in electrochemistry, we have particularly mass transfer effects and kinetic effects. So in your bulk solution, you will have different anions like bicarbonate, carbonate, and proton and CO2. These ions have to be transported to the catalyst layer or the cathode surface. And the catalyst layer, there is a diffusion layer. We know that from the bulk solution to the electrode surface, so diffusion will occur, and as a result, the concentration gradient will be generated. For example, bulk solution will have more number of cations and anions, whereas near the electrode surface, it will be lesser. For example, the diffusion layer thickness also affects the migration or the mass transport of these ions. So other factors affecting the diffusion and concentration profiles are the boundary layer. For example, if you have a smooth surface, electrode surface, the boundary layer will be different. And if you have a curved or a rough surface, the boundary layer will be different. Also, if you have a porous catalyst, the boundary layer will be different. So these can also influence the CO2 reduction. As I told, the CO2 concentration or the dissolved CO2 concentration, local CO2 concentration, and pH gradient can also affect. So these can also affect the performance, and also the boundary layer plays a major role. So what are the types of mechanism or the CO2 reduction mechanism? So we are using aqueous and non-aqueous electrolyte. Different pathways occur in these electrolytes. For example, in the aqueous electrolyte, there are only two pathways. One is the C1 pathway, that is one or a single carbon containing products like methanol. So it can be two types. One is the pH dependent pathway and the pH independent pathway. So what do you mean by pH dependent pathway? So if the product is in the liquid phase, then it will depend on the pH like methanol, ethanol, or any kind of alcohols or formic acid. Whereas in the case of pH independent pathway like CO, carbon monoxide, or ethylene or methane. So for example, the best example, pH dependent pathway leads to the formation of methane, and pH independent pathway leads to the formation of ethylene. So you can tune this pathway to tune the selectivity. So whereas in the case of aqueous electrolyte, oxalate intermediates will be formed. Instead of dimerization of carbon dioxide, here oxalate intermediates will be formed, and you can introduce the some ionic liquids to increase the CO2 local concentration. So what is the role of ionic liquid here? For example, if you use a pure aqueous electrolyte, so the CO2 solubility will be very less, whereas if you add some ionic liquid containing imidazolinium cation, it can form a complex and it can absorb on the catalyst surface. This can increase the local CO2 concentration as well as it can stabilize your intermediate. So the mechanism for the methanol, and depending on the intermediate, that is the H3CO and HCO. So based on the intermediates also, the pathway can be different. Also, if you add some ionic liquid, the pathway can be different. So the main reason is they have different free energies, and these free energies determine the selectivity. So why methanol production? So because methanol is a valuable product, and there are different catalysts have been used for producing methanol and other value added products. For example, copper is the best one. The main reason is it has the more positive free energy, and also depending on the potential, the energy for the CO absorption can vary. So we have to pay attention, and we need to get this information from the theoretical chemist, and we have to perform some DFT calculation. So as I told, why copper is preferred for CO2 reduction? The main reason is it is the only metal, you can see all metals, it is the only metal with the positive hydrogen absorption energy, and as well as it has a negative absorption energy for CO. So this is the main reason, because CO is the important intermediate, and people use copper for producing different chemicals from CO2 reduction. So intermediates have different free energy. This you can obtain from the DFT calculation. And for example, for the methanol, CHO and CH2O intermediates are the main intermediate. So the challenges will be in CO2 reduction. Carbon dioxide can be reduced to carbon monoxide as well as alcohol. So the selectivity is a key issue, because it is a multiple electron transfer process, and suppressing the unwanted side reaction. This can be done by adding some buffer ions or ionic liquid to enrich the local CO2 concentration. So the main drawback with copper is it requires high over potential and high hydrogen yield. So hydrogen evolution will be dominant or over the CO2 reduction. As a result, the turnover rate and Faraday efficiency will be less. So what are the selectivity criteria? So every catalyst will have a different criteria, and you have to pay attention to these values like hydrogen binding strength. So if a catalyst has a positive or a more strong hydrogen binding strength, and it can lead to hydrogen evolution. So alternatively, if you see here, there are different metals have different hydrogen adsorption energy as well as the CO, okay, the carboxyl group adsorption energy. So these adsorption energies determine the selectivity. For example, compared to copper, so the metal nitrogen containing centers have more positive values for the hydrogen adsorption energy. As a result, they are preferred for the CO2 reduction recently to minimize the hydrogen evolution. Also, as we know, the nitrogen doped materials have different types of nitrogen like pyridinic, graphitic, and pyrrolic. So they also have different free energy for carboxyl group. So this can also affect your CO2 reduction. For example, the low free energy is for pyridinic and pyrrolic nitrogens rather than graphitic or pure CNT. So I am going to focus mostly on my talk methanol production, because we did our work on producing methanol. Methanol is a value added product. So what determines the selectivity of methanol? Like hydroxyl binding strength determines the methanol production. For example, if the hydroxyl binding strength is weak, it can be the intermediate or CH3 can be easily removed. So the only difference between the methane production and methanol is the binding strength of hydroxyl ion. If you have weak binding strength, you can generate the methanol. So if you want to design a catalyst for methanol, then try to have a weak hydroxyl binding strength. So if you have strong hydroxyl binding strength, it will form methane because of the oxygen intermediate. So CO binding strength and also hydrogen binding strength determine the methanol selectivity. For example, the metal with more positive binding strength for hydroxyl ion produces methanol, whereas the more negative metals with more negative hydroxyl binding strength produce the methane. Similarly, it is in the case of CO binding strength. So what are the active metals? There are different types of active metals like copper, zinc, nickel, and ruthenium and platinum. So platinum and gold are expensive, so people prefer to use copper. So the main drawback with the copper is the bulk copper, the Faraday efficiency for methanol is very poor. So people are using nanostructure copper as well as the alloys because of the increased active sites. So it can produce more amount of methanol. So the anode and cathode needs to be separated by a membrane. This is a typical cell, and this is the CO2 electrolyzer, and you will have a cathode and anode, and carbon dioxide can be reduced by applying some potential. So this is the these are the values reported in literature. Faraday efficiency based on the electrode potential. Faraday efficiency can vary with respect to potential, and also energy efficiency can vary. So Faraday efficiency is calculated by the number of moles of methanol formed that you can determine by gas chromatography or liquid chromatography or HPLC, and number of electrons consumed. For example, methanol, 6 electrons will be consumed, and this is a Faraday constant, and Q is the total charge passed. You can obtain this value from your IT curves. And also based on the theoretical and experimental value, you can determine the Faraday efficiency. So the methanol selectivity for copper oxide, that is cuprous oxide, is much better than the copper because it stabilizes the CH3CO intermediate. And also if you use a GDE, you can achieve a higher Faraday efficiency than the other catalyst without GDE. So it is preferred to use gas diffusion electrodes. And also importance of in situ monitoring of reaction intermediates. So different products will be formed in your liquid. So you have to monitor those products in situ methods. Like if you have your electrochemical cell, this headspace can be connected to a gas chromatogram or a mass spectrometry, and you can monitor the products. So whether it is a hydrogen or carbon monoxide or ethylene or acetylene, you can monitor. Also, you can use some in situ methods. For example, you can place a mirror near your working electrode, and you can reflect this one, and you can connect it to a spectroscopy, and you can monitor the products. Also, like infrared spectroscopy, Raman spectroscopy, and X-ray photoelectron spectroscopy. So these methods are very useful for monitoring the products. Also, in the case of FTIR, you can use either external reflection adsorption. So here you can place a calcium fluoride disc, and you can reflect the IR radiation, and you can monitor the intermediate. Similarly, you can also use internal reflection methods where the calcium fluoride can be directly attached to your electrode surface. So these in situ methods will give you valuable information. So this is our recent work we did with Dr.S.Senthil from SICRI. This is a collaboration work which I did in National Taiwan University. So here we use a flexible paper electrode and we soak it in a pyrrole solution. And since it is soaked in the pyrrole solution, since it is a paper electrode, it will absorb the pyrrole. And this, after absorbing the pyrrole, this paper electrode can be introduced into the copper solution. So the copper is a metal, and so metal to ligand charge transfer will initiate the polymerization of pyrrole. Also during hydrothermal process, we add a catch-in polyphenol to initiate the formation of cuprous oxide particles. As a result, we can form the brown color particles, that is polypyrrole coated cuprous oxide. The main idea of this work is, so as I told, GD is playing a major role, and the paper have the microporous structure, whereas the fiber layer will have a macroporous. Although this electrode is not acting like a GDE, but because of the difference in the porosity, the gas flow and the electrolyte flow can be controlled, and the mass transport is much efficient. So these are the particles which we prepared: copper oxide, cuprous oxide, polypyrrole composites. We are able to form icosahedron as well as the octahedra size particle. So this is the TM measurement showing both octahedra and icosahedron. So this is the how we control the morphology. Actually, we tune the NaOH concentration. At low concentration, octahedra is preferred, whereas at high concentration, more number of crystal facets will be developed, and this will form the icosahedra. So as a result, we are able to form low index facets as well as high index facets. So the high index facets have high selectivity. So this is the elemental mapping for copper, nitrogen, and oxygen. Also, compared to the bare electrode, the onset of the CO2 reduction is much lower for the composite electrode, that is the blue one, whereas for the green one, the octahedra material, it is much more negative. Also, this we confirmed by the electrical conductivity measurements using impedance. For bare electrode, you can observe a resistance of 500 ohms, whereas for our material, the resistance is much lower, and we observed only a diffusion element. And also we did IV measurements to confirm the stability and the conductivity of the cuprous oxide in presence of polypyrrole is 1 order higher than without the polypyrrole coating. Also, the stability compared to cuprous oxide polypyrrole is much conductive. So liquid product analysis. So after CO2 reduction, so for CO2 reduction, you have to apply different negative potential, like we applied -0.25, -0.45, and until -0.95. So we monitored the product, liquid product methanol, by using gas chromatography. In the bicarbonate solution, we did not observe any methanol product. But whereas for the octahedra electrode, we observed less amount of methanol production, whereas for the composite with the high index and low index facet, we observed much higher methanol production. So this is the calibration plot. From the calibration plot, you can determine the amount of methanol in micromoles. From that, you can know the amount of charge passed during your electrolysis, and you can calculate the Faraday efficiency. For example, compared to octahedra, the composites is 2-fold higher producing methanol. Also, the only liquid gaseous product we observed is carbon monoxide, and this is the standard carbon monoxide peak in gas chromatogram. This is the peak which we observed at a retention time, same retention time for the carbon monoxide. So we also did long-term electrolysis GC analysis to monitor the hydrogen. As I told, in this electrode, the hydrogen evolution is suppressed because we observed only trace amount of hydrogen. Also, we monitored the NMR analysis, the product methanol, and we used D2O as the solvent, and the methanol peak, standard methanol peak, and for the composite, the 2-fold higher intense peak can be observed. So we did some post-analysis, like long-term analysis. The electrode is stable for 15 hours, and we determined the copper content by ICP-MS analysis, and we only observed trace amount of copper leaching from the electrode surface until for 15 hours of electrolysis. Also, we did some XPS measurement, and we monitored the change in the N1S peak, but we did not observe any change in the copper peaks. So the cuprous oxide is very stable, and whereas we observe some increase in the pyridinic nitrogen. So based on this, we proposed this mechanism. So since we are using hydroxyl medium, so polypyrrole is doped with hydroxyl, and bicarbonate can undergo some anion exchange. And this is the pathway, general pathway reported in the literature, and the intermediate is the CH3CO. And after protonation step, methanol can be generated. So we also did post-analysis like Raman. These are the characteristic peaks for Raman, that is for cuprous oxide, and this is for polypyrrole. So we did not observe any, almost most of the Raman peaks are observed for the fresh electrode as well. electrode subjected to CO2 reduction for 15 hours. So this is the low index and high index phase sets of cuprous oxide. We observed almost the low index and high index phase sets before and after electrolysis. This also confirms the stability. So this is the SEM post characterization and high resolution.
Dr. Arun,
Sir?
could you please now wait, take another 2 minutes going up?
Yes, sir. I will finish it, sir. Almost done, sir. So post-analysis confirmed the polypyrrole cell is retained and also the high index phase set like 2,2,0 is retained. So finally, the take-home message. So whoever working on CO2 reduction for methanol production, pay attention to the cation effect, morphology effects, and also grain boundary effects and phase set effects. So if you create some high index phase sets, you can produce the have a better selectivity. Also for improved selectivity, try to increase the local or dissolved CO2 concentration and pH, local pH changes. Also use GDE instead of the to overcome the mass transport issues. So the hydrogen binding strength, hydroxyl binding strength, and CO binding strength determines the methanol formation. So anions with low buffering capacity can lower the hydrogen evolution. So when you use an electrolyzer, you have to pay attention to the electrolyzer configuration, electrode structure, and type of electrolyte, whether it's ion. Also pH control and electrolyzer operating pressure and temperature can affect. So recommended best practice, go for best practices like purity of the components, try to purify your electrolyte, and also pay attention to your kinetic measurements like Tafel plots, and also turnover number or turnover frequency. So selectivity, you have to use some proper methods to determine the selectivity, and catalyst deactivation. As I showed, you can do n number of post-analysis to confirm the selectivity. So finally, in our work, we have prepared freestanding GDE mimicking cuprous oxide polypyrrole composite paper electrode. The mass production is very cost effective because the paper electrodes are very low cost. And also the particles are conductive. Polypyrrole cell protects the cuprous oxide particles from aerial oxidation. Whereas if you have only cuprous oxide particle, it can oxidize in air and it will affect the conductivity. So polypyrrole coating enhances the local CO2 concentration, and it is selective for the C1 product with a Faraday efficiency of 93. So finally, I would like to thank my supervisor, Professor Chan from National Taiwan University, our collaborator, Dr.A.Senthil Kumar sir, and also I would like to thank Dr. Annamalai Senthil Kumar sir for giving me this opportunity. I also would like to thank the group Bio Nano Analytical Lab, as well as the group in Queen Mary and Imperial College. Also, I would like to thank my current supervisor, Anna Sobrido and Tritucci. So thank you all for your kind attention.
Dr. Arun, nice presentation. You covered fundamentals up to the technology level of utilizing this carbon dioxide. Very nice presentation and a very informative presentation. Thank you very much. So there are a few questions from the audience. Maybe one by one I'll ask. One of the audience, they asked difference between the copper and the copper oxide in this CO2 reduction reaction. What is your opinion?
Yes, sir. It's a nice question, sir. Actually, the copper, as I told, copper is the only metal with a positive binding energy for the CO, as well as the negative binding energy for CO, whereas the positive binding energy for hydrogen. So the only drawback with copper is it is not selective for producing liquid and gaseous products. It will generate a lot of, because it is multiple electron transfer process, as I told in CO2 reduction. If 2 proton, 2 electron, it will form hydrogen, whereas 6 proton, 6 electron, it will form methanol. So on the copper surface, the selectivity is poor, whereas on the cuprous oxide surface, as in our case, we are able to suppress the hydrogen evolution and we are able to produce methanol. So cuprous oxide is more selective for CO2 reduction, whereas the copper is not that much selective for CO2 reduction. Still, it is a good catalyst for CO2 reduction.
But cuprous oxide case, no, because oxide you cannot convert into the low valent species, because already copper metal means is a low valent species. Very effective for the reduction, because for the carbon dioxide reduction, low valent species is much better than the high valent species. So copper metal is already exists in 0, but for the copper oxide case, no, it is in 1 or 2. So it is difficult to convert it to zero oxidation state.
True,
so
sir.
That,
actually,
I expect be less.
Yes, sir. So there is always a possibility because we are applying negative potential. So the cuprous oxide from the oxidation state can be lowered and it can be reduced back to copper, sir. But as I showed in the post-analysis, we didn't observe much change in the characteristic copper peaks. And also we didn't observe any satellite peak for Cu or something. So maybe the surface oxide can be reduced during the CO2 reduction, but not the cuprous oxide inside the core will not be reduced, I think. So it all depends on the electrolysis time, and the electrolysis conditions may affect the cuprous oxide reduction process.
One more quick question.
Yes.
Because this recent time, no, there is a very important role in the electrocatalysis. How about
yes.
copper nanoparticle in CO2 reduction reaction?
Yes, so like the copper nanoparticle, as I told, the size effect has some effect on the CO2 reduction. Also, the structure have some effect on the CO2 reduction. So it is preferred to have smaller sized particle. So instead of having a copper particle with a size of 50 nanometer or 100 nanometer, we can go for copper nanoclusters with 1 or 2 nanometer size, or even less than 10 nanometer size. So I already showed in my presentation the gold nanoparticle with 4 nanometer is producing higher current density than, because it may have more number of active sites and higher surface areas, electrochemically active surface area. So this can result in better performance. So we need to focus on controlling the particle size, crystal phase set, and also morphology. So I think these 3 aspects, if we focus, we can improve the activities.
Okay, thank you very much, Arun. It's a very informative interaction. I wish you all the best in your future career. Maybe if you come to India, please do visit to CO2 Center.
Definitely, sir. I will visit to
Arun, because I would like to join my colleague, Dr. Annamalai Kumar, in thanking you. Thank you very much. Thank you very much for your time and effort. And we want to extend an open invitation to you, to our center. Whenever you come, please, let us know. We'll make arrangement. Thank you very much.
Thank you for your kind invitation, sir. Definitely, I will visit your center. Thank you for this opportunity.
Okay, I'll contact you, Arun. Okay, thank you very much.
Sure, sir. Thank you, sir. Thank you. Nice.
Okay, nice. Yes. Now, yes.
Next speaker, sir.
Next speaker, Dr. Sengodan. I hope he's. Hello, Dr. Sengodan.
Yeah, I'm here.
Hi. So it's a good afternoon.
Good afternoon.
Okay. Could you please? Okay, I already uploaded. Okay. I'd like to introduce Dr. Sengodan. Just a minute. Okay. Yes. Sivaprakash Sengodan, right? Currently is in Imperial College London. He's completed his BSc degree in Chemistry, Bardiyar University, 2001 to 2004, and corresponding is MSc Chemistry degree in Madras University, completed in 2006. He also did a MTech program in Anna University Polymer Science and Engineering Department. He completed in 2009. After that, he moved to South Korea to complete his PhD program. He completed his PhD in 2015. And after that, he moved to a postdoctor in the University of Warwick, UK, first postdoctor in 2015 to 16. And the second postdoctor 2016 to 2018 again back to the Ulsan National Institute of Science and Technology, Korea. Now currently he is in Imperial College as a research fellow in the Department of Material. He has received several honors during this research time. First one is recently, 2019, he has got a grant from Royal Society of Research grant about $20,000 for his research. Similarly, he has got a career award with a honor of $2,000 from STFC Future Yearly Career Award, and Imperial College Research Fellowship also he has got. Similarly, he got number of research fellowship from the South Korea Institute also. And, He has also involved in during the PhD time. He's also involved in the teaching. He has given a number of invited talks. He has published over 20 international papers. Notably, he has recently, 2019, he has published Nature Communication regarding to the some perovskites based some physical chemistry aspects. With this highlight, I request Dr. Sengodan to give his presentation. Sengodan, please welcome.
Thank you for the nice introduction, Dr. Annamalai, sir. So today I'm going to talk about my research on development of layered perovskite materials for solid oxide fuel cells.
Dr. Sengodan, please restrict your talk to
yeah, sure.
35, please. Okay.
Yeah,
thanks.
And then my talk is on introduction, and then the status of fuel cell, current solid oxide fuel cell technology, and then my work on the solid oxide fuel cells, both in layered perovskite cathodes and layered perovskite anodes. And then I will conclude. Due to time restrictions, I will directly jump into the types of fuel cells. So there are types of fuel cells. Fuel cells are broadly classified based on the electrolyte material used in the fuel cell materials. So I'm working on the solid oxide fuel cells, which operate at about 700 to 1000 degrees Celsius, where the stabilized zirconia membrane is used as an electrolyte, where we get the efficiency about 65%. When the solid oxide fuel cell is combined with the gas turbine engine or other heat recovery systems, the efficiency can be improved more than 92% of 92%. So I'll directly jump into the development. So basic principles, I will explain from the basic principles. Solid oxide fuel cells are electrochemical devices where we convert the chemical energy directly into the electrical energy. So main advantages of solid oxide fuel cell is the direct conversion of fuel into electricity, high efficiency, environmental friendly, and fuel flexibility. The disadvantage is the performance degradation at high operating temperature and high thermal stress due to the high operating temperature about 1000 degrees Celsius. So there is an immediate requirement to decrease the operating temperature of the fuel cell from 1000 degrees Celsius to 700 to 500 degrees Celsius. Due to this reduction, there will be severe degradation in the cathode, and the catalytic activity of the cathode for oxygen reduction reaction will be diminished. So mainly in solid oxide fuel cell, perovskites are used as the electrode materials, both as the anode or the cathode materials for solid oxide fuel cells. Primarily, simple perovskites are used as a cathode material or anode materials. Structure of perovskite oxide is shown here, where the general formula AbO3, where A is the lanthanide series metal and B is the transition metal, O is the oxygen. By creating the oxygen vacancy either by doping with a smaller valence cation or decreasing the partial pressure of oxygen or increasing temperature, we can create oxygen vacancies. These oxygen vacancies can use for conversion of conduction of oxygen ion conductivity. So traditionally, BSCF or LSCF or LSM or LSCM are the simple perovskite materials used in solid oxide fuel cells. But the main advantage compared to the simple to layered perovskite oxides is the layered perovskite oxides have high ionic, high electrically conducting material, fast oxygen diffusion, and has an excellent surface exchange coefficient with oxygen. It has an excellent durability. So I will explain how from simple structure to layered perovskite is formed. So this is the unit cell of the simple perovskite structure. In a simple perovskite structure, when we start doping a larger cation like a barium in A site, layered perovskite is formed. So this is the layered perovskite structure. And this is the unit cell of the layered perovskite structure. This is the barium, this is the B site cobalt or a manganese oxide. This is the lanthanum here. And oxygen is the smaller one, lattice oxygen. When we by increasing temperature or controlling the oxygen partial pressure, we can create oxygen vacancies. From there, here, we can start conducting the oxygen ions from atmosphere to the fuel cell electrodes. The main requirement of the electrode is, the four main requirements should be catalytically active. For example, in a solid oxide fuel cell cathode, it should be catalytically active for oxygen reduction reaction. In case of anode, should be catalytically active for hydrogen oxidation reactions. Second requirement is the electronically conductive. It should be highly electronically conductive for conduct the electrons towards the external circuit to fulfill the current migration. And then third requirement is should be ionically conductive for ionically conductive from the atmosphere towards the center of the electrolyte. And fourth requirement is material should be compatible. The electrode material should be compatible with other components of the fuel cell. For example, in case of it should be compatible with the electrolyte, it should not react with electrolyte or other components of fuel cell like current collectors, everything. Since the fuel cell is working at high temperature, there will be always be side reactions or unwanted reaction happening in the solid oxide fuel cells. So main requirement here is the four main requirements should be catalytically active, electronically conductive for conduct the electrons in the external circuit. Third one is the ionically conductive to conduct the oxygen from the reaction site towards the electrolyte. Fourth condition is the material should be compatible with the other components of the fuel cell. So based on these requirements, we have developed a solid oxide fuel cell layered cathode material. So before going to the development, I will just a brief introduction how fuel cells are fabricated. So in solid oxide fuel cells, the anode materials is tape casted, and then the electrolyte is deposited either by spray deposition, or it can be tape casted and can be laminated. And then anode and the electrolyte is first sintered at 1600 degrees Celsius, and then third layer of a cathode is deposited by screen printing. In solid oxide fuel cell is tested under laboratory condition in a coin cell type. Aluminum tubes are both end, and then the fuel cell is sealed with a ceramic bond, and then PT wire or other silver wire used for the current collection. So this is a completed fuel cell sintered at 1600 degrees Celsius. This planar one and then circular button one. This figure shows the stacking of the fuel cell in the commercial fuel cells. This is the fuel cell after lamination. This is the anode. The green one is the anode. The white one is the electrolyte. And then the laminated but not sintered one. After this, it will be sintered for 1600 degrees Celsius to get the complete fuel cell like this one. So the conventional cathode, what is the main drawback of the conventional cathode is due to decrease in the operating temperature of the fuel cell, the oxygen reduction reaction was limited. And then because of this oxygen reduction reaction limited, the performance of the fuel cell goes down with decreasing operating temperature of the fuel cell. So the traditional electrodes or conventional electrodes are BSEF or LSEF or LSM. So to improve the catalytic activity or oxygen reduction reaction, I have developed a layered perovskite material which shows high performance. The first we took the prismidium, barium, cobalt oxide, the layered perovskite. We took this as a parent material. We choose this material because of its high diffusion, that is a diffusion of oxygen and then surface exchange coefficient values. It has enhanced oxygen transport kinetics. So doping a small amount of strontium in the barium site increases the oxygen reduction reactions. Then we found that because of the cobalt present in the B site, there will be a huge or a large thermal expansion coefficient is happening. Because of this, we cannot use this material in the commercial fuel cells as a cathode material because of the thermal expansion coefficient of electrolyte and the cathode is different. So we need to match the thermal expansion coefficient of the electrode with the cathode. So in order to match that, we started doping a small amount of iron in the cobalt side. By doping amount, we found that the thermal expansion coefficient decreases. At the same time, oxygen ion diffusivity and then oxygen reduction reaction activity was increased. So based on this strategy, we fabricated a solid oxide fuel cell based on ceria-based electrolyte, praseodymium, barium, strontium, cobalt iron oxide. We call this as the PBSCF material. And then at 650 degrees Celsius, it shows a power density of about 3 watts per power density and a current density of like 10 ampere per centimeter square at 650 degrees Celsius. We checked the stability of the material over 100 hours. This material is very stable at 0.6 volt at 550 degrees Celsius, does not show any degradation, whereas the material without iron, with only having the strontium, shows the high performance, but its durability is not very good because of its, because this may be due to the poor thermal expansion coefficient. And then we have compared this material with a traditional or conventional cathode material like a BSCF. BSCF shows the performance one order lower than the developed PBSCF material. So in conclusion, we can say that PBSCF shows a high power density, excellent durability at over 100 hours at 550 degrees Celsius. Then I have developed a layer perovskite material for solid oxide fuel cell anode. So before going to the and directly into the development, I will introduce why we need to develop a solid oxide fuel cell anode. So conventional solid oxide fuel cells use one pure hydrogen as the fuel, whereas we cannot use the hydrocarbon as the fuel. So what will happen if you use the hydrocarbon as the fuel means, to use the hydrocarbon as the fuel, we need external reforming. Because of this external reforming, the efficiency of the fuel cell was decreased about 20 to 30%. And then pure hydrogen is very expensive to produce and hard to move around, transport between the source and then the utilization point. So we are already having a well-established hydrocarbon fuel infrastructure where we can easily transport the hydrocarbon like a natural gas or a methane or propane. And then we don't need to have additional installations for hydrocarbon transportations. And then directly utilizing in the fuel cell in the hydrocarbon will increases the efficiency of the fuel cells. And moreover, hydrocarbon is very cheap and useful fuel and will be readily available in all households. And then the second problem is that inside the material, conventionally nickel, and why is that? Is this zirconia-based material is used as the electrolyte material, because it's have high electronic conductivity, excellent activity for clean reforming fuels, and it will be physically and chemically compatible with zirconia electrolyte. But this nickel-based anode, when used with the hydrocarbon fuels like a methane, it undergoes a severe carbon coking problems. So this SEM image shows the carbon fiber formation on the nickel particle. This is the nickel particle. When exposed to hydrocarbon, carbon is formed here. Because of this, carbon coke will be built up in the anode chamber, and eventually cell will undergoes the breakdown. And the second problem is, first we start with the nickel oxide. Under reducing condition, that is in the fuel cell operating condition, nickel oxide gets reduced to nickel. That's where the fuel cell is operated. Once the fuel is shut down, then nickel is converted back to the nickel oxide. Here there is a volume change is happening inside the cell in the anode. Because of this volume change, the cell undergoes a severe degradation, or the cell will eventually break down. And then the second problem with the direct hydrocarbon fuel cells with the nickel-based anode material is the severe sulfur contamination. For example, in natural gas, there will be a huge, like over 100 ppm of sulfur is present in the LPG or methane. Because of this reason, this nickel electrode degraded very quickly, even within few seconds. And then the third disadvantage is the reoxidation, that is the redox stability. So there is an immediate need to develop a new electrode material that should not have any coke formation redox stable in sulfur containing fuels. Based on we can summarize that the requirement of the anode material is it should be compatible with the other fuel cell components. It should be electrically conductive. It should be catalytically active for fuel oxidation. In case of if you use the hydrogen, it should be catalytically active for hydrogen fuel oxidation, or methane fuel oxidation, or propane or jet A fuels. So we need a good tolerant electrode to function this good requirement to act as a good electrode material. So based on this strategy, I have developed a praseodymium barium mangan oxide as a layered perovskite materials. It shows the high structural property, that is the redox stability. It shows the excellent electrical conductivity. Redox stability means that fuel shutdown and fuel on. There is no volume change happening here. It shows the high fuel oxidation. Hydrocarbon fuel also it shows. The stability is excellent here. I will explain one by one. To prepare the layered perovskite oxide, first we prepared the simple perovskite oxide. Then when you expose it to reducing condition at 400 degrees Celsius, it undergoes a spontaneous phase transformation from simple to layered perovskite structure. And then this is the XRD of the simple perovskite structure and the layered perovskite structure. And then this is the electrical conductivity measurement of praseodymium barium mangan oxide anode. It was compared with other well-known alternative anode materials for solid oxide fuels. This is SMMO, strontium, molybdenum, magnesium oxide, LSCM, lanthanum, strontium, chromium mangan oxide. But our material shows the highest electrical conductivity of 10 Siemens per centimeter square under reducing conditions. When we fabricate a fuel cell based on praseodymium barium mangan oxide as an anode material and tested for a solid oxide fuel cell anode, it shows about 1.7 watts power density at 850 degrees Celsius. In propane, it shows about 1.2 watts power density in propane. In methane containing fuel shows about 0.5 watts power density. It shows with added catalyst about 5% added catalyst, cobalt nickel alloy catalyst. It shows the stable performance over 500 hours. There is no degradation at 700 degrees Celsius. Also, we have checked the stability of this anode material under 30 ppm sulfur containing fuels. Over 50 hours, there is no degradation in hydrogen. When switched to sulfur containing fuel, there is no degradation over 50 hours at 700 degrees Celsius. This shows that our electrode is very good active material for solid oxide fuel cells. Then we introduce the concept of exsolution. Exsolution is the process where the metal nanoparticles exsols from the perovskite oxide under reducing environment. So for example, this is the perovskite material when exposed to reducing condition at 800 degrees Celsius in reducing condition, that is in hydrogen. A small amount of transition metal, maybe here is a mangan or a cobalt, undergoes a segregation and then moves towards the surface as a catalyst nanoparticle. This is having advantage because this nanoparticle is stacked on the surface of the material. Here, some of the particle is stacked on the base material. Because of this reason, it will not undergo any agglomeration when operating temperature. This is the example for deposited material on the surface of the oxide perovskite material. When increasing the temperature and operating conditions, the cobalt, all the cobalt materials on the surface of the oxide agglomerate to form a more bigger particle. Because of this agglomeration, we lose the catalytic activity. So to develop this exsolution process, first we started with the praseodymium barium mangan oxide, and then we doped a small amount of transition metal. Here is a cobalt, nickel or mangan and iron, and at 800 degrees Celsius in hydrogen, it undergoes a exsolution to form the praseodymium barium mangan oxide with the transition metal, and small amount of transition metal is exhaled towards the surface. Here only a small fraction of the material is exhaled. Here I showed the TEM image. This is the bulk material and this is the cobalt exhaled on the surface of the material. Based on the DFT calculations, we found that not all the transition metal segregate towards the surface of the material. Only the cobalt and nickel exsolved, but compared to nickel iron. This is due to high co-segregation energy compared to the iron. This cobalt and nickel having high co-segregation energy compared to mangan and iron. Because of this reason, cobalt and nickel is more exsolved, and mangan does not show any exsolution. Iron does not show exsolution. Then we developed adapted the image here. The root one shows the conventional exsolution process. The perovskite material is presented, and then the small amount, the blue one is the small amount of transition metal, either can be cobalt. Under reducing conditions, a small amount of cobalt is exsolved towards the surface of the material, but some of the cobalt material present in the bulk of the material, but not all the cobalt is exsolved here. So using our second strategy, we completely exsolve all the cobalt materials present in the bulk of the material so that we can utilize the full catalytic activity of the catalyst material. So for this, first we prepare the perovskite material with the transition metal dope. Second, we deposit a small amount of iron on the surface of the material, and then we do the reduction process, that is exsolution process. Here, the iron diffuses in bulk of the material towards the bulk of the material and exchange its position with the iron, with the cobalt, and then all the cobalt material is exsolved. So we start with the cobalt here, and then during reduction, iron diffuses into the bulk of the material, and then all the iron cobalt is pushed towards the surface of the material, and the iron is exchange its position in the bulk of the material. Based on exsolution DFT calculations, we found that why this iron undergoes the topostatic ion exchange. First, the iron is deposited on the material in the first step. Second, due to the positive incorporation energy, iron is switched its cobalt position. Iron diffuses to the bulk of the material into the cobalt position, and then cobalt moves towards the iron positions, and then the excess iron is reacted with the cobalt to form the alloy, and the iron goes into the bulk of the material in the final state. This is due to the because of low co-segregation of energy of iron, it tends to diffuse into the bulk of the material. Using the new exsolution strategy, we did a dry reforming test in methane. So the importance of dry reforming, sorry. The figure shows the dry reforming of the methane. This is the support, perovskite support, and then cobalt iron alloy exsolved particle is present on this. And the dry reforming of methane, it undergoes a role of de-alloying and alloying process. So in de-alloying process, sorry, I will go with the alloying process. In alloying process, methane reacts with the cobalt surface to split into carbon and the hydrogen, and then carbon is deposited on the surface of the cobalt. In de-alloying process, this deposited carbon reacts with iron oxide to regenerate the carbon monoxide on the cobalt surface and the iron surface. This iron oxide reacts with the carbon. This iron oxide is formed in the de-alloying process by reacting with the iron and then carbon dioxide to form iron oxide, and then carbon monoxide is formed here. So here the STM image shows the iron oxide present in the exsolved nanoparticle. This is the praseodymium, this is the barium, this is the mangan oxide, cobalt oxide here. This iron oxide shows in the bulk of the material. There is no cobalt oxide in the bulk of the material. This is the oxygen. Based on this strategy, we fabricated a solid oxide fuel cell. This is the porous praseodymium barium, small amount of cobalt doped material, and then we deposited a little amount of iron, undergoes exsolution to form the topostatic ion exchange. This is the SEM image. This shows that this yellow highlighted region shows the exsolved nanoparticles. By increasing the amount of iron doping, we can increase the amount of exsolved nanoparticles. So this is the praseodymium barium mangan cobalt without any ion deposition. Only few number of cobalt nanoparticles are generated at the surface of the material. Second, we deposited 3 weight% of the ion. It shows increases the cobalt nanoparticle formation. Then we increase to 12 weight%. It shows more number of cobalt nanoparticles. So this is the TM image of a praseodymium barium mangan iron oxide, and then this is the cobalt iron alloy particles. So here is the praseodymium bulk of the material. Praseodymium is presenting there, barium is present there, mangan is present there, and then there is no cobalt present there. First, we started with the cobalt material where bulk will contain the cobalt material, but after exsolution, there is no cobalt element present in the bulk of the material, that all exalt towards the surface. And then after depositing the ion on the surface of the material, this diffuses into the bulk of the material. We can see there is the bulk of the material having ion diffusion. This again confirmed by TM HAB patterns. Here you can see that there is an ion present in the layers of the material, but whereas in the cobalt, there is no signals for cobalt in the bulk of the material. After that, we fabricated a fuel cell based on the topostatic ion exchange process. This is without any catalyst, but topostatic ion exchange material shows the power density was increased from 1 watt power density to 2 watt power density in hydrogen at 800 degrees Celsius, and the dry reforming of methane at 800 degrees Celsius. Topostatic shows about 10% of CO2 conversion, whereas at 900 degrees Celsius it shows 30% CO2 conversion, and it shows the carbon monoxide selectivity about over 50%. Again, we check the stability of the carbon-dioxide conversion in dry reforming of methane. Or 200 hours, there is no degradation and no carbon coke formation in this material at 800 degrees Celsius. So in conclusion, we have developed a high performance PBSCF cathode material for solid oxide fuel cells, and then we developed a praseodymium barium mangan oxide as the anode material for solid oxide fuel cells. In conclusion, we say that the perovskite materials are very attractive electrode materials for solid oxide fuel cells. Also, this layer perovskite material have applications in metal air batteries, proton conducting solid oxide fuel cells, solid oxide electrolysis cells, and other applications. Thank you.
Yes, thank you very much, Senkudan. You are completed on time. Thank you very much. Senkudan is a very nice talk, and I think this solid oxide fuel cells, actually, I could see a very rare people working in this topic. In India, I don't know who is working on this kind of topic in India. Anyone is working on this topic in India?
A few people working in Banaras Hindu University, IIT, BHU, and then one of the group were doing the modeling in IIT Delhi at metallurgy department. Frankly, there is no material development or catalyst development in India going on there, but there is a modeling and other works are going on there.
Yes, that's when I could see a lot of experimental investigation, optimizing the catalyst and working with several models of the catalyst. Really interesting, actually, because these are technology-oriented research work, and directly you go to the practical applications.
Yeah.
And okay, one of this main problem already perovskites reported to be highly unstable at a certain condition, but how? What are the stability issues regarding this kind of catalyst?
So in terms of cathode BSF material, the stability issues we can say that it depends on the oxygen partial pressure. So for example, BSCF, that is a praseodymium barium.
Yes.
So these cathode materials, when we use it in anode operating condition, the oxygen is completely reversed. It undergoes a severe degradation. The material will be decomposed to barium oxide, strontium oxide, cobalt, and iron. But we need to carefully design the electrode material for where the where the material is stable in hydrogen condition. Because of this, mangan is present in the B side. It undergoes a multiple oxidation state. Under reducing condition, mangan can take a +2 state, +3 state, and then +4 state. Because of this multiple oxidation state, this material is very stable under reducing conditions. But once we replace this mangan with completely with the cobalt can take all these transition state, but majority of the state goes to under reducing condition. It will be a 2+ state. Because of this reason, cobalt cannot be used as an anode material in solid oxide fuel cells. Whereas the mangan, majority of the state, although it can take the 3 state, +3, +2, and then +4, majority of the states will be +3 and then +4. Because of this reason, mangan-based materials are stable in reducing conditions.
And is there any, do you have any, because the system seems very interesting, is there any commercialization of this kind of catalyst? Do you have any idea?
So currently, we in my previous work, so this Miko company, in the fuel cell company, they started commercializing the fuel cell after our novel catalysts were published. So this company is interested in developing the new cathode material. So they already installed a prototype solid oxide fuel cell at Ulsan National Institute of Technology, running on the hydrocarbon fuel cells. So still it's a commercial, alternative anode materials are still under research, under prototype development only. But the conventional electrode material like a nickel, that's already commercially available. For example, in fuels, in USA, very big companies, the corporate companies, Bloom Energy, and the very other companies are there. Many other companies are under commercial.
Yes. In the Indian scenario, this kind of solid oxide fuel is not much grown, and not much invested. Any research work or other funding engines, I don't think they are come forward to fund this kind of solid oxide fuels in India. Maybe this is a good opportunity if you come back to India, maybe you can venture into this kind of research work. I appreciate your interest. All the best for your future endeavors. Okay.
Thank you.
Thank you very much your presentation, Sengodan, because I know that now this is a very critical time. I hope COVID also a very serious issue in the UK also. Thanks for sharing your valuable time in this critical COVID-19 time. Thank you very much.
You're welcome.
Yeah. Even I would like to join my colleague. Thank you very much, Prakash, Dr. Prakash. And thank you for your time and sparing your effort. And I want to extend an open invitation to you to visit our center. Thank you very much.
Okay, sure. Thank you.
Thank you. Now I'll contact you. I will send you a mail to you.
Okay. Any other questions?
Thank you very much. No, that's all.
Okay, thank you.
Thank you very much. Thank you. Yeah, I'll hand over to the organizer now.
Yeah. So the next talk is going to be by Riley Batra. Riley, thank you very much. Very good morning. It is my pleasure to welcome you on behalf of my university, Vellore Institute of Technology, V8 University. So we have two more important guests actually. Professor Eket Grol is the chair of Mechanical Engineering Department at Purdue University. I would like to extend a warm welcome to Professor Eket Grol. And thank you, sir. Thank you very much for joining us. And we have another important professor, Professor David, Professor of Mechanical Engineering at Purdue University. So both of them have joined with Mr. Riley. I want to welcome all of them. Mr. Riley is going to talk on advancements in transcritical carbon dioxide refrigeration cycles and ejector design. Over to Riley.
Great. Thank you very much for the kind introduction and for the invitation today. So as the introduction stated, my name is Riley Barta. I'm a PhD candidate at the Herrick Labs at Purdue University studying mechanical engineering. And this morning, my talk will be on advancements in transcritical CO2 refrigeration cycles and ejector design. So the overview of the talk will begin with a background of the issue. Then we'll give an overview of some CO2 refrigeration systems. And then we'll go through the experimental test stand work we've done here, as well as ejector design, before finishing with conclusions and future work. So for just some context here, if we look at the refrigerants that have been used over the last, let's say, couple hundred years, right? Refrigeration wasn't terribly prevalent until the end of the 19th century, at which point it was mostly industrial chemicals. And interestingly enough, carbon dioxide was actually one of the first refrigerants used at this time, primarily in marine application, due to the ability to reject heat to the reasonably low temperature ocean. However, compressor technology couldn't keep up with the required demand and efficiency. And then the advent of the chlorofluorocarbon, or CFC, in the 1930s then dominated the market and took over from there. However, CFCs do have high ODP, which is known as ozone depletion potential, and GWP, or global warming potential. If you have, moving on to the 1950s, you have HCFCs, or hydrochlorofluorocarbons, which have a lower ozone depletion potential, but still have a very high GWP. For example, we would have R22, which is still found in some residential units today. And then also if you move really to the 1990s, then we're into the HFC, or hydrofluorocarbon, which is much more prevalent today. Many cars have this, for example, R134A. Now we've eliminated ODP, or ozone depletion potential, but we have still a reasonably high global warming potential. So then this brings us to today. The two primary challenges and really fields that we've been looking at today are natural refrigerants, or hydrofluoroolefins and hydrofluoroolefins, or HFC blends, right? So some examples of natural refrigeration would be carbon dioxide, which is the focus of the talk today, or propane or ammonia, right? So while these fluids are much better for the atmosphere relative to their synthetic predecessors, they each have their own application issues of propane's flammability, of course, ammonia being toxic, as well as not being able to use copper piping, right? So all of these different solutions that we're faced with today, none of them are as perfect as we thought the previous solutions were, but being aware of the global warming situation, we need to adapt our ability to develop these cycles and make them efficient while also being environmentally responsible with our choice of working fluid. So we look at CO2, which is the focus of today's talk, right? As a refrigerant, it's got some very unique thermophysical properties. So CO2 is the base unit of GWP, or global warming potential. The idea being is that we can have some equivalence where if you lose X number of kilograms to the atmosphere, it's equal to, if it's a GWP of 100, that's equivalent to 100 kilograms of CO2 being released to the atmosphere in terms of the effect on global warming. Carbon dioxide is the base unit. We have a GWP of 1, which is wonderful from that respect. It's also non-flammable and non-toxic, with a high volumetric heat capacity, around 5 times that of R22, which helps us keep smaller volume systems. Now, when we say transcritical, if we look at the pH diagram shown on the right here, if you really, from a vapor compression cycle, simplified, you would compress from state 1 to 2, and then you would reject heat to the ambient from 2 to 3, before you would expand from 3 to 4, at which point you would then pull heat through the evaporator from the conditioned space from 4 to 1. When we say transcritical, that basically means that the cycle is exiting or is going all the way up from 1 to 2 above the vapor dome. And then from 3 to 4, you'll basically expand into the vapor dome. So transcritical meaning you're crossing the critical point. The reason that CO2 needs to run transcritical is because we have a low critical temperature of 31.1 degrees Celsius and a high critical pressure of 7,400 kilopascals. So that basically means that to reject heat to any appreciably warm ambient condition, you need to have a very high pressure. Now, that gives us advantages and disadvantages, right? The disadvantages are that we need to pull a significant, generally more compressor power in order to achieve the heat rejection, but it does free the high side temperature and pressure, right? In the two-phase region, temperature and pressure are not independent, but in the single-phase region, they are. So that basically allows us to say, okay, now we've got a degree of potential optimization in the high side pressure for a given ambient condition. Now, the challenge is that because of the increased compressor power necessary to achieve this transcritical state, generally requires more complex architectures to have a COP, which is competitive with HFC cycles. And the COP is just the coefficient of performance, which is the ratio in cooling mode of the heat transfer rate of the cooling air or the cooling fluid divided by the amount of net power needed to achieve that cooling. So if we talk about some of these modifications that help us become more efficient with transcritical CO2 cycles, one of them is known as open economization, which relies on a flash tank or phase separation. And there's a photo shown on the top right there where you basically have a two-phase inlet from the outlet of some expansion process, for example. And then you have liquid outlet from the bottom and vapor outlet from the top. So it relies on gravity, but in most applications that's not a challenge. And this can lead to higher performance than closed economization, but is somewhat difficult to control, especially given transient nature of phase separation. However, it can have high performance benefits than intercooling, which is basically just putting a heat exchanger between two stages of compression when utilizing the evaporator vapor bypass, which is one potential architecture with open economization. If we look at closed economization, that's an example of, for example, an internal heat exchanger, where we can basically transfer heat between different streams of the same working fluid to be thermodynamically advantageous. So for example, as shown in the schematic there, you could further subcool and then expand a portion of your fluid, go through that internal heat exchanger, and then you have vapor, which allows you to cool your compressor to decrease the discharge temperature while also increasing your subcool of your system to have increased efficiency or increased capacity, for example. Now this can also have a higher performance benefit than intercooling and is also controlled fairly similarly to how evaporators are controlled through an upstream expansion valve, such as an EXV or a TXV, which is the tried and proven control method. If we look at some other common cycle architectures, on the right-hand side, you have a schematic that kind of epitomizes a few different ways that we can modify these cycles. The first one on this slide would be parallel compression. So if you look at the two compressors denoted by the number 9, the idea there is that you can run a broader range of necessary or required capacities still with high efficiency, right? So for example, if you're running at a 50% load for the cycle's maximum cooling capacity, you can then just turn off one compressor such that you can run the other compressor in a variable speed range that still retains higher isentropic and volumetric efficiencies. So you're able to basically have an increased efficiency of your cycle over a broader range of required capacities. Of course, this is a redundancy as well for increased robustness and is commonplace in supermarket and industrial applications. For the evaporators, if you have a flooded evaporator, right, the idea here is that you're able to control the upstream condition of the evaporator in a way that basically minimizes, if not completely eliminates, evaporator outlet superheat. Now, they'll obviously put a receiver at the outlet or an accumulator so that we can protect the compressor. But the idea here is that the heat transfer coefficient in the two-phase region is significantly higher than that in the superheated vapor region. So if we're able to control it such that all of the heat exchange in the evaporator happens at a two-phase state, then we can move more heat with less surface area, thus saving money and also increasing overall heat transfer efficiency. Now, if we look at one of the most popular modifications, or at least the most promising modifications in carbon dioxide, it's expansion work recovery. The reason that this is so popular, we'll talk about in the context of thermodynamics in a moment. But an example of this would be an ejector, where you're able to have a fixed geometry, variable geometry, or multi-ejector. Now, we're going to talk much more about this over the course of the talk. But the idea here is that it's a reasonably passive device that basically just utilizes an increase in kinetic energy to decrease the compressor work. But we'll go into the inner workings there in a moment. The other primary method of expansion work recovery is through an expander, which basically just mechanically pulls that potential work out of the expansion process. And the two most common ways that that's been done is through positive displacement or turbo machinery, some examples of which are shown here in the two figures on the screen. So if we look at a more fundamental thermodynamic aspect of expansion work recovery, you have a pH diagram that we've discussed in a few slides prior. Right, so if you have an isenthalpic process where enthalpy is considered constant from H3 to H4, that's what we find in most of our vapor compression cycles. It's able to be done with an electronic expansion valve or thermostatic expansion valve, which allows nice control, it's low cost, but you don't recover any of that work. The And of course, you have the thermodynamic limitation, which is H3 to H4S, or an isentropic expansion process, right? So that's where you have a constant specific entropy over the course of your change in pressure. In reality, your expander will bring you somewhere between the two, where you have some H3 to H4E, where you move towards isentropic expansion. Now, from the first law, if you assume adiabatic, you can get that the power that you receive is equal to the mass flow rate times the change in specific entropy. Now, basically, how far can you get between isenthalpic and isentropic is quantified by your isentropic efficiency, which is shown by the equation eta IS on the bottom right-hand side here, where you basically have your realistic change in specific enthalpy all divided by your goal, your ultimate change, or your maximum, which would just be isentropic. Then once you have that method of quantification of that efficiency, you can find out exactly how much power increase you can pull out through the equation m dot delta H. And then that can either be fed to a generator to reduce the net work input, or mechanically coupled to your compressor to physically decrease the net work input. Not only do you get that net work input benefit, but as you can see with the lower specific enthalpy inlet to your evaporator for a given mass flow rate, you also get a higher cooling capacity. If we look more closely at an ejector and how it works, draw your attention to the schematic on the top left-hand side and the pH diagram corresponding to the same schematic on the top right, you'll come out at a high pressure state at MI, which is basically your gas cooler outlet. Then this flow is accelerated to MB through a motive nozzle, as shown here on the left. Now you have a high velocity flow, so you have a significant amount of kinetic energy. What that does is that entrains your evaporator outlet flow from SI here. Then it'll bring them into a mixing section, increase the pressure, and then go through a diffuser to further increase the pressure, provided it's not sonic in the mixing section, and give you some diffuser outlet state in the two-phase region. Now, what's important to note here is that there's a pressure differential between D and SI, right? The notion there is just utilizing expansion work that was previously wasted in the past, you're able to basically create a pressure differential between the diffuser outlet and the evaporator, or the evaporator outlet that was previously non-existent. So before you would have had to compress from that evaporation pressure, but now we'll compress from the diffuser outlet after you enter a phase separator to basically allow single phase fluid entering the compressor. So that free pressure is really the essence of why the ejector is so valuable. And on the bottom left-hand side, you can see some work that was previously done by our research team in kind of a physical manner of how this truly looks, right? Where you can see that the motive nozzle inlet flow is upstream. It's accelerated through a variable geometry needle here, at which point it entrains the suction flow in this pre-mixing section here before mixing and then diffusing to a higher pressure to give a more tangible example of what that looks like. Select CO2 cycle modifications. You can basically see a broad range here of different modifications that you can have from, let's say, normalized against the baseline cycle. You can see how with internal heat exchangers, expanders, ejectors, and things like that, you can get, you can approach 150% normalized COP with all these cycle modifications. But the question is how much is necessary? What makes sense for your application? And that's kind of the essence of what we're trying to do. If you look at a multi-stage evaporation cycle, which is what we're going to be discussing experimentally, basically the idea is that you have two evaporators or multiple evaporators in the same vapor compression cycle. So instead of having isolated complete vapor compression cycles for different temperatures and pressures, you're able to have one large cycle that's more complex, but it is centralized. So for example, in a supermarket, that's helpful to have everything in the back where you can access it more easily. Now, then you can have some medium temperature evaporation for your food that you just like to keep cold. And then you have low temperature for freezing your meats and things like that, all in the same cycle. Now, this is seen on the order of 50 kilowatts to several hundred kilowatts in supermarkets, but it's also done in transportation. If you require versatile storage opportunities and things like that. For example, one day you want to haul 60% of your load is frozen and 40% is just cooled, and the next day that's flipped, right? You need to be able to not only be able to operate at different evaporation temperatures, but also distribute the load between the two. So that's some background of really what we've been focusing on here and really the motivation for the work that we've done. So if we move to what we've done here, right? We've talked about a fair amount of different cycle modifications and things like that. Now, of course, the literature, since it became a common topic, has been looking more and more into, right, cycle modifications here, right? How much benefit can you get with one or two of these, right? But what is generally lacking is a more comprehensive analysis of, upwards of, let's say, 6 or even 8 different cycle architectures, all with the same cycle, all with the same components, your heat exchangers, compressor losses, and things like that. Furthermore, being able to do that and switch between these architectures on the fly, so we're not just capturing steady state performance, but we're also capturing transient nuances that we might not have been able to predict with just steady state modeling, right? So that's really the motivation for what we're doing here. Right, and we'll have 2 primary different modes, where one is through an electronic expansion valve, two different modes of expansion, excuse me, where you have an EXV driven cycle where we'll have several different EXV driven modifications, and an ejector mode. So that allows us to compare a cycle that doesn't use expansion work recovery with one that does, and things like that, as well as several. See, as I mentioned, right, we'll share as many components as we can: compressors, heat exchangers, flash tanks. And we'll prioritize our ability to control the cycle. So we won't, right, so that's important. We'll have redundant instrumentation, and then again, we'll be able to transition between cycle modes without turning the compressors off. If we look at kind of a high-level view of what the stand looks like, right, this is a theoretical pH diagram on the right and a schematic on left that shows our EXV mode cycle and what we're trying to do, right? So a few things to draw your attention to. We do have multi-evaporator architecture. So you'll have your medium temperature evaporation from 11 to 12 and your low temperature from 17 to 18, right? Let's say your source temperatures of 0 Celsius and -20 Celsius, more or less. Each of these evaporators has their own dedicated flash tank for economization. And as I touched on with open economization, right? The notion here is that you utilize phase separation to increase cooling capacity. So if we came in at state point 14 at a 2-phase state, we would then flash and send the vapor around the evaporator and then send the liquid down to state point 17 to enter the evaporator, right? That gives us a larger delta H across the evaporator and also decreases the superheat of the compressor suction at the outlet due to mixing with saturated vapor at 15. If we turn our attention to the schematic, that covers the low side aspects of the schematic. We do have one booster compressor between the 2 evaporators. And then you have basically a 2-stage compressor with intercooling that allows us to get to the high side pressure, where we gas cool from 6 to 7 before entering the EXV, which is, again, why we call this EXV mode, is the high side expansion. There are still several EXVs in both cycles. So anyway, that's an idea of what we're trying to do. And you can see here that on the pH diagram, the goal is to maximize our delta H for cooling, while also making sure that we keep our compressor discharge temperatures down, both of which are very advantageous for COP. On the ejector side of things, right, you'll see that a lot of the cycle is somewhat unchanged on the right-hand side, right? You still have your 2 stages of compression, for example. But then at state point 7, instead of going into an EXV, we're going to go into the mode of nozzle of the ejector, right? And we'll pull the medium temperature evaporator outlet at state point 13 into the suction flow, and then diffuse at a higher pressure into this 2-phase, into the flash tank, where we'll continue the rest of the cycle as was previously shown. Is that this pressure differential from 13 to 2 is what I was explaining in basically the introductory slide for the ejector, right? If we did an ejector, we're evaporating at pressure at 13, that's where our compressor inlet pressure would need to be. It would be further, right? But because we're using an ejector, at state point 2, we have a higher pressure that 3 will then compress from. So this 2 to 13 delta P is essentially free, right? That's how we've converted the expansion energy into something that tangibly we can use. And that's really the motivation for the expander in general, or for the expansion recovery. So then, all right, we talked about wanting to do this in the same cycle with many shared components. How can we do that physically? So I have basically a simplified schematic here, where it's color-coded depending on the working fluid path, depending on which architecture we're using. So in green, you basically have where the refrigerant will go no matter whether you're using EXVs or ejectors, right? You can see that the vast majority of the cycle is actually shared in that respect, which is a good thing in terms of minimizing external or additional piping. If you look at the EXV mode, right, you basically go from the gas cooler outlet into the flash tank, and your medium temperature evaporator will go to the compressor section, as we described a couple slides before. And with the ejector mode, right, you'll send that high pressure flow through the ejector motive nozzle, and then you'll basically reroute the flow from the evaporator outlet. Instead of going directly to compressor suction, you'll use that as your suction flow before it then diffuses to a higher pressure, enters the flash tank, and then continues back to the compressor and the rest of the cycle through the liquid lines. So that's how we're able to basically put so many cycle architectures within one cycle, right? And when we continue to say, right, we want more than just two architectures, right? We can basically turn economization on or off for each of these cycles. So because we have two different expansion methods, two different types of economization, that allows us to bring a lot of different comparisons to the table. So then if it's an experiment, right, how do we control this? If we have basically where the experiment is placed, it's put in cyclometric chambers at our A.W. Herrick labs. So that allows us to control the ambient temperature and humidity. However, we also want to be able to control the evaporators quite well. So instead of using air source evaporators, we elected to use two different, basically ethylene glycol baths to control the evaporators separately. So what this allows us to do is reasonably independently control the evaporation temperature and capacity independent of each other. So that's what's shown here is that we'll have two different chillers, right? One is for the low temperature evaporator and one is for the medium temperature evaporator to make up independent heat sources. And then we'll have a heat sink, which is the ambient air. This is a photo of what the cycle looks like in the site chambers. And if you want to get maybe a better idea of where things are placed, this cycle here, or this photo here, shows on the left-hand side, we'll have our medium temperature ethylene glycol bath with the lines running to the evaporators, low temperature bath, and then our CO2 system, right? You can see your intercoolers and gas coolers here. And then from a high level view, right, you can look a little bit closer. On the left-hand side, you can see our EXVs and ejectors, right? This is the high side, both options. So they're in parallel, again, with those valve changes being all that's necessary to switch between modes. Here you can see the two plate heat exchangers, right? These are our two independent evaporators with medium temperature and low temperature. And then you can also see our two compressors that are eventually in series. The right compressor is single stage and the left compressor is a two-stage with intercooling in between. How has this been working? Right, this is experimental data that we've taken. And the idea here is if we have bulk economization, right? This is the most complex version of the EXV cycle that we can run. So some things to draw your attention to is, first of all, it was able to be stable. Second of all, we were able to evaporate from -40 Celsius. And then we were able to do this at a moderate ambient condition of around 22 Celsius. We were able to have all this temperature lift basically without exceeding, right, 90 degrees Celsius. All of this cooling for the compressor really worked fairly well. Some things that aren't so good, you can see here that at 8, we would enter a flash tank, right? And in theory, those saturated liquid would put us on the saturated liquid line. The point here is that we didn't quite reach that. And the reason for that is we weren't bypassing vapor at a high enough rate. So by conservation of mass, it was having to go out the bottom of the flash tank, thus decreasing our overall cooling capacity. So that's since been hopefully addressed. We're still working on testing that, but we were able to capture that with redundant energy balances throughout the cycle. Then around 8 kilowatts. And while that is an order of magnitude lower than most, it's important to note that that is also, right, it's very scalable. The thermodynamics, the COP, is a dimensionless number, right? So to draw your attention to. Look at experimental results from the ejector, right? This is a bit more closed cycle. We didn't evaporate quite as low here. What we were able to find is that we reached stable optimum. We were able to get pressure lift from the ejector here. And we were able to retain a reasonably similar cooling capacity. So we have more comparisons with the ejector that look even better. Now, if we look at transient operation, right, we talked about that being one of the goals. What this shows is basically our ability to go from EXV mode at steady state, which is shown on the left side. We have 3 main pressure levels of the cycle being gas cooler, medium temperature, and low temperature evaporation here. So what we did is from this mode, we transitioned to the ejector without turning the compressors off, right? So yes, we lost a good amount of pressure differential here, but the cycle didn't completely collapse. So what was required here is we basically had to go from EXV, we had to open the ejector such that we were expanding the EXV and the motive nozzle. Then we had to open the evaporator bypass such that we were sending evaporator flow to the suction nozzle and the compressor. And then you turn off the flow to the compressor and you turn off the flow to the high side EXV, right? So we don't want to ever just stop the flow in the system. So it has to be done in a reasonably particular order. And that's what's shown here. But after that, we were able to achieve steady operation. And then what we're seeing here is we were able to basically move that the motive nozzle in such that we decreased the motive flow diameter and basically we're able to achieve similar to that same high side pressure and then allowed it to slowly reach steady state. So this is something we want to look a bit more into, but it was a promising start in terms of transient operation and the transition between EXV and ejector mode. If we look at some EXV versus ejector comparison data here, right, many people are familiar with the notion that if you have that maximum, or if you have a decoupled temperature and pressure on the high side with transcritical operation, then you can basically sweep pressures for a given temperature to find an optimum COP. Now, we didn't sweep nearly enough pressures to achieve a true optimum, but you can see that we were able to reach steady operation at 3 different high side pressures and achieve slightly different COPs at those pressures, which was kind of a validation of future work that we want to be able to do. Similarly, we did the same with the ejector, right? So we were able to use 3 different motive nozzle positions that push up and to the left such that we were able to achieve 3 different gas flowing pressures, and the cycle basically reacted accordingly, which was a nice result. And you can see kind of the initial comparisons between ejector and EXV operating. Next steps, we want to narrow the energy balance on the secondary fluid side so that we can capture efficiency of separation, monitor the liquid level, and then conduct some more parametric studies of modifications to performance. So now let's move into the ejector design portion of the work, right? So I already gave this overview of the ejector, but here's a physical ejector that's been used. Basically, we pulled experimental data from this work. This was the same technical drawing that I showed in the initial introduction, but it's a physical ejector, right? So this would be your motive nozzle needle that goes in and out of this hollow needle here to basically change your high side delta P. And then this whole assembly moves in and out here such that we can change the suction nozzle diameter as well. Your motive flow comes in here, is accelerated, entrains suction flow from here, mixes, and then diffuses at a higher pressure. So if we look at 2 primary previous works that have been done by our research team, right, there were kind of 2 main ways to model an ejector. One was done in 2005 with flux-based modeling, but constant efficiencies. So the flux-based was a benefit because it was maybe more broadly applicable. It didn't require geometry, but because it had constant efficiencies, we weren't able to capture basically variations in efficiencies over operating conditions, and there were no considerations of mixing losses. Now on the other side, there was a higher fidelity model developed and experimentally validated in 2013. And the notion there was that we had basically polynomial-based efficiencies from experimental data that allowed us to say, here's your motive nozzle efficiency, and here's how it varies with operating condition. So it was much more accurate in that respect. However, that model required dimensions as an input, right? So it was only for a specific ejector that you already had. So what we want to do here is take the best of both worlds, right? We want to be able to take the increased efficiency or basically the increased accuracy of the polynomial-based model with the mixing nozzle or mixing section losses, but make it flux-based, right? So if it's flux-based, then you can scale it as a function of mass flow rate and then get your dimensions out. So that's really what we've been focusing on here. From a quick numerical perspective, the motive nozzle, our criteria for convergence is choked flow. So we really would on the outlet state for a given inlet state until we were able to achieve choked flow or reach within the tolerance of speed of sound. The suction nozzle was slightly more complicated because basically you had to use an area ratio or a diameter ratio from the motive nozzle. Now, how can we do that if it's a flux-based model? And the idea is that we don't actually need to call in a mass flow rate to be able to do this. If we have an entrainment ratio, then we can basically create some pseudo mass flow rate, let's say 1 kilogram per second. And by the entrainment ratio, we can find the suction flow rate, and then use that to basically find out the outlet velocity from conservation of mass and compare that to the outlet velocity from from conservation of energy. And once those two close, we know that we have a reasonable suction nozzle output state. For the mixing section, we would look at the velocity from conservation of energy and conservation of momentum. Once those two agreed, we were okay. And for the diffuser, this lift coefficient, some C sub T, was proposed in the earlier papers I previously cited. But the notion is there, you can create some C sub P, or C sub T as a ratio of several thermodynamic and geometric parameters, and then use the second equation there to calculate your diffuser outlet pressure. Another thing to point out is this is another area where we used geometric ratios, some areas mixed by some area of diameter. Why that's important is you can input those and then scale it by any mass flow rate that you want, right? So you've got these geometries that have been experimentally validated, and you can take the ratios of their key components. And if you input into this model, then you can basically have a flux-based model that captures ratios of geometries. Then once you pass in the mass flow rates that you actually are applying this for, you can output geometry. And that's really what we've been going for here. So the first step of our model was to validate against experimental data, right? So what we did is we took the data from the 2008 work from our research team, and we also took their experimentally derived polynomials. So we basically rebuilt some aspects of that model, but did so on a dimensionless basis. Then we would pass in the mass flow rates from that experimental work, compare the geometry to what actually, which geometry was truly used for the ejector. And that was our validation steps. So if you look on the left-hand side, you can see the geometries throughout the cycle. You've got your, basically your motive throat, your suction throat, your mixing section, and your diffuser outlet were really the primary areas that we looked at. And you can see on the right-hand side that the diameter of the physical ejector was around 4 millimeters. And over the range of conditions that we looked at, we used experimental data for the motive and suction convergence here, but this basically numerically validated our ability to predict the mixing section and diffuser outlet geometry within 10% for a fairly broad range of conditions here. Now, if we were to look at that same idea, but do it completely numerically, right? Previously, we checked experimental data to converge the motive and suction nozzles. Here is completely numerical, right? Where you have just thermophysical properties as your inlets and outlets, and then your mass flow rates from experimental data. You can see that to get all 4 points to converge, or all 4 components to converge was numerically challenging, but once they did, they all communicated quite well, right? You have reasonably accurate diameters for your motive and suction nozzles, which were over a broad range of physical dimensions. And then the diameter in the mixing section also agreed quite nicely. So once we were able to consider our model validated more or less, we looked at key aspects of ejector design. Some of these key aspects were the ratio of the mixing section diameter to length, diffuser length to mixing section, diffuser angle, and then of course motive and suction nozzle design. But you can see that 2 of those ratios are all based on our ability to accurately model or predict the mixing section diameter. And that's why that calculation is so vital. Now, we also wanted to look at, okay, well, which components are more sensitive or which components can have a stronger effect on efficiency than others, right? So if you look here on the y-axis, we have the overall ejector efficiency, right? And then what we did is we looked at, for the x-axis, for a range of motive nozzle efficiencies, how can changing the diffuser efficiency and the suction nozzle efficiency affect the overall ejector efficiency? And what we found was that we would argue that the upward trend in motive efficiency makes sense. But if you look at the potential change in impact from 50 to 90% of the efficiency of the diffuser changes only across the green colors, right? However, that same difference from 50 to 90% in suction nozzle efficiency will go from X to X, right? So you can see that we have several times the change in, or basically the effect on the efficiency with the suction nozzle efficiency relative to the diffuser efficiency. And that's absolutely vital for us to be able to prioritize which component we want to have maximum efficiency with. Now, if we look at how does the efficiency affect, right, the input efficiency, how does that affect our actual diameter output from our design script, right, or a design model? And you can see that, yes, the motive throat is more or less only affected by the motive efficiency, which should make a fair bit of sense. But what's notable is here on this slide, where you can see that the mixing section diameter is exceptionally affected by the suction nozzle efficiency, not as much by the mixing or the diffuser efficiency, or even the motive nozzle efficiency. This was quite an interesting find, but all of this results in our ability to kind of predict which design we should be using, or at least understand how we can look at, for a given mass flow rate and entrainment ratio, that these efficiencies will affect our geometry. So what do we do with this, right? How does that help us? If you look at some previous work here shown on the bottom left-hand side, you can basically see that if we're able to achieve the relationship between the W, which is the entrainment ratio, or basically the mass flow rate of the suction nozzle, divided by the motive nozzle mass flow rate, if you're able to relate that through the outlet quality of the diffuser by this equation here, you'll have a maximum COP benefit, right? Now, to realize the cycle by conservation of mass, it can be an inequality, as shown in the second equation. However, that's done through a bypass, which then overall decreases your COP effect. So the goal is to reach this point here, and that's really the essence of using this design tool, is to utilize these kinds of relationships to input the efficiencies that we'd like, and then see what design we get out. So if we look at numerical next steps, right, we want to utilize the design tool to design a more efficient ejector, then prototype and experimentally validate our predictions, and then potentially even extend those efficiency polynomials from the initial range from that paper. That'll enable increased accuracy of ejector modeling over a broad range of conditions and maybe even working fluids. So the conclusions from this presentation are that we were able to develop an experimental transcritical CO2 test stand that's able to look at different architectures in both steady state and transient operations. We validated its operation and transient and have laid out next steps there. And then for the numerical aspects, right, we have a flux-based ejector model that we validated against experimental data, and an outline for an overall design tool has been presented. I'd like to acknowledge my advisor and colleagues. So Dr. Eckhard Grohl, of course, is my PhD advisor. Worked very closely with Professor Diviani as well. The Bechtel Corporation has supported us and provided motivation with some of the patents for some of our cycle architectures that we've shown. And then I'd also like to thank the Purdue MU Senior Design Team from fall of 2018 for their assistance in the experimental work. With that, I'd like to thank you. I very much appreciate the invitation, the chance to be here today, and I'd be happy to answer any questions.
It's a pleasure. Thank you very much. Riley, I have a couple of questions.
Yes.
Whether this system, a transcritical carbon dioxide system, is suitable for conditions like India, tropical conditions in India, where the temperature would be very high, something like 40 degrees Celsius.
Currently, I wouldn't say so. There are some small pilot plants being done in those types of ambient conditions. So for example, there's work that's done by a Norwegian university that's been validated in Jordan, which has maybe not as high as 40 all the time, but I'd have to look at the weather data. And that's been quite well, but that is a very complex system, and they're not done very often, right? Right now, it's more of a prototype idea. Where I think carbon dioxide cycles may work very well in Indian applications would be in a cascaded cycle, where you're able to utilize the low side benefits of CO2 and then reject to another working fluid that can work better at high ambient conditions. A supermarket example would be a CO2 cascade with ammonia or something like that. I think with today's technology, that's the most reasonable application in high ambience.
Okay. Okay. You talked about modeling of an ejector. Is it required to consider metastable flow? Because it is going to be non-homogeneous flow condition, because the speed would be very high. Flow speed would be something like a supersonic.
Absolutely. That's a great point. And really, if you look at the two main, let's say, thoughts of ejector modeling, you have kind of the polynomial first base principle camp, and then you have the CFD folks that are working on that as well. CFD is looking at exactly what you just described. There absolutely are instabilities that we don't fully understand, especially because it's very difficult to instrument the internals of an ejector. So you'll have oblique shocks that we can't really predict, right? You're going to have certainly slip ratios, right? The flows won't be at the same velocity between phases. So this is all, many ejector modelers are aware of this, and a lot of the CFD folks have been able to capture that. The idea here is to balance accuracy with computational efficiency, right? How much have those instabilities caused detriment to performance, and how well can we predict them with just polynomials, right? Where the polynomial can say, here's this 10% loss in efficiency may have been due to metastabilities, may have been due to oblique shocks. We're not really sure exactly why, but this has proven to predict this reasonably well at a very low computational cost, right? So more or less, is it good enough for the amount of speed that you want or for the accuracy you're trying to capture? And others are focusing more on the metastabilities that you referred to. But you're exactly right, and that hasn't been fully understood yet.
Okay, thank you very much. I have another question. You talked about introducing a heat exchanger after the gas cooler. Whether that gas cooler is advantageous even for an ejector cycle, because it is going to decrease the ejector input energy.
That's another great question. Yes, so what it's been found is it really depends on the ambient condition. Generally speaking, expansion recovery, to your point, is hurt by having an additional heat exchanger at the outlet. However, once you get into extreme ambient conditions, that begins to reverse a little bit. So for example, the military put out some calls for exceptionally high ambient condition CO2 cycles. And modelers hadn't previously looked at that because, as we discussed in really our first question, only really medium to low ambient conditions have been assessed. But it has been proven that for certain conditions, you can actually benefit the ejector, or you can still have a COP benefit with an internal heat exchanger and an ejector, but it really just depends on the operating conditions. As a rule of thumb, you're right, you shouldn't.
Okay. Thank you very much.
Thank you.
Yeah. Ma'am, is there any other question from audience?
Sir.
Okay. No other question. I want to thank you very much, Riley, for your very informative talk. Thank you very much for your valuable time, because this is early morning to you. And thank you very much. I want to thank Professor Grawl for all his support. Thank you very much. And and I want to thank Professor David also. I want to extend an open invitation to all of you to visit India and especially to our university. Thank you very much. It would be our pleasure to host you.
Thank you very much. Appreciate it.
Thank you very much.
Thank you.
Thank you.
Thank you, sir. Now I am inviting Dr. Vellore to brief about our next speaker. Thank you, ma'am. Good evening, everyone. In behalf of our CO2 Center and VIT University, I would like to invite Professor Sebastian Puig for his international virtual conference. Our sincere thanks to Professor Sebastian Puig for accepting our invitation and also for initiating collaborative work. Professor Sebastian Puig is from Laboratory of Chemical and Environmental Engineering, Institute of Environment, and it's an Institute of Environment from University of Girona, UDG, Spain. Professor graduated in chemistry at UDG in 2002, and he also pursued his PhD there. During his PhD work, he also visited and pursued his research work at Delft University of Technology, Netherlands, under the supervisor of Professor Mark C.M. van Loosdrecht, who is a pioneer in the area of wastewater treatment and resource recovery. Dr. Puig's academic career continued with 2 postdoctoral positions at very good reputed institutes at TU Delft and Catalan Institute for Water Research in the period 2008 to 2010, and a prestigious Vittorio D. Bayones Fellowship. In the year 2010, Dr. Puig was appointed as assistant professor in UDG, Spain. In 2014, he was greeted with a prestigious award entitled Young Talented Researcher in Sustainable Water Management from Cudison Beauty in Spain. In fellowship. In 2019, he was promoted as associate professor at UDG, Spain. He has supervised 4 postdoctoral researchers and 5 doctoral theses, and now 9 are ongoing. He has several international projects and national projects. He is currently PA for 2 H2020 European Horizon projects. One is biological routes for CO2 conversion into chemical building blocks, which is specific to capture and conversion of CO2 and industrial point source into valuable platform chemicals. There is BioRe-CO2 Ever. And there is electricity-driven low-energy chemical input, that is Electria, which are very prestigious projects. And one Swedish is Electrosynthesis, and 2 national projects like Combat and Buffer. He has diversified areas of work. With this introduction, I would like to invite Professor Sebastian Puig to deliver his keynote address.
Okay, thank you very much for this nice introduction. I hope you could see properly my screen.
Yes, sir.
Okay, so first of all, thank you for this kind introduction and also for inviting me to give this talk. I'm really proud to be here in front of you guys. And for me today, I'm going to explain a talk about something that I'm working on it since the last 15 years. That is on bioelectrocarbon dioxide recycling into carbon neutral products. First of all, let me introduce where I'm coming from. I'm coming from Girona. Girona is a small city located in the northeast of Spain. Okay, it's quite close to Barcelona. And our research team is mainly focused on several research lines related to water environments and CO2 environments, let's say. My main expertise is in two main topics: electrobioremediation of polluted water, and the other one is the one that I will talk today, is the electrobio-carbon dioxide recycling to carbon products. The first point that I want to show today is this slide in this photo. Is here in Europe, we have the so-called Fridays for Future. Okay, this is a huge manifestation from several students, as you could see, okay, in which they are claiming against the climate change, and also they are pushing forward all the scientists to go further and to do our best on that. Also, okay, so also in the news, this is in Spanish, but at the end, what it says is that at the end, the solution of carbon dioxide is not to plant more trees. We could not cope with that, so we should find better solutions. We could not sweep under the carpet the carbon dioxide, as sometimes is the case. Our approach is the biological carbon dioxide transformation. And for doing that, we simply we take a look at what it happens in our Earth. Thousands of years ago, okay, we had a reduced atmosphere in which mainly we had hydrogen, carbon monoxide, and carbon dioxide and methane. Under such really reduced conditions, we had a group of archaea called acetogens that are really important population that are capable to go for the gas fermentation bacteria. The mechanism of this CO2 transformation is as you could see in this slide. This is for instance, the basic metabolic pathway and energy conservation of a typical acetogen, that is Clostridium jungali. Clostridium jungali is capable to produce either acids or alcohols from CO2, hydrogen, and CO. It's true that without CO, it's also capable to produce as well these acids. So this is really important. We already have in the nature a microorganism that is capable to take carbon dioxide and transform it into something carbon neutral. That is the main topic of my my talk today. But we should address or overcome several challenges. The first one is that we are limited in hydrogen. Usually the carbon dioxide streams, in general, they are limited in hydrogen. The concentration or percentage of hydrogen is super low in general. Also, the low solubility of carbon dioxide and hydrogen that we could have. We need to solubilize and take it quickly, okay, from the liquid medium, this CO2, and transform it. There are several diverse metabolic routes and products. This is important to highlight because at the end we should aim to produce selectively one product, because at the end then the downstream processes the cost will be reduced clearly. And also in some cases some chemicals are needed for the carbon chain reactions. Our idea, the bioelectrocarbon dioxide recycling, is to provide just carbon dioxide to the system, also renewable electricity, and no chemicals to produce biofuels or carbon neutral products. How we are doing that? We are doing that using microorganisms that we call electrotrophs. I used to say that I'm in love with these microorganisms because they are capable to receive electrons for its growth, okay, and do several reactions. For instance, in terms of water, they could do, for instance, the reduction of nitrates into nitrogen gas, but also in terms of carbon dioxide, they can produce carbon neutral products. Over the last years, my group has been worked really hard on this topic, and the idea is always the same: to provide just carbon dioxide plus green energy, and to have several different products. Here is our portfolio of products. We start with hydrogen, the production of hydrogen from carbon dioxide. Then if you have carbon dioxide plus hydrogen, you could produce, for instance, methane, or you could go for acetate production. You could go even further to produce a C4 compound like butyrate. But this butyrate, in order to produce, you need ethanol, because the reaction is acetate plus ethanol, it goes to butyrate. Also, we could go even further with the production of bioplastics in this case. That this one I will explain briefly later. The point is always the same. We have bacteria that is attached to the one that we call biocathode. In this biocathode, we introduce, or we provide some electrons. And with these electrons, we are capable to produce several reactions. The first thing that we realize is that in our biocathode, we have the so-called compartmentalization, because the population that we have in our biofilm, that is the microorganisms that are attached to the electrode, are different than the one in our bull liquid. This community is completely different, and we have seen that mainly the reaction that is taking place close to the electrode is the production of hydrogen. This hydrogen then is used together with carbon dioxide to go further and to go for the production of acetate and ethanol. So in our case, we always have a hydrogen-mediated bioelectrochemical transformation into carbon neutral products. We use always to compare the work of our bacteria respect to the work, for instance, of electrochemical catalyzers. Here, we made a study in order that we compare, from the one side, the production, the rate of production of hydrogen versus the energy consumption. And the two different, using two different reactors. One, abiotic one, without microorganisms, and the other one, it was we inoculate biomass. As you could see, in terms of efficiency, that the bacteria biocatalyze this reaction of production of hydrogen production more in a more sustainable way than these chemical catalyzers. Are all bacteria capable to produce hydrogen? Not all, and they are producing hydrogen at different levels. Here, just as an example, this is a study that we recently submitted in which we have evaluated several different pure communities, pure cultures. I'm just showing three of them, We have the sulfovitrio, the sulfuricans, also the vulgaris one, and finally the pachyci one. And here we compare the hydrogen production of a pure carbon cloth electrode. Then, when we inoculate with our pure culture, with the first feeding of CO2, and then the second one. As you could see, what we observed is that we had different productions of hydrogen, and the one that worked properly or in a more sustainable way was the sulfovitrio pachyci. This one was considered for us the target pure culture to go further and explore the possibility to have co-cultures for the production of other products. Okay, we are capable to produce hydrogen, but at the same time, we could go further. We need biofuels. And one of the most used biofuel is itself methane. So from carbon dioxide plus hydrogen, it is possible to produce this methane. And here I present the recent study that we are doing in collaboration between the Vellore Institute, AAST, and our institution, Lekia, okay, in which we have different reactions taking place or different reactors. Okay, the first one, a control that at the end is purely anaerobic digester. Then an aerobic digester in which we add electrode material. This is really important because we have observed that maybe the conductive material could play a role in reinforcing the performance of such systems. Also, this conductive material, we could close it electrically to have a closed circuit, and we want to evaluate that. And also, finally, in some cases, it's necessary to provide some extra input to see if it is possible to go further in the production of this methane. So we will, in this study, we evaluated these 4 different situations. This is a nice scheme provided by Professor Belvisi, in which explain factors that we have. Again, control without no electrodes, with electrodes but without potential, when we have electrodes and also we have a closed circuit, and finally, when we have a cathode, okay, in which we provide some input, electricity input. This is just one results that we have that I consider really important in a way that you could see here, all 4 reactors. The one that is the control is the black one. And here we have the methane production, milliliters per day. As you could see here, is the one that is producing less methane. Once we add some electrode material, some conductive material, it seems that the performance increases slightly. So maybe in this case, it could be a situation in which the presence of conductive material stimulate the enrichments of these electrochemical active bacteria that we are using as biocatalysts. The performance of this methane production is even reinforced when we close the circuit. And then if we provide some extra energy, really small amounts, as you could see here in blue, the performance is really enforced, much better. So this study is really important because it explains the idea of the material that is playing a role, how to activate these electrochemical active bacteria, and also the role of the electricity that we are providing to the system. Could we go further in terms of methane production? Yes, we could couple that to even to another reaction. In the biocathodes, we could produce methane, but what about our counter electrode, our anode? In this case, we simply use a titanium MMO electrode, and we start with the production of disinfection byproducts. This was done in collaboration with the company in Spain that is FCC Aqualia, in which you could see here that we are capable to produce 2 different products. One from carbon dioxide, that is the biomethane, and the other one is this chlorine or disinfection byproducts that could be used itself in a wastewater treatment plant. In our study, we made an evaluation of a case scenario in which in a wastewater treatment plant of Aqualia that it has in Catalonia. This is the scheme of process flow diagram of this wastewater treatment plant. And the idea is, okay, you could have anaerobic digestion. Whenever you have the biogas, you could go for the cogeneration, you could go, use it boilers, you could go for the torch, okay? But at the end, you will have some extra amount of CO2 that will be released. Thanks to the technology that Aqualia provided to us, in this scrubber, we were capable to solubilize part of this CO2. And then this CO2 was used in our bioelectrical system. The idea is that in that wastewater treatment plant, in that case scenario, would be capable to promote almost more than 15% the biomethane production, but also reduce the carbon dioxide footprint and the co-production of disinfection byproducts, products that in this case is the chlorine that, as I told you, that is already used in reutilization of water. Methane is an excellent product, but also we could produce other organics from carbon dioxide. This is a proof of concept in which from carbon dioxide and hydrogen, we were capable to produce acetate. But then if you have acetate plus hydrogen, you could produce ethanol. And then if you have acetate plus ethanol, you could go even to butyrate. This was simply a proof of concept that we had. But the idea was to go further. And in this case, okay, we ran several tests in which, okay, the idea was always the same: provide carbon dioxide to the system, produce hydrogen. This hydrogen together with the carbon dioxide go to acetate, with extra amount of hydrogen produce ethanol, and then go to the chain elongation of this for the production of butyrate. This is a really nice story, but at the same time, we need not only to produce it, also we need to purify and concentrate. We did several tests using a liquid membrane extraction, using as a medium, extraction medium, dodecane with dodecanol. And we were capable to have a really concentrated butyrate stream that then could be used directly as a platform chemical for several different products production. As an example, we could have in our biocathode a broth that has, as you could see, 87 millimolar of butyrate and 1/3 of acetate. And thanks to this liquid membrane extraction, we were capable to concentrate and purify this butyrate. What we could do with this butyrate? With this butyrate, we could do the study that we did together with the University degli Studi di Milano in Italy, in which we combined two technologies: our technology, electrical systems, together with another technology that is the bioplastic production. The idea was to provide carbon dioxide to our bioelectrical system, include a separation unit, and then introduce the concentrate to our bioplastic production reactor system. Something that is important to highlight is the carbon balance. At the end, what we have seen is that from 1 kilo of CO2 that we provided to the system as carbon, half of it was transferred to volatile fatty acids. This, together with the good separation concentration step, was provided to that system. And at the end, we had 0.41 kilos of bioplastic. As you could see, the limiting step is in this moment related to the solubilization of this carbon dioxide. And I do agree with previous speakers that introduced the idea of the GDE, gas diffusion electrodes, as the way to solubilize properly this carbon dioxide. The idea is always the same. We have different CO2 feedstocks. We have a system that could be called electrofermentation, microbial electrosynthesis system. We have products that then needs to be purified and concentrate to go to the final products. Always we need to be aware of the social aspects related to this research. Nowadays, what we are trying to target is all these different points that I highlighted here. The first one, the carbon dioxide streams. This carbon dioxide stream is important in a way that what we have seen so far is that we have, for instance, thermophilic streams that has some heat. What we could do with that? Could we use that in a bioelectrical system? This, we tried that in the BioRecover proposal, okay, that is from the European Commission. It's a project that we have, okay, that compares bioelectrical systems together with fermentive or gas fermentation. The idea is to produce lactate or isobutane. As an example of the results that we have in the BioRecover, here we have a thermophilic reactor in which we have 50 degrees around of temperature, together with renewable electricity. Let's see if we are capable to produce some hydrogen and then some acetate. The idea to go further with the high temperature is because could promote reactions rates. We have less risk of contamination, and we are really aiming at product specificity. We did long-term experiments, as you could see, almost 1 year of experiments, 4 different reactors, replicates of the reactors, and we always achieve really interesting productions of acetate. In terms also of titers, but also on production rates. In terms of Coulombic efficiency, that is the amount of electricity that we are providing or electrons that we are providing to the microorganisms, you could see that the microorganisms were capable to use between 80 to 90% of these electrons that we provide. This is a pretty interesting results. But as I can see before, said before, this technology should be coupled with the electricity, renewable electricity. And for this reason, we did an experiment. This is super fresh results that one of my PhD students, Laura, is working on. Okay? And the idea is to see the influence of the renewable supply, electricity supply, okay, in our system. And also in case of you have a surplus of electricity. For instance, in Spain, you have an excess of electricity, of renewable electricity, around 8 hours over the 24. So we did this test, a system that all the time was on. So it means that we provided electricity. 3 weeks without we have this intermittent energy providing electricity. And finally, the last week in which we provided power. What we have seen so far is what I'm presenting here. 2 replicates, and here we have acetate and hydrogen production. Here we have the production, the quantity of acetate that we are capable to produce per unit of electricity that we are providing to the system. As you could see here, the productions using this intermittent electricity, okay, supply, it's much higher than once we have no continuous electricity supply. This is important because it could be linked to the better utilization of this surplus of electricity, and also it means that our bacteria, our community, could be interested, could be related, or we could yes, we need to see if these operational conditions could have an influence on the final performance of such systems. This is really interesting because we already have demonstrated that we are capable to use this carbon dioxide under high temperatures, 50 degrees, also the renewable electricity, but also we need to go further in terms of production. If we look at the thermodynamics, I'm chemist, what we have seen so far, or by doing simple calculations, from carbon dioxide to acetate, we are capable to use ethanol. From ethanol and acetate, we could go to butyrate. From butyrate to butanol with extra hydrogen, we could do that. The point in this case is that ethanol is like a key player that we need always to provide to the system. So we keep focus on that in one of our PhD students, with one of my PhD students, Amiro. This is the work that we recently publishing in chemistry. We are talking about 2 tubular bioelectrical systems. These 2 tubular bioelectrical systems, we provided carbon dioxide, and we monitor the performance. What we observe is that by operating the system under the good conditions, we were capable to have at the same time a ratio of acetate ethanol of 1:1. This is really important because at the end, this could be considered as an excellent broth for further fermentation reactions. Important that we observe that at the end, okay, in order to have selective production, we need to take a look at all our online parameters and all our operational parameters. This is what I'm trying to explain here in this slide. What we have seen so far is that we are capable to control the production of this ethanol by applying the good operational conditions. We could monitor and control the current demand. We could also take a look at the CO2 concentrations, also at the pH of the system, and of course, at the partial pressure of hydrogen that we have. If we apply the current conditions, we are capable to go to this selective production of ethanol. Something that always we are discussing in the community, or in the MED community, or this MED community, is that this technology usually is at a really proof of concept level or in the lab. We need to go further and to move towards upscaling the technology. And this is the idea of a project, European project, that we are proud to be in together with two companies from Spain, Aqualia and FCC Medio Ambiente, in which the idea, okay, is to steer CO2 fermentation with bioelectrical systems. The idea is always we have a bio digester or anaerobic digester, we have this biogas, we have an absorption tower, and then in this absorption tower we have a biomethane, and then the CO2 stream, okay, solubilized with water. The idea is, okay, let's try if our technology is capable to produce these volatile fatty acids that at the end we are talking about acetate or butyrate, and do the chain elongation reactions. In this project, we will test in two different sites our technology. One located in Madrid, and the other one, it will be located in the Czech Republic. This is the scheme of our system. We could have our organic waste. These organic waste, we could produce biogas nicely, but also we have a digestate. With this digestate, we need to treat the water. And with the treated water, together with the biogas, we could have a saturation step in which we could have our upgraded biogas. And then we could have a stream of CO2 saturated water that then is the one that we use in our system to go far. Just to conclude, okay, we could say that carbon recovery could be could become a niche for the microelectrochemical technology platform. The idea is to always to have a zero chemical input technology to minimize as much as possible any intermediates, to go for selectively to selective production of a product. And at this moment, we are talking that the technology is at the technology readers level about 4. So proof of concept already done, and we need to move towards these upscaling microelectrochemical systems. The idea is to do that in the Excalibur project that I recently explained. We need to move, because I have seen a lot of studies that always they use synthetic mediums to real streams. This is a nice example of what I'm trying to explain. Also, to keep in mind the counter electrode, so our bioanode. As already explained, we are capable to produce, for instance, these disinfection byproducts, chlorine. So organics from the one side, from the other side also disinfection products, but it could be other interesting reactions that could take place as well. More research should be done on the design and of the cells. For instance, the previous speakers already explained something of CFD. This could be really important to introduce here. And in terms of material, also to look for conductive material at low cost. This is the point. Last but not least, let me present you the the European meeting of International Society of Microbial Electrochemical Technology that should be in September this year, but we already postponed because of the COVID to next year. So if you are interested and you are a freak of Twitter like me, so you are more than welcome to follow our Twitter account. With last but not least, I would like to thank all my team, okay, located in Girona, and of course all the sponsors and collaborators. This is just a selection, and all of you for your interest. Thank you very much.
Thank you very much, Professor. It was very interesting. You took from basic to technology level. And I'm also thanks for accepting our collaborative work. And we are on the path. We have got it. Maybe in a couple of works we will still extend and we will go through it. So I'll just go through some few questions like regarding bioplastic. Bioplastic. Yes, like actually we also worked, but how fast the growth was, because we are not going to give oxygen here. So what was challenging in bioplastic?
The limiting factor was itself the bioelectrical system. So the performance, because the solubilization of CO2 is one of the key points. Okay. In terms of the growth of this bioplastic, that in our case we introduce acetate and butyrate to our system. Okay. We have a growth period or startup period of this bioplastic production bacteria, microorganisms, that it took us a couple of 3 weeks, and then we start to apply fast farming conditions in order to reinforce the production of these bioplastics.
Thank you. And another thing is like regarding mass balance. Yep. Like if it is of like a normal COD, then we are able to, okay, whatever waste we convert into in terms of COD and fine. But when it comes to CO2, we found a little bit tricky, like whether it comes, you already told that depends upon the solubility and so many factors. Like what else should we really consider more like to make it a very typical mass balance?
This is an excellent question. It's difficult because I'm also used to refer everything to the chemical oxygen demand. But in our case with carbon dioxide is another story. And we are lucky to have CO2 sensors that make us liquid CO2 sensors and also we use to analyze also the gas phase. So then the situation is more difficult in this case because you could have CO2 leaks, okay, that are not controlled at all. Also, you could have some solubilization of this CO2 into bicarbonate. Okay, we are also monitoring bicarbonate as well. But yeah, just it's a really, I would say, it's the tricky part. And but I think it's worth it to show these values because at the end, the people think that from 1 kilo of carbon dioxide, we could provide 1 kilo of a product, and it's not the story at all.
Yeah.
But for instance, I do agree with some of the previous speakers explaining the solubilization, using, for instance, gas diffusion electrodes. This could give a chance. But at the end, in terms of carbon dioxide balance, you need instrumentation. And in this case, it's related to the sensor for CO2 and also gas analysis.
Yeah. Another one, like regarding industrial projects. Yeah. Whenever so at the ultimate aim is like we are planning for industrial gas with whatever CO2 mixed gases. Like how far we could succeed in that when we go for industrial gases?
We have a couple of projects that we are dealing with that. Okay, the first one is the biorecover. Okay, in the biorecover, we are using CO2 streams from cement and steel industry. Okay, and something that is really important is that when we characterize these gas streams, they have a lot of oxygen, some of them. So we should get rid of that. There are several technologies that they are capable to deal with that. Okay, but it's something that still more should be done on that. And generally what we have is like carbon dioxide, some H2S, okay, but then with discovery is something that we could deal with that. But at the end, the key point is to get rid of oxygen. It's true that in some industrial streams, we have seen that almost no oxygen content, okay? So we are talking about less than 3% of oxygen content, okay, in the CO2, and also in some of them, also hydrogen or carbon monoxide. These are really good key players in the transformation. And industries are really interested because, as I told you, the European project that we have together with a company in Spain, Aqualia, that is Excalibur, the idea is to use the CO2, the biogas from the wastewater treatment plant itself. So this is making a, we are in the way. We are still not there, but we are working hard for reaching this milestone.
Okay. I'll just see a few more in chat. Like I've seen that in electrotropes, they were asking whether you are using the pure culture.
We are using pure culture. We are using an enriched population, and we are now also using genetic modified organisms. Okay. The pure culture we are using because we are interested in having to build a co-culture. Okay. For one that produce hydrogen and the other one that it use this hydrogen to produce something else. So, and this is a genetic modified organism. So we need to have a really specific conditions. I'm really into the enriched populations because they are really resilient, okay, and resistant to oxygen, for instance. And in terms, whenever you have an industrial CO2 stream, then with some oxygen, they could cope with that. And the answer is that we are using both. It depends clearly on the niche of application.
Okay. What is the scalability, sir? What is the scalability now you have planned for your scale-up reactor, like volume of the reactor?
In our volume of reactor, we are talking about already about 10 liters scale, more or less.
Good.
And
that's good.
Yes, it's really challenging. We are stubborn on that. It's running in Madrid on the Excalibur project, and I'm really confident that soon we could show you some nice results. But for us, it's already a big jump because we are moving from milliliters scale to liters scale. So this is really the challenging, and we are really into that.
Okay. Thank you so much, Professor. It was very interesting, and in spite of your busy schedule, you accepted and you have also included our collaborative work. I'm so happy that you have come and presented all the way. And so we are very happy. And in behalf of our management and CO2 Center, we thank you so much. Thank you so much.
Thank you to you. Really nice.
Yeah,
and it's a pleasure to be here and also to collaborate with your group. See you.
Yeah. Thank you, sir. Thank you. Bye.
Thank you very much, Professor. Okay. Now I would like to invite Dr. Ranjitha to brief about our next speaker.
Next, today's session is Dr. Ranjitha. He is Executive Director of the Team for Research and Capital.
Mute.
Hello. Sorry, sir. Okay. So the next speaker is Dr. Nalim. He is Executive Associate Dean for Research and Graduate Program at Purdue University School of Engineering and Technology, United States of America. He has 30 years of experience in higher education and professional practice with respect to industry, academia, and government. He also working at NASA Research Center and Purdue University. He has initiated novel concept for pressure gain combustion engine and non-steady flow pressure power generation engines. He has 7 international patents and over 100 publications, and supported by over $10 million in grants from NASA, US National Science Foundation, and other sponsors. He has received several awards and honors, and highest honors of his school for research and service. He has conducted several workshops and conferences on project enhanced active learning and engineering education supported by NSF. Now I'm glad to invite Dr. Nalim sir to give us invited talk on hydrogen economy. Sir, please proceed, sir. Hello.
Good evening.
Yes, sir.
Can you hear me?
Yes, sir. Yes, sir.
Very good. So I'm delighted. Thank you very much for your kind introduction. I'm delighted to join today the conference. I had the great privilege of spending several months at VIT in 2018 and early part of 2019 as a visiting professor in the Fulbright program. So I'm really delighted to continue the association through this conference and perhaps others in the future. So I will attempt to share my screen now, which I believe I can do that. Okay. Are you able to see my screen?
Yes, sir. Yes, sir.
With the university name, very good. So I'm speaking from Indiana University, Purdue University in Indianapolis, and my talk today is going to be on clean pathways from fossil fuels to the hydrogen carbon economy, and I'll explain what I mean by the hydrogen carbon economy. Briefly, my lab here is called the Combustion and Propulsion Research Lab, where we are doing a variety of different research projects, primarily in some non-traditional combustion systems with sponsorship from a number of different organizations, including NASA, including Rolls-Royce here in Indianapolis, and other organizations. The research I'm talking about today is actually a new direction for us, but I will briefly mention my research on pressure gain wave rotor combustion, because there is a relationship to this topic that I'm speaking on today. But really the topic I want to speak on today is one that I hope will be of interest to the CO2 research center and the interest that you have. But I want to really focus on carbon itself. So carbon, is an amazing compound. I'm sorry, not a compound, but an element rather. So carbon is the most versatile element of all that we know, because it forms millions of compounds, organic compounds, and together with water, it enables life here on Earth. What I want to argue today is that we really should value carbon so much that we should not be burning it. Even though I'm a combustion person, and I have done a lot of work in different ways of burning carbon and hydrocarbons, I believe that we really should stop burning it and use it for more valuable products. And I will focus on just what I think is the most high value currently, but the general idea is that we want to try to use this very valuable element more wisely. So carbon, is not only too valuable to oxidize, it's also too dangerous to oxidize, as we see whether it's carbon monoxide, which is a toxin, but carbon dioxide, which creates a greenhouse effect and really has a huge problem now for us to solve. If you think about the typical hydrocarbons that we are burning more and more now, it's more and more oil and gas, less of the coal. But the oil and gas that we burn is still a lot of carbon dioxide as well. In the US in particular, there is abundant gaseous fuel, natural gas and shale gas. And so if you look at those gaseous fuels like methane and ethane, about half of the energy content comes from the hydrogen and about half from carbon, roughly speaking. So if you could somehow separate the hydrogen and the carbon, roughly you will still have about 50% of the energy available in the form of hydrogen, ideally speaking, and you could burn the hydrogen and it's harmless in terms of the emissions, it's just water. but you would get roughly about 50% of the energy. Now that seems like you're losing a lot, but really the other part of it, which is the carbon, you can actually get more value by keeping it as carbon rather than oxidizing it to carbon dioxide. And that's what I'd like to focus on, so that you really are not losing by giving up the other 50% of the energy. So for example, if you go down to the molecular level, nanoscale carbon is amazing in terms of the different structures that you can get. I won't go into the details of the chemistry, but you've probably heard about the various allotropes of carbon that are being investigated today, from carbon nanotubes to graphene and so on. Of course, these are on a very small scale. So even though these are very high value, the scale is tiny compared to the scale of carbon dioxide that we generate by burning hydrocarbon fuels and other carbon. But it's still interesting to see the amazing properties of carbon at, in a really very ordered form at the nanoscale. So multi-walled carbon nanotubes, for example, have the highest tensile strength of any material. And even carbon nanotubes that are being produced now have been shown to have 1,000 times the tensile specific strength of low carbon steel. And people are still looking at theoretical models for what are the ultimate properties of these materials in the form of very highly ordered structures, of course, like carbon nanotubes and graphene. The other thing that's interesting to look at is that the cost of elemental forms of carbon, not other compounds of carbon, but elemental carbon, varies by a factor of 10 to the power 9 in the different forms that we use carbon, from coal to graphite to carbon black to carbon fiber, graphene, and all the way to diamond, which is about the most expensive form of carbon. But let's leave diamond aside because it's used in very tiny quantities. If it was highly available, it wouldn't be so valuable, right? So but let's just look at all the other forms of carbon and see whether does it make sense to convert carbon in high volumes, not in tiny amounts, but in high volumes, to useful products, and which of those would it be? So the key thing to keep in mind is that once you oxidize carbon to carbon dioxide, it has no useful energy content, right? Like water has no useful energy content. So essentially, the useful energy content of water and carbon dioxide is 0. But methane, which is the most abundant hydrocarbon that we have, is close to 890 kilojoules for 1 mole in terms of energy value. If you split it into carbon and hydrogen, it's slightly more, but it's say about the same. But then if you then take the carbon away and you still have all the hydrogen, it would be a little more than half the value of energy, as I said, still there. Now, if you burn it and you form carbon dioxide and you want to try to do something with it, you have to put energy back in. And I respect all of the research that many of you are doing, but you really have to make the argument that why put the energy into carbon dioxide to make something with it, rather than use that energy directly for some useful purpose. So it seems to me that it's always better to stop creating the carbon dioxide in the first place, rather than trying to do something with it after you've made it. Because the whole point, the reason we're making so much carbon dioxide is just to get the energy from it, right? So putting that energy back in, just, it doesn't come. Cycling that process is going to involve more and more losses as you keep doing that. So the question is, can we make carbon valuable as a material, and what would be the forms of it? And particularly, I'd like to focus on carbon fiber. But before I do that, I also want to talk a little bit about how can we use the hydrogen as a fuel. And of course, there's a lot of research that's been done for the use of hydrogen in many different ways as a fuel source. For example, fuel cells and so on, but then you need very pure hydrogen. But what if you had hydrogen-rich fuels that still had a lot of other hydrocarbon content in it? Well, you can still use that in combustion engines, the large amounts of hydrocarbons are burned in gas turbine engines and internal combustion engines. And you could still do that, but there's a difference between those two different types of engines. Gas turbine engines operate on approximately a constant pressure, free expansion process, and it's not easy to stabilize hydrogen fuel in those situations. Plus, it also has an inherent thermodynamic loss versus, on the other hand, the ideally constant volume combustion process in a piston engine, as well as in new engines that we are working on in my lab, would have the benefit of not only better capture of the available energy, but it can also burn hydrogen or hydrogen-rich fuels reliably. In particular, we're working on something called a wave rotor constant volume combustor for gas turbine engines. I won't have time to go into that, but it has an internal combustion process that's similar to a piston engine, but it looks totally different, and it's much more compact and high throughput combustion system. And we would be able to use hydrogen-rich fuels very easily in this system. So to move back to the story of carbon fiber and carbon products, so the chart I showed you earlier, now I'm showing again slightly differently, showing the amount of consumption of these different forms of elemental carbon. Coal, of course, is huge. It's 7 billion metric tons of carbon that's consumed in the form of coal. But if you look at the other things that are of high volume, carbon black, natural graphite, and carbon fiber are relatively high volume compared to the other forms of carbon. Carbon fiber in particular, the volume of use of carbon fiber is growing very rapidly. And that's one that I'd like to focus on today to see how could we decrease the cost of carbon fiber, which is 1,000 times the cost of coal, and increase the production of carbon fiber. Excuse me. So if you look at the different ways in which carbon fiber is used, about a quarter of it is used in wind turbines actually these days. Another significant amount is used in aerospace, in aircraft, and then some in pressure vessels and automobiles. And then there's the other half of it is in various other consumer products, medical, recreational products, and so on. We'll talk about the different ways in which carbon fiber is made, but what we want to look at is the potential for using ethylene from ethane as the fuel source, or the feedstock rather, for carbon fiber. So carbon fiber, as I mentioned, among the other benefits of carbon in this form, the very high stiffness and lightweight and high tensile specific strength, corrosion and temperature resistance being quite good, and some very important properties that are being taken advantage of. But it's expensive compared to other structural materials. So it's used for aircraft, it's used for wind turbines. If you look at a 787 Dreamliner and compare it with the previous generation of a similar size aircraft, like the 767, about half of the weight of the 767 has been replaced, instead of metal being replaced with carbon fiber. So we're already flying this aircraft, and there are even all carbons in terms of structure, all carbon fiber aircraft that have been built and flown as well. And wind turbines, of course, the blades of a wind turbine are very similar to airplane wings. And so those are now almost all the large scale ones are made of carbon fiber as the structural material. In automobiles, they're used in very high value vehicles right now because it's expensive. But if we could bring the price of carbon fiber down, we could be using it in all automobiles that are built today and replace the metal that's used in automobiles. And that becomes a very large scale proposition. And that's, I think, where perhaps there's going to be the greatest impact in terms of using carbon as a high value product derived from the major sources of carbon today, which are still fossil fuels. If you want to scale up to this level, that's really the idea, is that we can divert that carbon. The demand for carbon fiber, as I said, has been growing rapidly, particularly since commercial aircraft like the 787 and the Airbus 380 and 350 started using a lot of carbon fiber. The rate of use has gone up substantially since the time before that. So let's look a little bit deeper into carbon fiber, where if you look at it, you know, under a microscope, you'll see that there are fibers of a diameter of 5 to 10 micrometers, and they are made of crystalline structures that are roughly aligned with the long axis of the fiber. And so if you look at it, you know, even deeper, ultimately those are formed of graphitic sheets at the micro scale, which are roughly aligned with the fiber axis, not perfectly, but roughly aligned with the fiber axis. But they're not like carbon nanotubes that are very highly ordered. There's a great amount of ordering, but there's, you know, still not that kind of perfection in ordering. So the properties are not the same as carbon nanotubes. They're still extremely good for structural use. If you look at the different types of applications, the aerospace applications have a need for very high tensile modulus and very high tensile strength. But if you look at the automotive applications, those actually are not as demanding. And so the question might be that if you want to go to very high scale production for automotive use in particular and other similar uses of carbon fiber, would it be possible to use a process that is less expensive, may not have the same level of tensile properties as the current aerospace grade carbon fiber, which is made of a precursor called polyacrylonitrile, which we'll go into momentarily. So the precursors are really the key for the use of the properties that you get from the carbon fiber. The most widely used today are fiber from polyacrylonitrile, which is from petroleum, ultimately mostly from petroleum products. What we want to think about is the use of polyethylene as the precursor polymer, which is much cheaper than polyacrylonitrile. I'm having a little trouble with my slides. If you would excuse me. Okay. So as I was saying, the PAN or polyacrylonitrile is the most common and high quality fiber that is currently used for aerospace grade carbon fiber, for example. So we want to look closely at one of the possibilities for very high volume production at a much lower cost. And so we're going to focus on polyethylene, which is a low cost commodity polymer. And there may be others, but that's the one we want to talk about today. If you look at the current process, there's a number of steps in going from the precursor, which is polyacrylonitrile, to carbon fiber. There's the solution spinning process, which actually it uses a lot of energy. Then there's the stabilization and carbonization processes, and then there's some after treatment. And the PAN accounts for 50 to 65% of the carbon fiber cost because of the commodity price of PAN and the solution spinning process in particular. And there's some amount of CO2 that's generated in this process. And so part of the challenge is to minimize CO2 production as well from whichever process we use. If you look at the alternatives, polyethylene is a significant opportunity. There are others as well. Polyethylene has some benefits of having high carbon yield and relatively high tensile properties, but it might involve some larger capital cost and special processes that still have to be refined and researched. There's also efforts being done to improve the current processes by modifying them in different ways, and I won't go into that in a lot of detail, but there's research on that as well. And as I said, the properties that you get with alternatives to PAN are not as good as PAN in terms of tensile strength in particular, but they might be acceptable for different applications. The key interest currently, at least from the US perspective, is to use ethane from shale gas to make ethylene, which is already happening on a very large scale. And ethylene is routinely converted to polyethylene to create polyethylene plastics, LDPE, HDPE, and so on. And there's research now on use of polyethylene to carbon fiber. We're not doing all of this research in my lab. What we're doing is really trying to take a high-level thermodynamic view to assess the energy use and the carbon dioxide emissions from the entire life cycle of this proposed new process, so that we can see that whether it is justified to promote this as a way to sequester carbon and have a pathway to high-value products from carbon and what I call the carbon hydrogen economy of the future. So we're focusing on all of the steps, the ethane to ethylene process, which is well known, so I won't go into that. The ethylene to polyethylene process, well, we'll go into each of those, but very briefly, and then the polyethylene to carbon fiber. So ethylene production primarily comes from the steam cracking of hydrocarbon feedstocks. As I said, in the US, it is primarily ethane. In other countries, it may be naphtha and other feedstocks. But because of the availability of ethane from shale gas now, there's a two-step process of first processing the shale gas to separate the ethane and propane primarily, and then the ethane and propane then go into a olefin production process, which is usually a steam co-cracking process, and that's well established now. And what we're trying to do is assess the energy use and carbon dioxide emissions very carefully for this step and the other steps in the process. And if you look at the overall energy intensity of the PAN-based process versus the polyethylene process, speaking, add up all the different contributions, not only the on-site, but also the off-site power and energy use from electricity, steam, and so on. Overall, for PAN, we're talking about 870 gigajoules per ton of carbon fiber. And it's been estimated that the energy use can be reduced with some new technologies with using PAN as a precursor to maybe 600 or somewhat over 600 gigajoules per ton. But with polyolefins, polyethylene in particular, the energy cost, the overall energy intensity can be much less. It could be less than 200 gigajoules per ton of carbon fiber. So there's a substantial opportunity, not only for diverting the carbon into a high-value form of carbon rather than burning it, but also actually having a very low energy intensity in that final carbon fiber that's created in comparison with the current methods. Just briefly talk about the different fabrication processes involved. The precursor processing step is different. The stabilization steps are different. So because it's a different polymer, polyethylene has a process of polymerization and melt spinning rather than wet spinning. There's a wet stabilization process, which is somewhat tedious, and it's just has not been given enough attention to scale up. But there is a lot of research going on, and I'm sure those problems will be solved. There is a sulfonation process in particular as part of that to create the cross-linking that's required to have good properties of the carbon fiber. The carbonization then has to be done at a lower temperature. And then the post-treatment is fairly similar. But overall, the cost is substantially lowered. So currently, we're looking at about $25 per kilogram for carbon fiber from PAN, and it's estimated that you could bring that down close to $15 a kilogram for polyethylene-based carbon fiber, which is very substantial. And if that is scaled up to the volumes that are required for, let's say, automotive use or structural use, and maybe other structural uses, maybe buildings and so on, for tensile strength, where tensile strength is required, that price point potentially could be lowered even further, because the volumes would be much, much larger than what is currently used in terms of carbon fiber, which would enable the greater volume of use, and which would have the higher impact on the global use of carbon overall, and potentially avoid the combustion of carbon into carbon dioxide. So there are still some challenges. As I mentioned, the sulfonation process has to be done very carefully to deal with environmental regulations in particular. And the properties are not as good as pan-based, but there's a lot of scope for research for improving the properties once we have a fundamental understanding of the effect or the impact of the different processing on the properties. I think I'll skip some of this so that we have time for questions. There's research being done on the different types of polyethylene precursors. In particular, there's the use of some additives in the process, and different options for stabilization, and how that affects the tensile modulus and the tensile strength is being researched currently. So it's not a single answer of polyethylene that you use. There may be even potential for recycling of plastics, for example, into carbon fiber in the future, which is not really being researched very much, but that's another potential area of research. In the US, Oak Ridge National Labs is doing significant amount of research on carbon fiber technology, not only not mainly on improving the current pan-based processes. At Penn State University, there's a project going on the use of polyolefin precursors for pressure vessel applications, where there's a big demand for storage of gaseous fuels in very lightweight pressure vessels, particularly in vehicles. So that's an area of interest as well. So to conclude, carbon fiber products are revolutionizing already aircraft design and wind turbines, and have the potential for lightweight, very high volume use in automobiles and many other applications. So this potential for use of carbon fiber throughout throughout the world in built infrastructure, in vehicles, and so on, is something I believe is worth continuing research on as a way of addressing not only the properties, use of the amazing properties of carbon, but also reducing the amount of carbon dioxide that's generated. And eventually, there might be ways of really going into more perfectly ordered single crystals of carbon, like carbon nanotubes and graphene, to be scaled up from the nanoscale to macroscopic structures. That would be further into the future compared to the carbon fiber work that I've mostly talked about. That's currently, of course, those applications are very small scale, so they're not going to have any significant impact in terms of carbon dioxide. But it's still all a part of having better understanding of the properties of carbon so that they could be applied to all of these opportunities. The use of polyethylene appears to be the best pathway currently, particularly if there is there continues to be the availability of low-cost commodity polyethylene from different sources. In the US, it's now primarily from ethane from shale gas. So here, I think there's an opportunity to take advantage of that low cost availability of feedstock. We do need to focus on looking at the embodied energy throughout the life cycle, throughout the supply chain or the chain of operations that are needed to produce carbon fiber from polyethylene and from ethane, to ensure that we can optimize those systems to minimize energy use and minimize carbon dioxide emissions. And so I really want to close with a challenge to all of us, scientists and engineers, particularly those with a chemical science and engineering background, to see how we could use commodity polymers like ethylene to make carbon fibers and revolutionize the manufacturing of many products that could use carbon instead of steel or aluminum, which are very high energy embodied energy products. And so potentially we could have very low embodied energy in carbon fiber and in the process have lightweight, low cost, immensely strong structural materials, and help create these more or less permanent objects that do not then allow that carbon to go into the atmosphere and the oceans. I'll be happy to take your questions.
Hello.
Hello, yes.
Yes, sir. I have one question, sir. What type of carbon filters are used in aerospace, sir?
So carbon fibers, in aerospace structures, so if you look at the 787 aircraft, for example, all of the structural parts of this, the wing, the fuselage, so the wing obviously has to be very strong. So if we look at the cross-section of a wind turbine blade, that's very similar to an aircraft wing. So you see this, this rectangular structure inside. That's a structural carbon fiber product. So that's a very long beam, essentially, right? So the aircraft wing similarly has those kinds of beam-like structures that are made of carbon fiber and composites that are primarily carbon fiber. So that's one of the major use. And if you look at the fuselage of the aircraft, the main body of the aircraft, that's essentially a pressure vessel, right? Because the aircraft is pressurized as it flies. And so you have a cylindrical shape like a pipe. That requires the ability to have high tensile loading of that circular structure that is used to make up the body or the fuselage of the aircraft. Similarly, when it comes to other applications, the carbon fibers are used at locations where you have high tensile loading.
Sir, whether we can use any kind of sulfonated polymer, sir?
I don't have a slide that goes into the details of the process. The sulfonation is really used to create cross-linking between the main polymer chain. I don't know if your question is regarding the reason for the sulfonation process, or
Yes, sir.
is that
Yes,
your
sir.
question?
Actually, you had explained we use that polyethylene and polypropylene material as a polymer precursor. Whether we can use sulfonated polymer, sir, polymer based.
I see, sulfonated polymer. That's a good question. I don't know. I'm not very familiar with approaches that have been taken. The thing is, the polyethylene itself is in its common forms, LDPE, HDPE. These are low cost available polymers, right? So you would normally, that's what you would, industrially, you would have available to you. And so from there on, then you have to create the process, within a particular commercial entity, they would have to create that process. So typically the process that has been discussed involves some steps for treating the fiber, the polymer, and then the sulfonation process to create the cross-linking, and then the carbonization process, and finally the fiber. So I think there might be some interesting polymers that you could create, but what would be the cost of those would be the question that industrially you would need to look at, because the commonly available forms of polyethylene are that's the most widely used plastic in the world. You can source it from almost anywhere, wherever the cost is low. So the wide availability and low cost, I think, would drive generally most commercial processes to want to start with those widely available forms of olefin polymers.
So thank you so much, sir. Thank you so much for your informative talk on hydrogen carbon, sir. Once again,
Certainly.
on behalf of CO2 Center, my sincere thanks to you, sir. Thank you, sir.
Very good. Thank you. It's really my pleasure. Appreciate the opportunity very much.
Yeah, Professor Nalim, I would like to join my colleague, Dr. Ranjitha. Thank you very much. It was my pleasure to listen to you. It was in a completely different perspective you put forth. Really, I enjoyed your talk. Thank you very much. And also, You have been a well-wisher of V8 University. You have been helping V8 University in a different ways, and I appreciate that. Thank you very much. Yeah, thank you.
I enjoyed the opportunity very much. Thank you.
Thank you, sir.
Bye.
So next session, I'd like to call Dr. Vijayalakshmi Madam to brief about the next speaker of the session.
Thank you, ma'am. It's my great privilege to introduce Dr. A.M. Kannan, Professor. Dr. A.M. Kannan is a full professor and graduate engineering program chair at School of Engineering, Arizona State University. He received his PhD in electrochemistry from Indian Institute of Science, Bangalore in the year 1990 and MS in chemistry from Madurai Kamaraj University in the year 1985. He comes along with rich academic and industry experience. Prior joining to Arizona State University, he served in reputed organization as a scientist. He did his postdoctorate at University of Texas, USA, and served as a chief scientist in Hoku Scientific, USA. Dr. Kannan also received 8 US patents in fuel cells and batteries. He has authored several research papers in reputed journals, also a recipient of many honors. To name a few, Best Employee Award in Excite Battery Limited, Dean's Award for Faculty Excellence in Scholarly and Creative Activities, ASU and Fulbright Distinguished Chair Award. His current research interest includes lithium-ion batteries, fuel cells, and photoelectrochemical water splitting. Over to you, sir.
Oh, thank you, Dr. Vijayalakshmi. So, can you see my screen?
Yes, sir. Yes, sir.
Okay, thank you. So, I'm going to probably briefly make some introduction to hydrogen economy and how hydrogen and the fuel cell could play a major role in meeting the decarbonization of the global energy scenario. So, thank you for the opportunity to talk on these aspects. I'm sure I think all the participants had been listening to a lot of talks related to CO2 and also how we can mitigate. So if you look at this slide, all our human activities are actually adding more than 70 million tons of CO2 into the atmosphere every day. And certainly, global warming and greenhouse gas emissions very serious issue for all of our human population, and certainly we want to protect, and also we want to keep that for our future generations. So this happens, mainly because of various activities, also man-made activities related to respiration or transportation, decomposition, deforestation, industries, and also residential or other industries. So overall, if you look at these numbers, this is mind-boggling. Almost 20 billion metric tons of CO2 is the net gain per year in the whole world. So, we need to somehow, make a control, or probably we make it to negative CO2. So in this context, I thought, hydrogen economy would make a good case in terms of, decarbonization and also reducing the global greenhouse emissions. So when we talk about hydrogen economy is nothing but, using hydrogen as an energy carrier in the place of hydrocarbon fuel, like any fossil fuel, in terms of meeting the requirements in the stationary power, transportation, industrial, residential, and also other commercial sectors. So certainly hydrogen is the most simplest known element to mankind or humankind. So hydrogen is obviously the most abundant element in the earth, but unfortunately it does not occur alone, or it doesn't occur naturally as an individual gas. So certainly because of its activity, it's always combined, it's available as a combined material with other elements such as oxygen if you consider water. So certainly, if we separate hydrogen from these other elements from the compounds, hydrogen can be used effectively in a fuel cell, or you can use it in a compression process to make electricity, or direct conversion into electricity. So certainly, the hydrogen is the only truly chemical or cleaner chemical fuel which we have right now. So why do we look at the hydrogen? So certainly, I mean, there are some advantages compared to fossil fuel. So certainly, I mean, hydrogen gas is highly comparable with the high efficiency fuel cells, where hydrogen can electrochemically react with oxygen from the atmospheric air to produce water as a byproduct, and in the process it could produce electricity and also heat. And hydrogen can also be effectively used in a combustion engine or the reciprocating engines for producing power with near zero emissions of certain pollutants like carbon and nitrogen and sulfur oxides. So when the hydrogen is being used in these devices, it could produce just zero amounts of greenhouse gases, specifically carbon-di-oxide oxides. And that is very true in the whole round trip scenario if we produce also hydrogen from renewable or nuclear sources. But if you produce hydrogen from fossil fuels like natural gas, we certainly need to look at carbon sequestration to minimize the CO2 emission. Currently, hydrogen could serve in all the sectors, specifically in the transportation, power generation in large scale, industrial, and also other buildings or residential structures. So hydrogen could also, certainly it is a fuel, but it also has a direct link with how it could reduce the carbon dioxide emissions. So, as we all know, the transportation of, people, especially vehicles and goods or services, is one of the major sources for CO2 emissions worldwide. And specifically, if you use fuel, hydrogen-based fuel cell vehicles, that could certainly reduce the carbon dioxide emissions really significantly, especially if you, again, as I said, if you produce the hydrogen from renewable means, or if you produce the hydrogen from fossil fuel in conjunction with CCS or carbon capture and sequestration and storage. So this slide is very important in terms of motivating the researchers and industries around the world, mainly because of the fact that hydrogen shows almost 3 times energy density, that's weight-based compared to that with the fossil fuels, mainly diesel and other hydrocarbon equivalents. So if you look at these numbers here, so gasoline only has about 13,500, whereas hydrogen, based on the weight, shows almost 39,000. But unfortunately, if you use the hydrogen at lower pressure, suddenly it's going to give you extremely low energy density based on the volume. That's from the lowest density of hydrogen gas. It's only about 0.09 kilogram per meter cube. But because of this extremely lower density, hydrogen also has an advantage of escaping to the atmosphere in case there's a leak or in case there's any catastrophe associated with the stored hydrogen in high pressure. So there's no issue with the safety aspect because of the lower density of the hydrogen gas. So in other words, among all the known fuels, hydrogen is the one with the highest gravimetric energy density values. So in fact, we recently did a series of papers in the International Journal of Hydrogen Energy, mainly on how hydrogen economy can become realizable in the foreseeable future. So, all these slides are actually from that particular 3 sets of papers. So if you look at this, this is the whole hydrogen economy, meaning you produce hydrogen from various means. We'll also see what are the different methods to produce hydrogen effectively. And once you produce, the hydrogen is not going to be used in the same place where you produce. So the hydrogen needs to be stored, especially if you use, renewable energy sources like solar and wind. We need to store the hydrogen and transport it to the actual place of use, and then, use it in the devices where it could operate automobiles, trains, or any other transportation or any other purpose associated with any industries. So in other words, production is very important. How we store hydrogen once it is produced, because it needs to be transported to other places, and also to use the hydrogen during time where you don't have access to the renewable energy source. Once you store, then you need to actually distribute and also convert it into electrical energy for various applications given here. So the hydrogen can be certainly utilized, as we just learned. So hydrogen can be produced from natural gas or from coal by coal gasification, and also by renewable resources, or certainly from the nuclear energy produced through electrolysis. And the hydrogen, because it's a pure fuel, that could be used in hydrogen fuel cells or internal combustion engines or gas turbines, or it could also be used as an energy storage device in various other electrochemical devices. In addition, it can also be a feedstock in petrochemical industries, and also for methanol production. Applications can also be in the electronics industry, and certainly ammonia production. And iron actually is one of the major element for humankind. So hydrogen can also be used in the metal production process industry, food processing industry, and also in cosmetics. So hydrogen production methods certainly can be used with fossil fuels. So when you produce a hydrogen from fossil fuel, say like a methane or maybe even gasoline, that hydrogen is actually called gray hydrogen. So if you produce a hydrogen from biomass, that's a blue hydrogen. But if you produce, say, by electrolysis and also by using electricity generator from renewable resources, that's a greener hydrogen. So hydrogen can be, gray, or blue, or green, depending on what the starting material is or what the process is. Certainly, if you look at the green hydrogen, it does not involve any of the carbon footprint. So CO2 emission, throughout the process is kept at its minimum. So in the greener hydrogen production method, it can be electrolysis or thermolysis or photoelectrolysis. In the biomass-based products, you can make hydrogen by partial oxidation or autothermal reforming. Whereas in using fossil fuels, you could use hydrocarbon pyrolysis or hydrocarbon reforming, like steam methane reforming. And in the steam methane reforming, you can still have 3 different methods to produce hydrogen, like steam reforming, partial oxidation, or autothermal reforming. So this slide also gives you a little bit more details along with the timelines. So if you look at say 2015 to 20, so the circle size shows you the amount of hydrogen that's produced per day. That's or you can say plant capacity. And this triangle in red, it's about 1,500 kilogram hydrogen production capacity per day. So if you look at 2021 to 25, it's mostly again, small scale and also, electrolysis and, by electricity produced from wind turbines and also from biogas and gasification. So after 5 years, things are going to suddenly take a huge turn in terms of how we produce hydrogen for various applications, like gas, coal gasification with the carbon capture and storage, electrolysis, high temperature electrolysis. Photoelectrochemical water splitting is one of the key because it's fully involved with renewable energy sources, and also STCH, that's a solar thermochemical way of producing hydrogen, and also photobiological. If you wonder, how much would be the cost of hydrogen if it is produced by electrolysis, if it is a hydrogen generation from alkaline electrolyzer with a plant capacity of about 3,800 kilogram or 380,000 kilogram of hydrogen per year, with a system efficiency of about, say, 73, that could lead to $3.2 per kilogram. So when we talk about per kilogram of hydrogen, it is almost the same as 1 gallon of gasoline. So 1 gallon is almost the same as 1 kilogram of hydrogen in terms of energy consumption. So you can actually compare the energy cost or the fuel cost of hydrogen with that of the gasoline. So that's a 3.68 liters in 1 gallon. So, carbon dioxide emission through this process is also very important. So this slide gives you the carbon dioxide emission in the process to produce 1 kilogram of hydrogen. So if you look at the one at the right end, which says steam methane reforming without the carbon capture and sequestration, that's again about 13 kilogram hydrogen, 13 kilogram carbon dioxide being emitted when you produce 1 kilogram of hydrogen. So it's basically, you try to, pollute in another place and then, try to use the hydrogen in a place where we have the human habitation. But otherwise, if you look at the slide or the figure on the left side, so photofermentation or wind electrolysis or thermolysis, photoelectrolysis or solar PV. So the CO2 emitted is extremely low to produce the hydrogen. But again, if you look at the cost benefit for producing hydrogen with steam methane reforming or from the natural gas, you could actually reach about $2.27 or almost $2 if you do the steam methane reforming without or if you do the CCS, it's about 2.27. And if you don't capture the CO2, then the cost is actually lower. So you can have 2.08. But when the hydrogen is being produced in large scale, you could also suddenly do the carbon capturing, and then price is still under control. So storage certainly is a major part of the whole hydrogen economy cycle. So hydrogen can be stored, compressed form up to say 700 bar or 70 pascal, or hydrogen can also be stored in liquid form. That's certainly done at minus 253 degrees Celsius. So one of the major benefit is that when you store hydrogen, you can actually have huge amount of hydrogen in smaller volume. But unfortunately, there's always some kind of a pile of loss. But you can also store solid hydrogen. So that's certainly going to be really safer in terms of using in residential applications. But when you transport, you can actually transport them through containers or trailer trucks and things like that by road, or you could transport hydrogen through pipelines. So transporting fuel through pipeline is a well-known technology these days, and it's happened. Only thing, there needs to be certain modifications in the existing pipelines. Or using ocean, so using ships also can be means to transport the hydrogen from one place to another to the site where you could have various applications. So a little more details here, but if you look at the one on the road, you can have say tube trailers, or you can have the metal hydrides and then transport, or you can also transport the liquid hydrogen in the truck trailers, or using pipelines. So you can also use underground or above ground pipelines. And certainly you could transport the hydrogen in liquid form, or you can also transport liquid organic hydrocarbon carriers. So I think there are some materials like cyclohexane and things like that that can be used for transporting hydrogen-rich fuel, and then you can reform the cyclohexane-like chemicals to produce hydrogen at the site where you want to use the hydrogen. In terms of storing hydrogen, this is mainly for metal hydride. So you can have a physical storage system that is mainly by using hydrogen in liquid form or in high pressure compressed form. Or you could also use the material storage based, so solid hydrogen or liquid organic hydrogen. So like cyclohexanes or heterocyclanes or formic acid and materials like this. In the solid state storage of hydrogen, you can have a physisorption and a chemsorption. But most of the materials are related to graphene or any kind of nanomaterials or MOFs or chemical hydrides or intermetallic compounds or multi-component systems. But again, the major materials are like mesh metals or different materials which could store higher amount of hydrogen per unit mass of these hydrogen storage materials. So here actually you can see the capability and also the targets specified by the US Department of Energy for effectively storing hydrogen in the metal hydrides. So gravimetric capacity, that's like 55 grams per kilogram of material. Our ultimate goal is to store a higher amount, that's up to 75 grams per kilograms of materials. Or if you look at the operating temperature, so not extremely high or not too low temperature, delivery temperature is you slightly warm up the material with the hydrides and the hydrogen could easily come out for various applications. So cycle life, it has to work for at least 5 years effectively to almost 95% efficiency. And when you recharge the metal hydride, that should happen within probably 3 to 5 minutes for storing 5 kilogram of hydrogen. So this 5 kilogram of hydrogen is nothing but the fuel amount which can be used in a typical automobile or a car for driving about 350 miles range per tank or per tank of metal hydrides. So this one is a little more crowded, but we try to incorporate too much of details pictorially, where it tries to tell you how we transport hydrogen in liquid form, store it after you produce hydrogen from various means, whether it is produced from large scale from steam methane reforming or any other renewable sources, and then transport liquid hydrogen tank trailers, and then store it in the place where you want to use. And once you open, it goes to the room temperature and then delivered to the applications. Or if you store the hydrogen in compressed form, you can store it at 160 bar in the beginning, and then you can raise the to go to high pressure. That's mainly to keep the cost also under control. Or you can also store hydrogen in salt caverns. There are multiple underground caverns around the world, so you can still use the natural or man-made caverns to store hydrogen and then distribute hydrogen after compressing it to the required pressure. So the delivery sites certainly require, depending on the application, you can have 350 or 700 bar pressure. Okay. The low pressure to high pressure again is done by the compressors, but depending on the application, you can have a 700 bar hydrogen dispenser. So there are, I think there are about 600 hydrogen dispensing stations around the world right now. And most of the dispensing units have 2 outlets, one with 700 bar, another one with 350 bars. So that again, it depends on what kind of vehicles and what kind of requirements are needed for various applications. So, typically the cars need cars or SUVs probably need high pressure. That is to minimize the refilling time to less than 3 minutes. So if the smaller letters are visible here, so this is for a typical car. So storage tank volume is 125 liters of water volume. Otherwise, it is for storing 5 kilogram of hydrogen at 700 bar. That 700 bar pressure, 5 kilogram, can drive the car up to 600 kilometers. So that's again pretty much the same compared to the internal combustion engine based automobiles. So this, in most of the stations, there are almost about 50 to 60 vehicles are being filled. So that could need about 200 kilogram of hydrogen per day. So that amount can be drawn from probably stored trailer behind the station. So in other words, you do not have to really produce hydrogen on site, but there are also hydrogen stations in California where the hydrogen is being produced by electrolysis from the electricity produced on site by solar PV modules. So, like we saw in a slide, that the hydrogen can be transported from place of generation or place of production to the site. So this one is actual. So this hydrogen, which was actually produced by coal gasification in a place in the southern part or southeastern part of Australia to Japan, and the liquid hydrogen is actually being transported. That's almost 5,000 nautical mile. The cost to transport is not very high. So I think I'll also show you some numbers on how the cost compares when you transport hydrogen by various means. Okay. So if you look at, say, on the left-hand side, this is the full cost of hydrogen per kilogram. So that includes hydrogen generation, hydrogen storage, hydrogen transportation, and dispensing cost. So if you look at the red line, which is based on the hydrogen pipeline, so this is typically for a longer distance, right? So liquid hydrogen via ship, that's on the top. But again, for longer distance, if it can be transported through ocean, the cost from lower to longer distance remains almost the same. Or you can actually use ammonia. You can produce ammonia and transport ammonia. And hydrogen by pipeline. So for shorter distances, it's okay. But if you have to go to the longer distance, it is going to be too expensive. But the graph on the right-hand side gives you the cost of hydrogen distribution. So this is only distribution cost. The lowest or the mediocre value is mainly for the liquid organic hydrogen carriers. But if you look at the one which is a hydrogen, gaseous hydrogen in truck, so for longer distances, certainly, the cost is going to be lower. So if it's going to be used within the land, within the probably shorter distance, it makes more sense to transport hydrogen by truck or compressed or liquid hydrogen trucks. Utilization mainly for global energy systems. I think it's similar to the slide which we saw, but again it adds a little more details on how the applications are incorporated in industrial fuel cell based for various transportation applications, including drones, aviation, maritime, materials handling, automobiles, cars or trucks and trains and buses. And also, as I said, hydrogen can also be effectively used in the internal combustion engines with a slight modification of the engine by direct injection of hydrogen, or you can use it effectively in gas turbines. And also, you can use the hydrogen to produce thermal energy. And certainly, hydrogen economy or implementing hydrogen economy towards meeting the global energy requirement also comes up with various challenges, but you can also have a SWOT analysis to understand what is involved in terms of challenges. So all the challenges can certainly be considered as opportunities for R&D and demonstrations. So if you want to look at automobile, mainly fuel cell, so this is now possible. So automobiles are available in California or wherever we have access to hydrogen filling stations or hydrogen refilling stations. So fuel cell vehicles are now being designed and manufactured specifically for fuel cells, not retrofitted with the existing vehicles. So smaller vehicles probably are not perfect for hydrogen because of various complications. But again, there are almost 2,500 fuel cell vehicles which are operational today in the state of California and the US. So this slide gives you, commercial vehicles. So this is about $55,000. So this Toyota Mirai means the future. So this vehicle could drive about 335 miles range. That's about 500 kilometers using protonic chain membrane fuel cell stacks, which also has about 5 kilogram hydrogen in a full tank. Okay, so you can also see the fuel cell stack and the hydrogen. So this is actually in the front seat. All these are very safe, as I said, because of the lower density. So hydrogen, even if there is a leak, certainly there won't be any leak, but even if there is any misuse or any catastrophic conditions, hydrogen will just escape to the atmosphere. So fuel cell vehicles have some requirements specified by Department of Energy in the US, and all these companies like Hyundai have 2 models, Honda Clarity and also Toyota Mirai. So all this, it gives you the amount of hydrogen and also the range which can be driven or which can be by the vehicle. And all these, vehicles also have battery systems. So batteries are again complementary to the fuel cells in the electric vehicle because fuel cells cannot meet high power demand. So batteries are needed for accelerations or starting. But otherwise, the fuel cells can meet the energy requirements or range extension requirements. So this is the cost and also durability and all those things. So again, various countries have come up with targets. So these $40 or $30 ultimately is the target from the US Department of Energy. Power density or peak power efficiency, like 70% or power density up to 850 watt-hour per liter. And the vehicle should also start at minus 30 degrees Celsius. So that's one of the very stringent requirements. So Japan, new energy development organization. So, and also the fuel cell and hydrogen joint undertaking in Europe, and also most, in the Ministry of Science and Technology in China. So major countries have come up with various targets for fuel cells if they have to operate in the automobile applications. So Europe has a huge target in terms of increasing the number of large-scale buses. So that is certainly going to happen in the coming decade in terms of increasing the numbers. So one of the, I think, large-scale application is actually the trucks, which is going to be a monster with a huge fuel cell stack. So this is actually the Hyundai fuel cell truck. This is named as a Neptune. So with a fuel cell of about 200 kilowatt protonic chain membrane fuel cell with a motor, which is a traction motor, 350 kilowatt. So that's a huge. And the vehicle could actually run for 400 kilometers with one tank of hydrogen gas, which can be refilled in 7 minutes. So tank capacity is of almost 33 kilogram hydrogen at 350 bar pressure. And in fact, there's a huge company which is coming up in the state of Arizona, Nikola Motor Company. So they are actually, building the trucks with fuel cells without actually making it commercial yet. They have probably 2,000 trucks pre-ordered. So these fuel cell again are protonic chain membrane fuel cells. And in fact, when they demonstrated last year in Phoenix, Arizona, it was a huge gathering with more than 3,000 people from all around the world to witness and also order these vehicles. And this is happening. So, hydrogen and the fuel cells are coming to the energy scenario, both for transportation and also for stationary applications. So again, if you talk about stationary and residential applications, again, the hydrogen can be, if you have smaller home, hydrogen can be produced by PV generated electrolyzer. And also, you can use smaller batteries to store energy in case you want to use the inverter or, converter, DC-DC converter directly. or additional electrical energy produced from PV modules can also be used in the electrolyzer to split water by electrolysis to produce hydrogen that can be stored in the hydrogen tank. Once you have the hydrogen in the tank, you can use a fuel cell during any time. So about the 5 kilowatt fuel, 5 kilowatt system is typical for a larger home in any countries. So in other words, you can have a completely off-grid home and make it with a 100% renewable energy for all applications. So this is again, you know, I'm not going to go into this, but you can have a direct injection of liquid, hydrogen into the internal combustion engine fuel inlet. So, you know, with a little modification, but otherwise you can also have pressure boosted hydrogen internal combustion engine. And also you can have a hybrid vehicle with a fuel cell, battery, and also internal combustion engine. So internal combustion engine operates with the hydrogen, and that's a smaller battery. And you can have, say, hydrogen and the battery, but again, you know, there's no fuel cell, but instead you have an internal combustion engine. So in other words, again, you know, you can have a zero emission vehicle with the various combinations. So these are happening. So these are all projects carried out or being carried out in Europe. So one was Miranda, High Dime, High Seas, and the flagships. So the flagships again is operational right now. High Seas 3 is also being done right now. So these are all with the large scale proton exchange membrane fuel cells from, say, about 200 kilowatt all the way up to 600 kilowatt fuel cell stack. So these fuel cell operated ships are being supported heavily by two projects in Europe using Horizon 2020 and also FCH joint undertaking projects. So like I said, you know, hydrogen can be directly used for generating thermal energy. If you look at the, you know, color of the flame, so this is slightly lower endurance. So that's from the natural gas. You can actually enrich the natural gas by mixing with hydrogen, or you can also use pure hydrogen to produce a high amount of thermal energy. In fact, the thermal energy or energy content of the hydrogen is 2.5 times that of the hydrocarbon fuels like gasoline, diesel, or methane. So this one we want to, you know, give a very thorough, but also with a little bit of timeline, but you know, not quantitative. But you know, if you look at say from the bottom to the top, so the bottom is kind of gray hydrogen, and then blue hydrogen, and then once you go to the top, this is a greener hydrogen. So, like I said in the beginning, gray hydrogen is being actually made in large scale from the fossil fuel. Once that is produced, then you can deliver and distribute from trailer trucks, or you can use a pipeline, or you know, if you have access or if you need the requirement on site, you can actually refill the electric vehicles like cars, buses, and trucks. Or if you in the midterm, that may be after like 5-6 years, or maybe after 10 years, if you produce hydrogen from the biomass, you can still, make use of that hydrogen and store it. Maybe, you know, in the large scale, you can still use the underground salt caverns, or you can use pipelines and then use it for various applications in large scale for shipping or transportation, or steel making, or ammonia production, or urea production, or dimethyl ether production, DME, or methanol production. And at the end, so maybe after the 20-30 years, right? So that's what we consider as a long-term. Hydrogen is certainly going to be made in large scale from electrolysis by the electricity produced from all renewable means, and then use the hydrogen or transport hydrogen through the pipelines and transport electricity, or have a transmission lines, or also have a CHP. So that is to make use of the combined heat and power from the fuel cell or other thermal energy systems using hydrogen as a feedstock, or making use of the thermal energy for various applications on the road or on the ocean or on the air. So we have also listed some barriers in terms of fuel cell costs or distribution network lacking. And also capital investment is certainly a large factor in terms of holding on to the easier or quicker or near-term implementation of the hydrogen economy. Certainly, integrating the energy vectors into various application areas are one of the major barriers as we see. And target is always the 2050. So from 30 years from now, things are certainly going to make a huge change in meeting the global energy requirements. So this again, gives a little more. This is at the US. So if you look at various timelines, so this is only like a 2-3 years, and 23 to 25, 26 to 30, 31 and beyond, and then 2050. So if you look at the ones in red, so all the red ones are early commercialization or under development, whereas the ones in blue are the ones which are already matured. So that means, material handling equipments are again ready to use, batteries or certainly fuel cells. Our power generation is actually available for large scale with more than 10 megawatt fuel cell systems in operation in a small town in South Korea, and various hospitals and data centers in the US. And certainly train is actually operational in Germany, and all these ones in blue are already available. So there are planes which are again being evaluated. So again in probably 5 years it's going to be still red, but after 26 and beyond, so there will be a plane. I think Boeing and also Airbus have already demonstrated fuel cell powered commercial airlines, smaller airplanes. And as you see here towards the end, so that's not too far beyond 10 years, right? So this is in the US, and most of the countries think this is going to be feasible. Okay. So to summarize, certainly the electrolysis by water splitting using electrical energy generated from renewable resources, complemented by steam methane reforming technology, would be the major production methodology for large scale production systems. And as of now, hydrogen in compressed form is commercially available because the limited use is slightly limited. And if you have to transport hydrogen, certainly compressed hydrogen is the best option right now, considering the cost, mainly for automotive applications. And hydrogen can be used effectively in fuel cells for various transportation and also stationary applications. And hydrogen can also be used, in the internal combustion engines and gas turbines, and also for producing thermal energy. So if you look at this slide, I think hopefully the numbers are readable. So we try to calculate the amount of carbon dioxide which will be emitted by a car per year, because per year the typical car runs about 11,400 miles. So in other words, each car will produce 4.7 metric tons per year. So there are about 1.3 billion number of cars in operation around the world, but certainly not in the COVID-19 pandemic situation. So certainly, these are numbers which will be mind-boggling. So you could do a math by 4.7 metric tons times 1.3 billion number of cars. If you want to have an idea about how much carbon footprint we are making in the transportation sector alone. But if you have to use, zero emission vehicles, certainly, there's no emissions, so CO2 is certainly zero. And, if you use all the renewable energy combining, with even homes, with building integrated solar PV modules or wind turbines, and that's for using electrolyzer for producing hydrogen. You can use 100% off-grid homes also. So certainly, I mean, decision is ours, so we could make the carbon footprint carbon neutral or negative carbon if we have, if we put in our efforts. So, like I mentioned in the beginning, we took this, effort in the past probably like more than 6 months from authors around the world. So we have, 2 parts are already, part 1 of the paper is already published in the International Journal of Hydrogen Energy. So, if you are really interested, and part 2 is already in press, part 3 is in review. So the authors are Hassan Nasir from Pakistan, Navaneethan from Norway, Sintrala from India, United Trichy, Sujin from Madurai Kamaraj University, Nicholas from Belgium, from Fuel Cell and Hydrogen Joiner, checking of the European Union, Elena from Romania, Marte from Marte and Christina Flax from Aalto University, Finland, Pertti and also Tanya, both again from Aalto University, Finland, Gilberto from Brazil, Kaido from Estonia, Yamre, our editor-in-chief of the International Journal of Hydrogen Energy in the USA, and also Alfredo from University of Sevilla from Spain. So I would like to thank all of them for the contribution. Thank you very much.
Thank you, Professor. I would like to ask some of the questions from our audience.
Okay.
Sir, how could we manage?
Whether I can see the questions? No. But okay, yeah, you can read them and you can answer.
Yes, sir. Sir, how could we manage the sub-freezing temperature in cold weather operation of fuel cell electrical vehicle?
That's right. So, in fact, Toyota demonstrated their fuel cell car operation in Canada in the winter a couple of years ago, when the ambient temperature was minus 25 degrees Celsius. So the fuel cell can start at sub-zero temperatures, but obviously the power output is going to be slightly lower. But as long as the vehicle can start with the lower power, the fuel cell can internally get warmed up because of the internal resistance. So in other words, fuel cells can operate at sub-zero temperatures. And in fact, fuel cells can also operate in extremely warmer temperature, because I think it was the Mercedes-Benz in 2015, which was actually demonstrated in the Death Valley in California, where the temperature was 150 degrees Fahrenheit. So fuel cell could actually operate at a sub-zero temperature or extremely stringent high temperature. In the high temperature, actually the driver and the co-passenger made the water from the fuel cell for drinking.
Sir, how about the performance of these type of vehicles?
Can you repeat? I couldn't hear.
How about the performance of these fuel cell electrical vehicles when compared to them?
So in terms of fuel cell operated vehicles in comparison with the internal combustion engines, right now the cost is slightly higher. So maybe like 20% or more for a typical car. But certainly we need to have the hydrogen refueling infrastructure. But in terms of performance, this is a high performing vehicle. So in terms of acceleration, or in terms of distance per tank of hydrogen, or comparing with the tank of gasoline, it's huge advantage, because also very comfortable, because it's an electric motor, so there is no noise, and also in the tailpipe the carbon dioxide coming out is zero. In fact, when vehicle companies or electric vehicle companies, the fuel cells demonstrate or advertise, you could see that the tailpipe has droplets of water instead of CO2 or instead of carbonaceous or noxious or sulfur oxides. Performance, durability is also very good, because the requirement is that the fuel cell operate continuously for 5,000 hours with a 30 miles per hour speed. That means 150,000 miles overall. That is more than 15 years. So performance is amazing in terms of comparing them with internal combustion engine based cars.
Next question, sir. Hello, sir. Sir?
Yes.
Yeah,
Sir,
yeah,
could
please.
you hear me?
Yeah, can you hear me?
Yes, sir. Yes, sir. Sir, energy efficiency is a challenge for hydrogen storage approaches. So what about the efficiency in your technique, sir?
So the overall efficiency is still relatively higher because the hydrogen generation in electrolyzer can be all the way up to 95%. Or in terms, if it's alkaline fuel cell, people have reported up to 98%. Hydrogen storage with these materials, if you consider adsorption, desorption, the reversibility is again, more than 90%. And in the fuel, if you consider CHP with, heat also for various other applications, both electricity and heat, you can go above 80% depending on the fuel cell type. So overall, there's no issue. But the cost is because of the materials and also because of the lower volume compared to gasoline-based or natural gas or other fossil fuel-based systems. The volume is lower, so it is slightly higher.
So what all the environmental parameters you took care of?
So environmental parameters are mostly the carbon footprint. So, again, if you make use of steam methane reforming for producing hydrogen, CO2 is a major issue. But again, if you look at all the pollution level or CO2 level, the CO2 level is a maximum in the cities. So that's again, works perfectly for fuel cell or again, battery operated zero emission vehicles where you can make this hydrogen in a place where you have the fully grown forest where the carbon dioxide can be utilized. Or carbon dioxide can be secured and stored and then transport hydrogen or use the hydrogen for powering the automobiles or transportation sector where we have the huge population. So in other words, in the cities, the carbon dioxide emission can be very well controlled if we have a means to produce hydrogen by steam methane reforming or from any other fossil fuel.
Thank you so much, sir.
Ma'am, I have a question.
Yes, sir.
Sir, you talked about hydrogen for thermal applications.
Yes.
You showed some burner and so on.
Yes, yes.
My question is, hydrogen is regarded as a high-grade energy. Is it advisable to use it for thermal applications?
You need to make a small change actually because the burning characteristics are slightly different. So we have a lot of literature on that. In other words, if you have a burner, you cannot just feed hydrogen. So we need to make some changes.
Sir, my question is,
in England, there are several places where hydrogen or hydrogen enriched natural gas is being used for generating thermal energy.
No, sir, my question is different actually. Thermodynamically, hydrogen is considered to be a high-grade energy, high-quality energy.
Yes.
So, whereas the thermal application will be able to get thermal energy with the inferior fuels. What is the rationale behind using hydrogen for thermal applications? That's what my question was.
Oh, okay. So especially in places where you want to avoid CO2 emission, all these, commercially available fuels have a carbon content. So certainly during combustion burning, thermal energy generation is also along with the CO2. So the major rationale behind using hydrogen is mainly to avoid or to eliminate the CO2 emission, to reduce the carbon. Thank you.
Okay, thank you, sir. Thank you very much. So I want to join my colleague, Dr. Vijayalakshmi, in thanking you. I appreciate very much, because you attended our inaugural session, and again today is the last session you are giving. So practically it was 2 days, but it was last night and today morning. No, thank you
So
very much.
I already gained one more day.
Okay. Okay. Thank you. Thank you very much.
Thank you and good night. Yeah.
Thank you
Bye-bye.
so much, sir.
All right.
Over to Dr. Murugavel. Do you want to make any announcements for the participants?
No, sir. Like I think conveners can do it, sir, in case if they have any information to be passed on.
Tomorrow's session starts at 2 p.m., sir.
Okay.
I'd like to invite all the inform the participants to join.
Okay. 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 Fine. Okay. Then now goodbye to all of you.
Okay, sir. So we shall meet at 2 o'clock tomorrow.
Yeah.
So I'm ending the session for all, sir.
Yes, thank you for the participants.
Okay.